The domain that is deep learning is gaining rapid momentum in today's world. The goal of deep learning is to impart a sense of human-like thinking into the machines. When handling large amounts of data, machine learning might just not be able to understand the complex features present. This is where deep learning steps in and handles a large amount of data with ease. In a world surrounded by data, this is a domain that finds its applications literally everywhere. With this comes a huge demand for proficient deep learning experts. Now, keeping this in mind, we here at Great Learning have come up with this deep learning tutorial to help you completely understand the theoretical and the practical aspects of the domain itself. Use this as a guide to understand the complexities of this domain in a really easy to understand and simple manner.
Before we get started, I want to introduce you to Great Learning Academy, a free initiative by Great Learning. You can access over 200 plus courses with 1000 plus hours of free content on trending high demand domains absolutely free. Register now to complete the course and get your free certificate of completion. Check out the link in the description of the video below. If you haven't yet subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notifications bell so that you do not miss out on any new updates or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing. So make sure you share this video with your friends and colleagues. Make sure to comment on the video if you have any queries or suggestions, and I'll respond to your comments. Now we'll start off with this library called as NumPy, which stands for Numerical Python. And as it is stated over here, it is the core library for numeric and scientific computing. So whatever numeric or scientific calculations you'd have to perform, NumPy should be your go-to language. And this library called as NumPy consists of multi-dimensional array objects and a collection of routines for processing these arrays. So let's go ahead and create our first NumPy array. So you can have a single dimensional NumPy array or a multi-dimensional NumPy array. Now, we'd have to start off by importing this library. So to import NumPy, we'll type in import NumPy as NP. So this NP which you see over here is known as the alias. So we are importing the library NumPy with this alias NP. Now, this NumPy library has a lot of methods, and one method is called the array method. And with the help of this, we will be able to create the NumPy array. All we have to do is type in np.array, and inside this I am passing in the list of values starting from 10 going on till 40, and I'll store it in this object called as n1. And when I print it out, I get the result 10, 20, 30, 40. Similarly, I go ahead and create a multi-dimensional array. So here we are passing in a list of lists. So here we had a single list. Here we are passing in a list of lists. So as you see, we have a list over here, and inside this we have two more lists. The first list comprises of the elements 10, 20, 30 and 40, and the second list comprises of the elements 40, 30, 20 and 10. And when I print it out, this is how I get this multi-dimensional array. The first list is present in the first row and the second list is present in the second row. Now let me go to Jupyter Notebook and implement these two. Let me just add a comment over here. I'll name it as NumPy. Now I'd have to import the NumPy library. So I'll have import NumPy as NP, and let's just wait till this library is loaded. Now that this is loaded, I can go ahead and create the NumPy array. So for this, I'll have to use np.array, and inside this I'll be passing in a list of values. So I'll pass in 10, 20, 30 and 40, and I'm storing it in this object called as n1. Now let me print out n1 over here. And as you guys see, I have successfully created this NumPy array, which over here the values are 10, 20, 30 and 40. And just to be sure, I'll go ahead and check the type of this NumPy array. So I'll have type. Inside this, I'll pass in n1, and as you guys see, we get the result numpy.nd array. So nd array stands for n dimensional array. Now we'll go ahead and create a multi-dimensional array over here. So to create a multi-dimensional array, we'd have to pass in a list of lists inside this np.array method. So I'll have this outer list. Inside this, I will create two lists. So the first list, let's say, comprises of the elements 1, 2, 3 and 4, and the second list comprises of the elements 4, 3, 2 and 1. Now I'll just print out n2 over here. And I have created this multi-dimensional array where all of the elements from the first list are present in the first row and all of the elements from the second list are present in the second row. Now that we have created these NumPy arrays, we'll now see how to create or how to initialize a NumPy array with different ways. So now let's say if I want to initialize a NumPy array with only zeros, then we have a method called as zeros. It's very intuitive, isn't it? So here we are importing the NumPy array, then we are using np.zeros and it takes in two parameters. So these two parameters basically indicate the dimensions of the NumPy array. So if I want to create a 1 cross 2 NumPy array where all of the values are zeros, then I can just go ahead and type in np.zeros and inside this I'll pass in the dimensions, which is 1, 2, and I get a 1 cross 2 NumPy array where the values are only zeros. Similarly, over here, I am creating a 5 cross 5 NumPy array where all of the values are zeros. So I'll just use np.zeros and inside this I'll pass in 5, 5. Now let me go ahead and implement this in Jupyter Notebook. Here I'll add the comment np.zeros. Now I'll go ahead and let me just create this in n1, and inside n1 I'd have to use the np.zeros method, and over here I'd have to pass in the dimensions. So the dimensions would be 1, 2, and let me go ahead and print out n1 over here. So as you guys see, I have successfully created this NumPy array. Now if I want maybe a NumPy array with a different dimension, so the method would be the same. I'll have np.zeros over here, and inside this, let's say I want to create a 3 cross 3 NumPy array which consists of only zeros, and this I'll go ahead and store it in this object called as n2. Now let me print out n2 over here, and we have a 3 cross 3 NumPy array which comprises of only zeros. Now if I want to initialize a NumPy array with the same number, then we can go ahead and use the full method. So here I am using np.full, and this takes in two parameters. The first parameter is the dimension of the NumPy array. The second parameter is the value which we'd want to insert into this NumPy array. So here we are creating a 2 cross 2 NumPy array where the value is filled with 10. So as you guys see, it's a 2 cross 2 NumPy array where we only have tens. So it's time for np.full. I'll just type in np.full. I'm adding a comment over here. Then let me add np.full, and I'd have to give in two parameters. Let's say I'd want a 4 cross 8 NumPy array, and I'd want the value 5 inside this. Now I'll store this in this object called as n3, and I'll just print out n3 over here. And as you guys see, I have created a 4 cross 8 NumPy array where the value is only 5. Similarly, if I want to initialize a NumPy array within a particular range, then I can go ahead and use the arange method. So here, as you guys see, I am using np.arange, and this again takes in two parameters. The first parameter is the initial value from which the range has to start. So here when I give in 10, as you guys see, the range starts from 10. And when I give in 20, so here again you'd have to remember that 20 is exclusive, or maybe the second parameter is exclusive. And since this is exclusive, we'll only have values starting from 10 and going on till 19. And that is why 20 is not included in this result over here. Now we can go ahead and add another parameter. So here the initial value is 10, the final value is 50, and we have the skip value. So the skip value is 5, which would mean that after 10 we'll have 15. So 15 plus 5 becomes 20, 20 plus 5 becomes 25, and that is how this keeps on proceeding. Now when we reach 45, when you add 5 more to 45, that becomes 50. And since 50 is exclusive over here, that is why we end at 45. But on the other hand, if we had given the final value as 51, then we would also have the element 50 over here. So let's go ahead and implement arange method over here. np.arange, and I'll store this in n4. Now I'd have to use np.arange, and I'll go ahead and give in the initial value as, let's say, 100. Then I'll give the final value as 200, and I'll print out n4 over here. And as you guys see, we have all of the numbers in sequence starting from 100 going on till 199. Now if I actually want the value 200 to be included in this as well, let me make the final value to be 201. And as you guys see, this time the range starts from 100 and also includes 200 over here. And we can also add a skip value. Now let's say if I given the skip value of 10. So here after 100 we have 110, then 120, and this goes on till 200. Now instead of 201, if I keep the final value as 200, we see that this numpy array ends at 190 because 200 is exclusive. Now we can also go ahead and initialize a numpy array with random numbers. And to initialize numpy array with random numbers, we can use random.randint. So here we are invoking np.random.randint, and over here we have three parameters. The first parameter is basically, and over here we have three parameters. The first two parameters basically indicate the range from which we would want the random numbers. So we would want the random numbers in this range of 1 to 100. And this third parameter would tell the Python interpreter how many random numbers do we need. So in the range of 1 to 100, we would need 5 random numbers. And as you guys see, this is the result which you get over here. So we have 95, 88, 26, 22 and 76, which are 5 random numbers generated between the range of 1 and 100. I'll add this comment random. Now let's go ahead and initialize a numpy array with some random numbers. So I'll have np.random.randint because I want a random set of integers, and this will take in 3 parameters. Let's say I would need values between 50 and 100, and I would need 10 random values over here. And let me store this in n5. Let me go ahead and print out n5 over here. And as you guys see, I have 10 random values which are generated between the range of 50 and 100. Now, similarly, if I go ahead and run this again, I'll get a different set of values. As you guys see, we have a different set of values again. When I click this, we again have a different set of values. That was all about initializing a numpy array with different methods. Now you can also go ahead and check the shape of a numpy array. And to check the shape of a numpy array, we have the shape method, which again is very intuitive. So here we are creating a numpy array where we are passing in a list of lists. So in the first list we have 1, 2 and 3. In the second list we have 4, 5 and 6. So obviously we will have a numpy array where we'll have 2 rows and 3 columns, and this is what the n1.shape gives us. Now if we want to change the shape of this, then we can use the same method. So here what I'm doing is I'm typing in n1.shape and I'm changing the shape from 2, 3 to 3, 2. That is, instead of having 2 rows and 3 columns, I will have 3 rows and 2 columns. So this same shape method can be used to check the shape of the numpy array and also reshape the dimensions of the numpy array. So let me create a numpy array over here. So we would have to create a multi-dimensional numpy array. So this will be n6 is equal to, I'll have np.array, and inside this I'll have to create a list of lists. So in the first list I'll have values 10, 20 and 30, and in the second list I'll have values 40, 50 and 60, and I'm storing this in n6. Now once that is done, let me just print out n6 over here. So you guys can see this numpy array. Now I'll also go ahead and check the shape of it. So I'll have n6.shape, and we get the result that this is a numpy array where we have 2 rows and 3 columns. Now I can also go ahead and change the shape of this. So I'll have n6.shape, and over here I am changing the shape to be equal to 3, 2. Then I'll go ahead and print out n6. And as you guys see, we have converted this from a 2 cross 3 numpy array to a 3 cross 2 numpy array. So you had 10, 20, 30 in the first row. We've got 10, 20 in the first row here. So similarly, this is how this has been changed. Then we have some stacking methods over here. We have vstack, head stack, and column stack. So let's just start with vstack. So we are creating a numpy array n1 where we have the values 10, 20, and 30. Then we are creating the numpy array n2 where we have the values 40, 50, and 60. Now when we use vstack over here, this again takes in two parameters where we'll just pass in two numpy arrays inside this. So as you guys see, we are vertically stacking over here. So when I say vertically stacking, I have one numpy array on top of another numpy array. So because I'm using n1 comma n2, n1 comes at the top, n2 comes at the bottom. So this is how vertical stacking works. Then we can also go ahead and horizontally stack two numpy arrays. So n1 and n2, we've got the same numpy arrays over here, and instead of using vstack, I'm using the head stack method. I'm passing in n1 and n2, and as you guys see, 40, 50, and 60. So n2 has been stacked horizontally to n1. Then we have the column stack. So if we want to stack these numpy arrays into separate columns, so we have n1 and n2, and when I'm using column stack over here, as you guys see, n1 goes into the first column, n2 goes into the second column. And this is how we can work with these stacking methods. So I'll have to create these two numpy arrays over here. I'll have n1, which will be np.array, and inside this I'll have 1, 2, and 3. Then I'll also go ahead and create n2. So this will be np.array, and inside this I'll have 4, 5, and 6. So I have my n1 and n2 ready. Now I'll start off with vertical stacking. So I'll use np.vstack, and inside this I'm passing in n1 and n2, and let's see what would be the result. So we have vertically stacked n1 with n2. n1 is at the top, n2 is at the bottom. You can also change how these are stacked. So instead of giving n1, n2, let's say if I give in n2 and n1, you guys would see that n2 is at the top and n1 is at the bottom. Now we can similarly work with the head stack method. So here I'll type in np.hstack, and inside this again I'll pass in n1 comma n2. And as you guys see, I have stacked n2 at the back end of n1. Now, if I want n2 first and n1 second, I just have to change the sequence. So inside np.headstack, I'll give in n2 comma n1, and I have 4, 5, 6 first, and n1 is attached at the back end of n2. Then we have column stack. So I'll just have np.column stack over here, and inside this I'll pass in n1 comma n2. And as you guys see, I have n1 in the first column, n2 in the second column. Similarly, if I give in n2 comma n1, you will see that I have n2 in the first column and n1 in the second column. So this is all about stacking the numpy arrays. Now we'll also work with intersection and difference methods. So here again we have two numpy arrays. So in the first numpy array we have the values from 10 to 60, and in the second numpy array we have the values from 50 to 90. And if I want the common elements between these two numpy arrays, then I can use the intersect 1D method. So here in the intersect 1D method, I would just have to pass in these two numpy arrays, and as you see in the result, we get a new numpy array comprising of the common elements in these two numpy arrays. Then over here I have n1 and n2. If I want to find out all the elements which are unique to n1, then I can use the setDiff1D method. So here in n1 we have the elements starting from 10 going on till 60. In n2 we have elements starting from 50 going on till 90. So here as you guys see, 50 and 60 are common in n1 and n2. And if I want the elements which are unique to only n1, then I would have to use setDiff1D, and I'll pass in n1 and 2. As you guys see, I get only 10, 20, 30 and 40 because 50 and 60 are present in both the numpy arrays. I can also change the sequence over here. So instead of passing in n1, n2, when I pass in n2, n1, then this will give me all of the unique elements which are present in n2. And since 50 and 60 are common in both the numpy arrays, the resultant will be 70, 80 and 90 because these are the only unique elements in n2. So let's go ahead and work with intersect 1D and setDiff 1D. I'll just add a comment over here, intersect 1D, and I would have to create two new numpy arrays. I'll have n1 over here, so I'll have np.array, and inside this I'll pass in 1 2 3 4 5 6, and I'll have n2, and inside this I'll go ahead and create a list of elements where the elements start from 5 6 7 8 and 9. So I have these two set over here. Now that my two numpy arrays are ready, if I want to find out the common elements which are present in these two numpy arrays, I'd have to use intersect 1D. So I'll have np dot intersect 1D, and inside this I'm passing in n1 comma n2, and when I hit on run, we see that the common elements between n1 and n2 are 5 and 6. Now if I want only the elements which are common to n1, then I can use the setDiff1D method. So here I'll have np.setDiff1D, and inside this again I'll be passing in n1 comma n2, and as you guys see I have 1 2 3 and 4 which are common to only n1. Now similarly, if I want all of the elements which are only common to n2, then I can have np.setDiff1D, and I'll just change the sequence over here. Instead of passing n1 comma n2, I'll have n2 comma n1, and the only unique elements which are there in n2 are 7 8 and 9. Now we'll go ahead and perform some simple numpy array mathematics. So we'll see how to add two numpy arrays. So again over here we have two numpy arrays. In n1 we have 10 and 20, in n2 we have 30 and 40. Now if I want the total sum of all of the elements which are present in both of these two arrays, I can just directly use the sum method. So I'll have np.sum, and inside this as a list I'll pass in n1 comma n2, and you will see that the resultant value would be 100 because 40 plus 30 plus 20 plus 10 is equivalent to 100. Now if I want to find out the individual sum along the rows and along the columns, then I can use the additional parameter called as axis. So if I want to sum the values along the column, then I'll set the axis to be equal to 0. So when I have the axis value to be equal to 0, as you guys see, I have 30 plus 10 equal to 40 and 40 plus 20 equal to 60. Similarly, if I want to sum these up along the rows, then I'll set the axis value to be equal to 1. And over here I have 10 plus 20 equal to 30 and 30 plus 40 equal to 70. I'll add a new comment over here, addition of numpy arrays, and let me create new n1 over here. So I'll have np.array, and inside this I'll have 10 and 20. Then I'll go ahead and create n2, and inside n2 I'll again have np.array, and over here I'll have 30 and 40. I'd have to pass this on as a list of values, so I'll have 30 and 40 inside a list. So I have created n1 and n2. Now it's time to find out the total sum which is present along all of these. So I would have to use np.sum, and inside this I'll just pass in n1 comma n2, and actually I'd have to pass this as a list. So I'll have n1 comma n2 over here, and as you guys see, the resultant comes out to be 100. If I want to add the values along the column, so I'll have np.sum, then I'll have this list over here, I'll have n1 comma n2, then I'll have this new attribute called as axis, and I'll set the axis value to be equal to 0. And I get the resultant 40 and 60 because 30 plus 10 is equal to 40 and 40 plus 20 is equal to 60. Now going ahead, if I want to add the values along the horizontal rows. So here it will be np.sum, and over here I'll have n1 comma n2 again, and this time I'll set the axis value to be equal to 1, and I have 30 and 70 because 20 plus 10 is equal to 30 and 40 plus 30 is equal to 70. Now we'll see how to do some scalar operations on these numpy arrays. So here we have a numpy array where we have values 10, 20 and 30, and if I want to add the scalar value 1 to each individual element of the numpy array, all I have to do is add this value 1 to this numpy array, and as you guys see, n1 plus 1 becomes 11, 21 and 31. Similarly, if I want to multiply each individual element of a numpy array with a particular value, so here if I want to multiply it with 2, I'll just write down n1 into 2. So 10 becomes 20, 20 becomes 40 and 30 becomes 60. And if I want to subtract a value, all I have to do is perform n1 minus 1. So 10 becomes 9, 20 becomes 19 and 30 becomes 29. And if I want to divide it, I'll just have n1 divided by 2. So 10 becomes 5, 20 becomes 10 and 30 becomes 15. So this was some basic idea about NumPy. Now let me just see what is there in n1 over here. Let me actually add some more elements inside this. So I'll have n1 is equal to np.array, and inside this I'll have 10, 20, 30 and 40. Let me also print out n1 over here for your reference. So now that we have n1, what I can do is I will just go ahead and add some scalar values to it. And let's say if I want to add 5 more to each individual element of this NumPy array, so I'll just write down n1 plus 5. And as you guys see, 10 becomes 15, 20 becomes 25, 30 becomes 35, and 40 becomes 45. Similarly, if I want to subtract a value, I'll just write down n1 minus 5 over here. And 10 becomes 5, 20 becomes 15, 30 becomes 25, and 40 becomes 35. We can also go ahead and multiply something to this. So I'll have, let's say, n1 into 10. Let me print this out. And as you guys see, we have multiplied these values with 10. Similarly, I can go ahead and divide this with something. So if I have n1 divided by 10, so we see 10, 20, 30, 40 becomes 1, 2, 3, and 4. So this is some basic scalar operation on top of the NumPy arrays. And we can also go ahead and use some mathematical functions. So we have this mean function over here, which would give us the mean value of all of the elements which are present. So the mean value of all of these elements comes out to be 35. Similarly, if you want to find out the median, then all we have to do is use this median method. We have to use np.median, we'll pass in this NumPy, and we see that the median value comes out to be 55.5. And if you want to find out the standard deviation, I'd have to use std, and I'm passing in n1 inside std, and the value becomes 36.59. So we have n1 over here, and if I want to find out the mean value, I'll just have np.mean, and inside this I'll be passing in n1. And as you guys see, the mean or the average value of all of the elements which are present in n1 comes out to be 25. Let me go ahead and create another NumPy over here. So I'll have np.array, and inside this I'll be passing in some random values. So let's say these are all of the values which are present in n2. And if I want to find out the median of all of the values which are present, so I'll just use np.median method, and inside this I'll be passing in n2. And the median of all of these values comes out to be 5. Similarly, if I want to find out the standard deviation, so here I'll have np.std. And if I want to find out the standard deviation of this particular NumPy array, so I'll pass in n2, and you would see that the standard deviation of all of the elements of n2 would be 2.397. So till now we've worked with some basic NumPy arrays. Now let's go ahead and work with a NumPy matrix. So here we are creating a 3 cross 3 NumPy matrix, and to do that you'll again need a list of lists. So over here we'll have 1, 2, 3, 4, 5, 6 and 7, 8, 9. So this first list goes into the first row, second list goes into the second row, and third list goes into the third row. Now that we have created this NumPy matrix, let's see how can we access individual rows and columns from this entire NumPy matrix. So here, let's say if we want to access the first row, again you'd have to remember that the indexing in Python starts from 0. If we want to extract the entire first row, we'll just have n1 and inside parenthesis we'll pass in 0. And as you guys see over here, I have successfully extracted the entire first row. Similarly, if I want to extract the entire second row, then the index value for second row will be 1 and I have extracted the second row. And if I want to extract a column, then I'd have to do something like this. So in a column, I would want all of the rows. So here from this NumPy matrix, I would want the second column and all of the rows from the second column. So here, since I would want all of the rows, I'll just put in a colon over here, and since I want the second column, I'll give in the index value as 1. And as you guys see, I have extracted the entire second column over here. Similarly, if I want to extract the entire third column, the index value will be 2, and I have extracted the entire third column. Let's perform this in Jupyter Notebook. So I'll just write in NumPy matrix over here. Now that this is set, I'll have np.array, and over here I'll have a list of lists. So in the first list I will have 10, 20 and 30. In the second list I will have 40, 50 and 60. In the third list I will have 70, 80 and 90. And I will go ahead and store this in n1 again. Now I'll go ahead and print out n1 and let's see what would be the result. So this is our NumPy array which we have just created. Now if I want to access individual rows from this, I'll have to give in n1, and inside parenthesis, let's say if I want to extract the third row, then the index for the third row will be 2. I'll just have 2 over here. And as you guys see, I have successfully extracted the entire third row. Now similarly, if I want to extract the entire third column, then this time I would have to write n1, and over here, since I would want all of the records from the third column, so I'll just have a colon over here, then over here. So here you'd have to understand whatever is given on the left side of the symbol would indicate rows, and whatever is given on the right side of this comma would indicate all of the columns. So I'd want all of the rows, and all of these rows need to be from the third column, and the index for the third column is 2. And I have successfully extracted all of the elements which are present in the third column. Now we'll see how to transpose a matrix. So what is transposing? Transposing basically means when you're interchanging the rows and columns. So here, as you guys see, we have 1, 2, 3, 4, 5, 6 and 7, 8, 9. Now the rows should be interchanged with the columns. So here 1, 2, 3 which is present in the first row comes into the first column. 4, 5, 6 which is present in the second row comes into the second column. 7, 8, 9 which is present in the third row comes into the third column. Let's go ahead and perform transpose as well. So all I have to do is use np.transpose, and inside this I'll just pass in n1 over here. So as you guys see, initially I had 10, 20, 30 which was in row. This became in column. 40, 50, 60 was in second row, became the second column. 70, 80, 90 was the third row, which became the third column over here. Now we'll see how to perform two matrices. So over here we have n1 where we have the elements starting from 1 going on till 9. Then we have n2 where we have elements starting from 9 going on till 1. Now if we perform the dot operator on this, which is basically matrix multiplication, this is how the multiplication happens. So the multiplication is row by column, which would basically mean, so here we have 1, 2, 3, here we have 9, 6, 3. So it will be 1 into 9 plus 2 into 6 plus 3 into 3, which will give you a result of 30. Then again we'll have row by column. So here it will be 1 into 8 plus 2 into 5 plus 3 into 2, which will give you a result of 24. Then it will be 1 into 7 plus 2 into 4 plus 3 into 1, which will give you a result of 18. And this is how this progresses, and finally we'll get this result over here. And the dot product of n1 into n2 and n2 into n1 will be different. So as you guys see, this is the dot product of n1, n2, and this is the dot product of n2, n1. Both of these will be different. So I already have n1 over here. Let me go ahead and also create n2. So here I'll write n2 is equal to np dot array, and over here I'll have the elements in reverse order. So I'll have 90, 80, and then I'll have 70. Going ahead, I'll have 60, 50, and 40. After this, I'll have 30, 20, and 10, and I am storing this in this object called as n2. Let me also go ahead and print out n2 for you guys over here. So this is what we have. Now if I want to perform the dot product, so I'll have n1, I'll actually have, if I want to perform the dot product here, I'll have n1 dot dot. Inside this, I'll pass in n2. And as you guys see, this is the dot product of n1 cross n2. But we know that n1 cross n2 and n2 cross n1 is different. So when I perform n2 dot n1, the result will be different from n1 dot n2. So this was about matrix multiplication. Now we'll go ahead and see how can we actually save a NumPy array and then load it from somewhere else. So here we are creating this NumPy array where we have elements from 10 to 60. Then to save this NumPy array, we just have to use the save method. And over here we are saving this NumPy array with this name called as my underscore NumPy. So this takes in two parameters. First parameter is the name by which we'd want to save this NumPy array. Second is the array which we'd want to save. Now once that we save this, to load this NumPy array, we will have to use np.load, and over here we'd have to give in the name by which we save this NumPy array. So we save this NumPy array as my underscore NumPy, and we'd have to give the extension which is .npy, which basically stands for NumPy, and we go ahead and store this in n2 and we print out n2. We see that we have successfully loaded this NumPy array over here. Now I'll go ahead and save this. So I'll have np.save, and this, as we have seen, takes in two parameters. The first parameter is by which I save this. So I'll have save n1, and I would want to store n1. So I have saved this. Now if I want to load this, I would have to use np.load, and over here I'd have to give the name of the NumPy array. So it will be save underscore n1 dot npy. Let me actually remove this over here, and I will store this in, let's say, n9. Let me click on run over here. So we have an error over here. We have this error because I'd have to give this inside single quotes. Now if I click on run, we'll get the result. Now if I print in n9 over here, we finally get the result. So Pandas stands for panel data and is the core library for data manipulation and data analysis. So if you want to perform any sort of data analytical task, Pandas should be your go-to library. And Pandas provides single and multi-dimensional data structures for the purpose of data manipulation. So the single dimensional data structure is known as the series object, and the multi-dimensional data structure is known as the data frame. We'll start off by understanding about the series object. So series object is a one-dimensional labeled array. So we have already worked with the NumPy array. So in NumPy array, we had no labels along with it. It was just a simple blank array where we had stored some values. But over here in a series object, as you guys see, we have labels, or you can consider them to be indexed with labels over here for these. So first we'd have to start off by importing pandas, which is the library, and we are giving this alias as PD. So import pandas as PD. Then if we want to create a series object, we'll have pd.series, and inside this I am passing in the values 1, 2, 3, 4 and 5. And when I print it out, I get this series object. So when I check the type of this, type of S1, this gives me pandas.core.series.series. Now over here, you'd have to keep in mind that S is capital over here. So if you're given a small s, you will get an error. So let's go ahead and create our first series object. So I'll just add the comment pandas. Now our first task would be to import the pandas library. So I'll go ahead and type in import pandas as PD. Let's just wait for this to be loaded properly. Now that we have loaded the library, I can go ahead and create the series object. So I'll type in pd.series where S is capital. Inside this, I'll pass in the list of values. So let's say I'll just have 10, 20, 30, 40 and 50, and I'll go ahead and store it in this object called as S1. Let me print out S1 over here, and as you guys see, I have created this series object. Let me also check the type of this. So inside the type method, when I pass in S1, you guys would see that this is a series object. And over here, we have the labels. So the labels are 0 to 4. So by default, the label or the index starts with 0 over here. So 10 is present at label or index 0, 20 is present at index 1, 30 is present at index 2, and that is how it proceeds further. Now, since we have labels in a series object, we can change how the label of the index looks like. So over here, we just had numbers starting from 0, but instead of numbers, let's say if I wanted alphabets over here, then I can add a new attribute called as index. So over here with this index attribute, I am setting the values to be equal to A, B, C, D, E. So here initially we had index 0. 0 has been changed to A. Then we had 1, 1 has been changed to B. We have 2, 2 has been changed to C, and that is how it proceeds. So now over here, let me go ahead and change these index values. So it is the same command over here. And with this same command, all I'm doing is adding a new attribute called as index. And I'll pass in a list of values for the indices. So I'll have A, B, C, D. Let me have D over here, and I'll have E. Now, when I click on run and I print out S1 over here, you guys would see that I have changed the indices from 0 to 4 to A to E. Now we can go ahead and see how to create a series object from a dictionary. So we have already worked with dictionaries. We know that the dictionary is a key value pair. So here we'll just give in pd.series, and over here we have 3 key value pairs, A10, B20, C30. So here automatically the keys are taken as the labels, and these values are taken as the series values over here. Let me create a new dictionary. So I'll have D1, and inside D1, let me have 4 key value pairs. Maybe I'll have A and 10. Then I'll have B and 20. After that, I'll have C and 30. Going ahead, I'll have D and 40. Now I'll just go ahead and print this out. As you guys see, I have successfully created this dictionary. Now I would have to create a series object out of this. So I'll just have pd.series, and inside this I'll pass in D1, and let's see what would be the result. So these 4 keys which were present became the labels, and these values over here in the dictionary became the series values as well. Now we can also go ahead and change the index position. So similarly, as we had actually changed the index values from numerical to alphabetical. So when I given the index values as B, C, D, E, this sequence is maintained. So I have B and C first. So for B, I have the value 20, C, I have the value 30. And D, we had not created any key with this particular index. So that is why we have NaN over here. And then we have A, for which we have the value 10. So this is how we can maybe add a new index position or change the existing index positions. So this is what we had over here. This was our series object. And now what I'd want to do is, so instead of A, B, C, D, I would want, let's say, C, B, A, and D. And if I click on run, you guys see that the sequence has changed over here. Now we'll also see how to extract individual elements from the series object. So here we have all of these elements starting from 1 going on till 9. And again, you'd have to keep in mind that the indexing starts from 0. So if I want to extract this particular element over here, so the index value for this would be 3. So 0, 1, 2 and 3. And when I given the index value as 3, I am able to extract this particular element. And if I want to extract a sequence of elements over here, so if I want the first 4 elements, then I'll have S1 colon 4. This would mean that I've been extracting all of the elements starting from index number 0 going on till index number 4. And since 4 is exclusive, so that is why we will only have till index number 3. So we'll have index number 1 going on till index number 3. And if you want to extract elements from the back side, here we'll have S1 and we'll type in -3 over here. So -3 basically means third element from the end. Third element from the end, when I give in colon, this would mean third element from the end going on till the end. So this is the third element from the end over here. So that is why I'll have 7, 8 and 9. And this is how I'll be able to extract a single element, a sequence of elements from the beginning and a sequence of elements from the back. Let me just create a new series object over here. So I'll have S1 is equal to pd.series, and inside this I'll pass in a list of elements. I'll have 10, 20, 30, 40, 50, 60 and 70. Now that I have this, let me extract this element which is present at index number 3. So I'll have S1, I'll have parenthesis, then I'll just go ahead and give in the index value. So index value will be 3. And as you guys see, I have successfully extracted this particular element. Now if I want to extract the first 4 elements, then I'll just give in the colon over here and I'll have 4. And as you guys see, I have extracted the first 4 elements. Now if I want the last 3 elements over here, then I'll have S1. Then I'll have colon and I'll type in -3, which would mean the third element from the last going on till the last element over here. And I have 50, 60 and 70, which are the last 3 elements. Now we can also go ahead and perform some simple operations on top of the series object. So if I want to add a scalar value, so initially we had this series object where the number started from 1, went on till 9. And if I just wanted to add the scalar value phi to all of the individual elements which are present in the series object, all I have to do is use plus phi. And as you guys see, 1 becomes 5, 2 becomes 7, 3 becomes 8 and so on. And we can also go ahead and add 2 series objects. Over here I have S1 where the elements are from 1 to 9 and S2 where the elements are from 10 to 90. And when I perform S1 plus S2, this would add the elements which are present at the same index position. So here we'll have 10 plus 1, 11, 20 plus 2, 22, 30 plus 3, 33, and this goes on till the last index position over here. So let's go ahead and perform some basic operations on top of the series object. So I already have S1 over here. And these are the original values which are present in S1. Now I'd want to add 10 more to these existing values. So I'll just type in S1 plus 10. And as you guys see, the values, all of the values which are present in the series object have been incremented by 10. Now also I can add 2 series objects together. So in the series object, I have 7 elements. I'll go ahead and create S2. Where I'll have 7 more elements over here. So I would have to type pd.series, and inside this, let me just have 7, 6, 5, 4, 3, 2 and 1. Let me print out S2 for your sake over here. So we have S1 and S2, and when I perform S1 plus S2, this is the result which we get. So 10 plus 7 becomes 17, 20 plus 6 becomes 26, 30 plus 5 becomes 35, and this proceeds to the last index value. So that was all about the series object, which was a single dimensional labeled array. Now we'll work with a data frame, which forms the major part of all of the machine learning data science projects. So what exactly is a data frame? It is a 2-dimensional labeled data structure. And if you'd have worked with SQL or maybe Excel, you would have dealt with tabular data. And a data frame helps you to deal with tabular data in Python seamlessly. So a data frame, because this is a tabular data, consists of rows and columns. Now let's see how can we go ahead and create a data frame from a dictionary. So to create a data frame, we'd have to use this particular method over here. We'd have to type in pd.dataframe, where D is capital and F is also capital. So by any chance, if you give maybe D as small or F as small, you'll get an error. So both of them have to be in capital case. And over here, I have two key value pairs. So the first key is name, and then we have a list of values which are Bob, Sam, and Annie. Then we have the next key, which is marks. Then we have the list of values for marks, which are 76, 25, and 92. So here, as you see, the keys become the column names and the values become the records over here. So name and marks become the column names, and these values over here, the list of values Bob, Sam, and Annie, which are the values for this key, become the records of this particular column. Similarly, these values are there for this particular key, and these become the records for this particular column. So let me go ahead and create a first data frame over here. So I'll just go ahead and type in data frame. Now to create a data frame, I'd have to type pd.dataframe, and D and F both have to be capital. And inside this, I'll create a dictionary. So to create a dictionary, I would need curly braces. So the first key would be name, and I'll go ahead and give in a list of names over here. Let's say the first name is Sam. Then we have Annie. Going ahead, we have Jennifer. Now, once we have the first key value pair, I'll go ahead and also add their marks over here. So the second key would be marks, and I'll have a list of values over here. Let's say Sam has got 50 marks, Annie has got 60 marks, and Jennifer has got 70 marks. And I'll go ahead and store this in df. Let me print out df over here. And we have created our first data frame, where the column names are name and marks, and the values are these over here. And let me go ahead and also show you guys the type of this object which I've just created. So inside this type method, I'll be passing in df. And as you guys see, this is pandas.co.frame.dataframe, which basically means this is a data frame object. Now that we have created our first data frame, we'll perform some basic functions on top of a data frame. We've got head, tail, shape, and describe. So we'll just implement all of these. Now to implement this, we will be performing them on a dataset called as the iris dataset. Now to read any CSV file, we have a method called as pd.read_CSV. So here I'll have pd.read_CSV, and inside this I'll give in single quotes and given the name of the file. So the name of the file will be iris.csv. And I'll go ahead and store this in a new object called as iris. Now let me hit on run. Let me check the first 5 records which are present in this iris data frame. So if I want to check the first 5 records which are present in this iris data frame, I need to use the head method. So iris.head, as you guys see, I have the first 5 records. So this iris data frame comprises of 5 columns, which are sepal length, sepal width, petal width, and species. And we'll have 3 different species, which would be Setosa, versicolor, and virginica. So this is how we can work with the head method. Now, similar to the head method, we would also have the tail method, which would give us the last 5 rows which are present in a data frame. So here I'll type iris.tail. And when I click on run, you guys would see the index value over here. The index value starts from 145 and goes on till 149, because there are 150 records in this iris data frame. So we have extracted the last 5 records and we have printed it onto the console. Then if you want to check the number of rows and number of columns which are present in this iris data frame, we can just use the shape method. So here I'll have iris.shape, and as you guys see, this gives us a dimension value of 150, 5, which means there are 150 records and 5 columns. Then we'll have the describe method. So here I'll have iris.describe. And now when I click on run, we have all of these numerical quantities over here. So let's say if I want to find out what is the minimum value which is present in the sepal length column. The minimum value present in this sepal length column will be 4.3. Similarly, what is the maximum value in sepal length column? It will be 7.9. What is the mean value? It will be 5.84. So these are some interesting metrics which we can find out with the describe method. So now that we know this, let's actually see how can we extract individual records or individual columns from a data frame. So for that purpose, we can use the .iloc and loc methods. So let's start off with the .iloc method. So .iloc method, with the help of it, we can extract rows and columns on the basis of index. So here iloc basically stands for index location. And over here, as you see, I have a comma, and on the left side of the comma, that would indicate all of the rows, and the right side of the comma, that would indicate all of the columns. So from this entire iris data frame, I am extracting the first 3 records. So here, the rows would be 0 to 3, and 3 is exclusive over here. That is why I'll have the records where the index values are 0, 1, and 2. And similarly, the columns would be 0 to 2, which would mean the column which is present at index 0, which will be sepal length, and the column which is present at index 1, which is sepal width. 2 again over here is exclusive. So let me go ahead and extract some rows and columns with this iloc method. So we already have this iris data frame with us. Let me again print out the head for you guys so that will be easier for you to have a glance at this. Now let's say from this entire data frame, I would want the records from index number 30 going on till index number 40, and I would want the columns which are present at maybe index number 3 and index number 4. So index number 3 will be 0, 1, 2 and 3. This is index number 3, this is index number 4. So here I'll have index number 3 going on till the end because this is the last column. Let me print this out and show you guys the result. As you guys see, I have extracted all of the records starting from index number 30 going on till index number 39, and the columns which you see starts from index number 3, which is this particular columns index, and goes on till the end over here. So this is how we can extract individual rows and columns with the .iloc method. Now we have the .loc method. So instead of giving the column index, if I want to extract columns on the basis of their names, then I can go ahead and use the .loc method. And over here, when it comes to rows, you see that I've given 0 to 3. Here, when it comes to .loc, you'd have to keep in mind that 3 is inclusive. This is the only case where maybe you will find that the final value over here is inclusive. So when I given 0 to 3, you will get all of the records starting from index number 0 going on till index number 3, which is also inclusive. And over here I'm giving in the column names which are sepal length and petal length, and that is what I'm extracting over here. So I have this iris data frame, then I'll just go ahead and use this .loc method. Now from all of these records, let's say I'd want all the records starting from index number 10 going on till index number 20, and the columns which I'd want to extract are sepal length and petal length. I'll just have sepal.length over here, and the next column which I want would be petal.length. Let me hit on run, and as you guys see, I have all the records starting from row number 10 going on till row number 20, and 20 is also inclusive over here. And the columns which I've extracted are sepal length and petal length. Now we'll see how to drop a particular column. So many a times it would happen that not all columns which are present in a data frame are important. So from this entire data frame, if we want to drop a particular column, then we can just go ahead and use the drop method. So here I'll have iris.drop, and I am dropping or removing the sepal length column from this entire data frame. So here, when I set the axis value to be equal to 1, this would basically mean that I am dropping a column. So if you want to drop a row, then you'd set the axis value to be equal to 0. And if you want to drop a column, then you'd set the axis value to be equal to 1. So if from this entire iris data set, again, I'll show you guys the head of this so that you guys can have a glance at all of the columns which are present over here. So from all of the columns, if I want to drop the species column, all I have to do is type in iris.drop, and inside this I'd have to give in the name of the column, which would be species, and I'd have to set the axis, which will be equal to 1 because I'm dropping a column. And as you guys see, I have successfully dropped the species column from this entire data frame. Now similarly, if I want to drop some particular rows which are present in this data frame. So here, as you guys see, the index value, it starts from 0, goes on till 4 over here. But if I want to drop the row indexes of 1, 2 and 3. Here, as you guys see, I have two parameters. First parameter, I'll give in a list of all of the indices that I'd want to drop. So I'd want to drop the index value 1, index value 2 and index value 3, and the resultant which you see over here, after 0 we directly jump on to the index number 4. So now from this entire data frame, this what you see over here, I'll just use iris.drop, and I would want to drop the index values of 1, 2 and 3, and I'll set the axis to be equal to 0. And when I hit run, you would see that after 0, we are directly jumping onto index number 4. So this is a very simple example of how to drop some records and how to drop some columns from your data frame. Now we'll go ahead and work with some simple pandas functions. So from the iris data frame, if I want to find out the mean values of all of the columns, I can just go ahead and use the mean method. Similarly, if I wanted the median values of the records of all of the columns, then I'll just go ahead and use the median method. Similarly, if I wanted to find out the minimum value, I'll use the min method. And if I wanted to find out the maximum value, I will use the max method over here. So very basic operations. So when I use iris.mean, this would give me the average values of all of the columns. So average sepal length of the entire data frame is 5.8. Average sepal width is 3.05, average petal length is 3.75, and average petal width is 1.19. Similarly, if I want to find out the minimum value of all of the columns, so I'll have iris.mean, and this will give me all of the minimum values. And if I want to find out the maximum values, I'll just go ahead and type iris.max, and this would give me the maximum value of all of the columns over here. So I've got the mean value, the minimum value, the maximum value, and I can also find out the median value. So I'll just type in iris.median, and when I click on run over here, this would give me the median values with respect to all of the columns which are present. Now we will get on with this library called as matplotlib, which is mostly used for data visualization. And with the help of this library, we can create stunning plots such as bar plots, scatter plots, histograms, and a lot more. So we'll start off by creating our first plot, which will be a line plot. So we would require two libraries over here. The first library would be NumPy, because we would want to create our data with this NumPy library. Then we would import this pyplot submodule from this matplotlib library. So we'd have to type in from matplotlib import pyplot as plt, and the alias which I'm giving for pyplot is plt. Then I'll create two NumPy arrays over here. The first NumPy array will be X, and I'm creating this NumPy array with the help of this np.arange method, and the range will be from 1 to 10. And then I'll create the next NumPy array, which is basically 2 times of X. So all I have to do is multiply X with 2, and then I'll get Y. So here we have 1, we have 2. 2 becomes 4, 3 becomes 6, and this is how it proceeds. Now once we create the data, all we have to do to create a line plot is use this plt.plot. So we'll have the plot method in this pyplot module. So this takes in two parameters, which are X and Y. So we have already created our data X and Y. So X will be plotted on the X axis, Y will be plotted on the Y axis. And as you guys see over here, X goes from 0 to 10 and Y goes from 1 to 20 over here. And we see that there is a linear relationship between X and Y, or in other words, as the value of X increases, the value of Y also correspondingly increases. So let's go to Jupyter Notebook and create our first line plot using matplotlib. So I'd have to start off by importing the required libraries. So I would need NumPy. Here I'll type import NumPy as np. And after this, I would also require matplotlib. So I'll type from matplotlib import pyplot as plt. Let me write those spelling properly over here. And once I've imported these two libraries, I'd have to create the data. So first I'll have x, and this I'll be creating with np.arange, and the range will be from 1 to 10. Since I want the numbers from 1 to 10, I'd have to give the value 11 because 11 will be exclusive over here. Then let me just go ahead and print out x for you folks over here. As you see, we have the numbers starting from 1 going on till 10. Now, if I have to create y will just be 2 times of x. So here I'll have 2 into x, and then let me print out y for you folks over here. And as you guys see, this is all of the elements are just 2 times of the elements which are present in x. Now, since I have to create a simple line plot, I would have to use plt.plot, and this would take in 2 parameters which are x and y. So this data would be plotted onto the x-axis, this data would be plotted onto the y-axis, and I'll just show this as a result. So as you guys see, we have this object x mapped on the x-axis, this object y mapped on the y-axis, and this is the corresponding line plot. Now that we have created this, we can also add the title x label and y label. So we'd have to use this title method. So we'll have plt.title, and inside this we'll give the title as line plot. Similarly, we can also add x label and y label by using these two methods. And as you guys see, we have added these two labels over here. So let me add the title x label and y label plt. So I'll copy this entire code over here and then I'll paste it over here. Now after this, I'd have to add the title. So for that, I'll use plt.title, and I'll just give the title as first line plot. Then I'll have x label. So here I'll have plt.x label, and here I'll give the x label as x-axis. Then I would have the y label, so plt.y label, and inside this I'll give the y label as y-axis. Let's run this and wait for the results. So as you guys see, initially this was just a bland plot without the title and the x and y-axis labels. Now with the help of these three methods, we have added the title, the x-axis label, and the y-axis label. Now we can also go ahead and change some more attributes with respect to this line plots. So we have color, line style, and line width. So initially, as you see over here, the color of this line by default is blue. But if I don't want the blue color and if I want some other color, then I can just use this color attribute and assign it a new color. Since I'm giving it a value of G, which basically means green color, and as you guys see, this is a green color. Similarly, we have this next attribute called as line style. So initially we have a solid line, but instead of a solid line, if I want a dotted line, then I can go ahead and use a colon over here. And as you guys see, we have a dotted line right now. And by default also the line width is 1. So we can go ahead and increase or decrease the line width. So here we are setting the line width to be equal to 2. And this is the final result which we get. So let's go ahead and add some color, line plot, and line width. I have the same code over here. Now what I'd have to do is add in some color. So I'll have this attribute called as color, and I'm setting, let's say I'll give it orange color to this. Now I would have to change the line style. So I would want a dotted line instead of this solid line. So I'll give in a colon over here, and I'll also change the line width. So I'll give the line width as 3. So as you guys see, initially this was the line which we had, but now I have changed it to this. So from blue, we have converted it to orange. From a solid line, we have converted it to a dotted line. And also you see that this is a thin line, and we have increased the width of this line by 2 points. Now, we have only created one line in one plot, but we can also have two lines in the same plot. So for this purpose, I'll have two y variables. So x variable will be the same, which will be the number starting from 1 going on till 10. But I'll have two y variables, y1 and y2. y1 is 2 times of x, y2 is 3 times of x. So now that we have y1 and y2 ready, I'll have to make two plots because I'd want two line plots in the same graph. So first I'll have plt.plot, and this line will be between x and y1. So this first line which you are making, it will be between x and y1. And for this particular line, I'm setting the color to be equal to green, the line style to be equal to, so this will be a dotted line. Then we'll set the line width to be equal to 2. Then we'll have our next line, which will be between x and y2, and the color of this line will be red, and this will be a dashed line, and we are setting the line width to be equal to 3. Then again we have the title, x label and y label, and we also have this new method called as grid. So in the earlier plot, as you guys see, we don't have any grid over here, but when we set plt.grid to be equal to true, we'll have a grid as well. And this is the resultant line which we get. So here we have the green line over here, which is this dash line. Then we also have this next line over here, which is between x and y2, and this is the line. And since I've also set the grid to be equal to true, we also have a grid over here in this particular graph. So I'll go back. We already have x. Now let me just print out x for you guys over here. These are all of the numbers which are present in x. Now y1, I'll set it as 2 times of x, and then I'll have y2, which will be equal to 3 times of x. So I have y1 and y2 ready. Now after this, I would have to make a plot between x and y1. So I'll have plt.plot, and onto the x-axis I'll obviously have x, then onto the y-axis I'll have y1, and the color for the first line I'll have green, and let's say the line width, I'll set this to be equal to 2. Then I'll have the next line which will be between x and y2. So here I'll just write down x comma y2, and for this line I'll set the color to be equal to red, and I'll change the line width over here again. So I'll set the line width to be equal to 5, and I would just have to print it out. So it'll be plt.show, and I would also want a grid over here. So before this I'll set plt.grid, and I will set this to be equal to true. Let's hit run, and as you guys see, I have two lines in the same plot. Now in the earlier example, we had two lines in the same plot, but if we actually want two subplots itself, that is, as you guys see over here, this is one subplot, this is one subplot, and this line is present in the first subplot, this line is present in the second subplot. So this is also something which we can create. So first we have x, y1 and y2. So these would be the same variables. Once we have our variables ready, we would have to use the subplot method. So we'll have plt.subplot, and inside this I am passing in 1, 2, 1. So here 1, 2 basically means that I would have two plots over here, and those two plots would be present in this way. So I'll have one row, two columns. As you guys see, I have one row and two columns. So this is column number 1, column number 2, which are present in the same row. Then I will give in the index of this subplot. So this is index number 1. And for this first index, this will be the plot which we'll be creating. So for the first index, the plot will be between x and y1, color will be green, line style will be dotted, and line width will be 2. And as you guys see, at index number 1, we have this green colored line between x and y1. Then we'll have plt.subplot, which is our next subplot, and the first two parameters will be the same. The third parameter here will set the index value, which is 2. So this is what we'll be getting over here. And the second index will have the line plot between x and y2, and the color as you see is red, line style is dotted, and line width is equal to 2. Then we'll just go ahead and print it out. So we already have x, y1 and y2 ready with us. Now after this we would have to start off by creating a subplot. So here I'll have plt.subplot, and I'd have to give in the dimensions over here. So I'll have 1, 2, 1. So I'm creating my first subplot over here, plt.plot, and this plot will be between x and y1, and I'll set the color to be equal to yellow. Then after this I'll go ahead and create the second subplot, and the first two parameters will be 1 and 2 because I'd want these two plots along the columns, and I'll set the index to be equal to 2. Then I'll have plt.plot, and the next plot will be between x and y2, and over here I am setting the color to be equal to orange. Then I can just go ahead and show you guys the result. So as you see, I have two subplots over here. The first subplot is between x and y1, and the color of this line is yellow. The next subplot is between x and y2, and the color of this line is orange. Now if I want the subplots along the row and not along the column, that is also I can set. So all I have to do is make this change over here. I'll set this to be equal to 2, 1, and similarly over here I'll make this to be 2, 1, which means that I will have the plots along the rows. I'll have 2 rows and only 1 column. When I hit run, as you guys see, I have 2 rows and only 1 column. This is the first subplot, this is the second subplot. So that was a line plot which helped us to understand the relationship between two numerical entities. So whatever we mapped onto the x-axis was a numerical entity, and whatever we mapped onto the y-axis was also a numerical entity. Now we'll go ahead and work with something known as a bar plot, which would help us to understand the distribution of a categorical column. So for this, we are creating a dictionary called as student, and it comprises of 3 key value pairs. We have Bob 87, Matt 56, and Sam 27. Now we'll go ahead and extract the names and values individually. So the names of these students are basically the keys. So I'll have student.keys, which will give me all of these keys, and I'll go ahead and convert these keys into a list. So I'll pass this into this list method, and I'll store the result in this names object. Similarly, I'll extract all of the values, I'll convert all of the values into a list, or I'll store all of the values into a list, and I'll store that list in this object called as values. So I've got names, I've got values, and to create a bar plot, all I have to do is use plt.bar, and this takes in 2 parameters. The first parameter will have the categorical values, the second parameter will have the numerical values. Since the first parameter comprises of the categorical values, I'll pass in names over here, and the second parameter will be the values. And as you guys see over here on the x-axis, I have the names which are Bob, Matt, and Sam, and on the y-axis, I have the corresponding values. So we see that Bob has scored the highest marks, followed by Matt, followed by Sam. Now, since we are creating a bar plot, I'll just add this comment bar plot over here, and I'd have to create a dictionary so that we get the data for this bar plot. So I'll name this dictionary as student, and we can create a dictionary with these curly braces over here. So I'll have the first student, who is Bob. Let's say Bob has scored 45 marks. Then we'll have the second student, Sam, and Sam has scored, let's say, 97 marks. Then we'll have Matt, and let's say Matt has scored only 23 marks. So we've got 3 key value pairs. Now that this is done, I'd have to extract the keys. So I'll type in student.keys, and I will convert this into a list. So I'll cut this, I'll put this inside the list, and I will store this in a new object called as names. Now that I have names of all of the students, I'll go ahead and also extract marks of all of the students. So I'll store that in this object called as values. I'll have to convert the result into a list, and inside this I would basically have to extract all of the values. So it'll be student.values. I have names and values ready, and to create the bar plot I would just have to use plt.bar. The first parameter will be names and the second parameter will be values. Then I can just go ahead and show out the result. So we have Bob, Sam and Matt mapped on the x-axis and their corresponding values, and we see that Sam has the highest marks and Matt has the lowest marks. And now the plot which we had created earlier was very bland, and we can go ahead and add the title, x label and y label to it, and also assign a grid. So we'll be using the same methods. To add the title, we'll have plt.title, and to add the x label and the y label, we'll be using plt.xlabel and plt.ylabel, and we'll also set the grid to be equal to true. I'll copy these two set of commands over here, and I would have to set the title. So here I'll have plt.title, and I'll set the title to be equal to marks of students. Then I'll have something on the x-axis, plt.xlabel, and I'll just have names and the x-axis. Then I'll have something on the y-axis. Here I'll just write down plt.ylabel, and on the y-axis I'll just write down marks, and I would also have to set the grid to be equal to true. So it'll be plt.grid, and here I'll set the value to be equal to true. And as you guys see, I have names on the x-axis, marks on the y-axis, and I've also set the grid to be true. Now after this, we can also create a horizontal plot. So the plot which we had created earlier was a vertical plot. So here we are basically doing two things. So if we have to create a bar plot, we have to use bar h instead of using just bar, and we are adding a color as well. So by default we had the blue color, and if I want to change the color from blue to green, I'll use this color attribute and I'll map the green color to this. Rest everything will be the same. Let me add a new comment over here, which will be horizontal bar plot. Now that I have added this comment, let me go ahead and copy everything. I'll paste it over here, and instead of just having bar, I'll have bar h, and I'll set the color to be red, and we have this bar plot over here. So it's just that we have to interchange the labels. So on the x-axis now we have the marks, so let me keep this as marks, and on the y-axis we'll have names. Let me change this to names, and as you guys see, we have successfully created this horizontal bar plot. Now that we are done with the bar plot, we will head on to the next geometry, which will be a scatter plot. A scatter plot again is used to understand the distribution between two numerical entities, and these entities are represented in the form of data points. So we'll be creating two lists over here. The first list will be storing in X, which basically comprises of the elements starting from 10 going on till 90. Then we'll have the next list A, which comprises of some random elements. And here you'd have to keep in mind that both of the lists have same number of elements, else there'll be an error. And to create a scatter plot, we'll just use plt.scatter. We'll pass this over here, we'll pass this over here as a second parameter, and then we'll just show off the result. Let me go ahead and add a comment over here. So this will be a scatter plot. Now to create this scatter plot, I'd have to create the data. So I'd have to store something onto the x-axis. So in x, I'll just have 1, 2, 3, 4, 5, 6, 7, 8 and 9. and then I'll have y, and then y, I'll just have 9 random numbers over here. So let me just store some 9 random numbers, which is done. Now to create this scatter plot, I'll have plt.scatter and I'll just pass in x comma y, and I would have to show out the result, plt.show. And as you guys see, I have created this scatter plot. Let's start off with this particular point over here. This particular point indicates these two. So I have x, y, which is basically 1 and 5. So this intersection between 1 and 5 is where we'll be getting this point. So I have x, I have y, and this is the point I have. Then I have 2 comma 2. So the intersection of 2 comma 2, I'll get this particular point. Then we have this point over here, which is the intersection between 9 and 7. So as you guys see, I have 9 and 7 over here. Now we can also go ahead and add some aesthetics or change the aesthetics of the existing points. So we had same x and a. These are the same list which we have. It's just that we are adding new attributes over here. The first attribute is marker. Initially, we just had solid circles. So instead of having solid circles, if I wanted a star, then with the help of this marker attribute, I'll add star over here. Similarly, to change the color, I'll just have C and I'll assign green to this attribute C. And also I can change the size of this, and to change the size of this, I'll be using S. Let me copy this entire thing. I'll be pasting it over here. So these two will be the same. I'll add this new attribute called as marker, and I'll set the marker to be equal to star, and I'll change the color. Color will be, let's say, I'll have orange again, and I'll have size to be equal to 200. Let me print it out. And as you guys see, this is the result. Just to show you guys what happens if we increase the size. Instead of 200, if I keep it to be 500, you guys see that the size has increased again. Now instead of 500, what happens if I keep it to be 50? You would see that the size of the stars has decreased. Now, as we did with the line plot where we had two lines in the same graph, we can perform a similar sort of thing over here where we'll have two different sets of points in the same plot. So for this, we would need a new list. We already have X and A. Then we'll create a new list called as B. Again, we'd have to keep in mind that the elements which are present in this list, or the number of elements which are present in this list, should be equal to the number of elements which are present in A as well as X. Then we'll go ahead and create our first scatter plot by using plt.scatter, and the first scatter plot will be between X and A. And the first scatter plot here, these dots will be represented with stars. Then we'll go ahead and create the second scatter plot, which will be between X and B, and these will be represented with circles. And also we have different colors for both of these scatter plots, and also the size of the different data points will be different. I'll copy this entire thing over here and I'll paste it down. I'll change this to be equal to y1, then I'll have a y2 as well, and then y2 I would need some bunch of elements over here, random 9 elements. So let me just have some random 9 elements. Let me just check how many elements do we have. So I have 1, 2, 3, 4, 5, 6, 7, 8 and 9. So these 3 lists are ready. After this, I'd have to go ahead and create the first scatter plot, which will be between X and Y1. Then I'll go ahead and create the second scatter plot, which will be between X and Y2. And I'm not adding the marker because we have already added the marker for the first one. I'll just change the color for this. So the color for second one, let's just keep it to be blue, so I don't have to add the color as well. And I'll change the size of this. So for this, I'll set the size to be equal to 500. So as you guys see, I have two sets of points over here. The first set of point is being denoted by the small stars. The second set of points is being determined by these solid circles. Now, instead of having those set of points on a same plot, we can go ahead and create two subplots as well. So we'll be using the subplot method as we had used during the case of line plots. So here we have these three lists, then I'll have plt.subplot, then we'll have the same three parameters, and since I want these plots to be present column wise and not row wise, I'll have 1, 2, which means that I'll have one row, two columns, and then I'll give the index. So at index number 1, we'll have this scatter plot which will be between x and a. So this is the scatter plot between x and a. Then I'll go ahead and create the next subplot, and the next subplot will be between x and b. I'll copy this entire thing. I'll paste it over here. It's just that I'd have to create a subplot now. So I'll have plt.subplot, and I want these plots column wise. So I'll have 1, 2, 1, and the first subplot will be this. Then I'll go ahead and create the second subplot. So I'll have plt.subplot, and here I'll be writing 1, 2, 2. And this is our first subplot, and this is our second subplot. So that was all about the scatter plot. A categorical column, but when it comes to a histogram, we'll be using that to understand the distribution of a continuous numerical column. And we'll be creating this continuous numerical column or continuous numerical data with just a list over here. So this is a very basic example. I'm just creating a random list which comprises of all of these numbers, and I'm storing it in this object called as data. And to create a histogram, all I have to do is use this hist method. So inside plt.hist, I'll pass in this list, and when I show out, this is the result which I get. So here, let's actually have a look at this particular bin. So in a histogram, these are known as bins. So here, for this bin, for the value 3, we have this value 4, or for the value 3 on the x-axis, we have this value 4 on the y-axis, which would mean that this number 3 is occurring 4 times. Similarly, if I look at this 1 over here, so for this 1 on the x-axis, we also have the value 1 on y, which would mean that 1 is occurring only once. Similarly, we have 4. So this number 4 is occurring 2 times. Then we have 8, which is occurring 3 times. So let's go ahead and create a histogram in Jupyter Notebook. I'll just add a comment over here. Histogram. And let me go ahead and create a list. So I'll store this list in L1, and I'll have some random numbers over here. So I have created my list. Now that this is ready, I can just go ahead and build out the histogram by using this method called as plt.hist, and inside this I'll be passing in L1. Then since I just have to show this out, I'll just have plt.show, and this is the result. So as you guys see, this number 3 is occurring 4 times. Then we have this number 6, which is occurring 3 times. And the rest of the numbers are occurring only once. Now we can also go ahead and change the number of bins which are present or the color of the histogram as well. So to change the color, we'll just use this over here. So for the color attribute, we are mapping in G, which will give us this green color. And initially we had 1, 2, 3, 4, 5, 6, 7 bins over here. But instead of 7 bins, let's say if I want to reduce the number of bins, I'll just use this attribute and set the number of bins to be equal to 4, and this is the result which I get. I'll copy this entire thing, I'll paste it over here. Now that I have created this histogram, I would want to change the color of this. So I'll set the color to be equal to green. And instead of, so how many bars do I have? 1, 2, 3, 4, 5, 6, 7, 8, and 9. So instead of having 9 bars, let's say I would want only 3 bars over here or 3 bins over here. I'll set the bins value to be equal to 3. And as you guys see, I have only 3 bins. Now let me set it to be 5. And I have 1, 2, 3, 4 and 5 bins. This was all about histogram. Now, the earlier histogram which we had created was with respect to a single list. But if you want to create a histogram on top of a data frame, then let's see how can we do it. So here we'll be building this histogram on top of the iris dataset. So if we have to load any data frame, we'll have to use read_csv since this is a CSV file. So inside read_csv, I am passing in the name of the file and I'll store it in this object called as iris. And when I use iris.head, this will give me the first 5 rows which are present in this data frame. Now after that, to create the histogram, we'll just use plt.hist, and inside this, so here we were passing in the list of numbers, but here instead of passing in the list of numbers, I'll pass in the column. So we have this sepal length column which is present in the iris data frame. So I'll just pass in the sepal length column and I'll set the number of bins, and I'll also set the color to be equal to something. And when I show it out, this will be the result which I'll be getting. So here I'd have to load the iris data frame first. So in the iris object, I'll just have pd.read_csv, and inside this, I'll give in the name of the file which will be equal to iris.csv. I'll click on run. So I'd have to import the pandas data frame as well to use read_csv methods. So I'll have import pandas as pd. And we have, let's just wait till this is loaded, both the library and also the data frame. Now in the while it is loaded, I'll go ahead and write in the head method as well. Now if I click on run, we'll have a glance at the first 5 records which are present in this data frame. And as we see, we have sepal length, sepal width, petal width, and the species column. And now I'd want to create a histogram for, let's see, this petal length column over here. Then I'll just have to type in plt.hist, and inside this I'd have to pass in this petal length column. So here, so I'd given the name of the data frame first, and using this parenthesis, I'll give in the name of the column. So the name of the column, let me keep this to be small, it'll be petal length, and I'll set the number of bins to be equal to, let's say 50. And after that, I'll set the color of the bins to be equal to green again. And we can just go ahead and show out the result. So this should be color and not C. I'll keep it as COLOR. Alright, so as you see, we have successfully created this histogram for this petal length column. Now we'll head on to the next geometry, which is a box plot. So this box plot basically gives us a 5 number summary. So here in this result, what you see, this is the minimum value, this is the 25% value, this is the 50% value, this is the 75% value, and this is the maximum value. So we'll be understanding more about this as we progress through the session. So first, what we'll do is we'll just go ahead and create 3 lists. In the first list, we just have numbers from 1 to 9. In the second and the third list, we have randomly given some numbers over here. And then we'll create a list out of all of these 3 lists. So inside this list method, I am passing in 1, 2, and 3 as a list, and I'll store the resultant list in this object called as data. Then if I have to create a box plot, I'll just use plt.boxplot, and inside this I'm passing in this data object which I just created, and when I show it out, this is the result which I get. Now when I compare these 3 boxes, let's actually understand the inferences over here. So for this plot, or this box basically refers to this particular list. This box tells us that the median value of the numbers which are present in this list is 5. The maximum value is 9. The minimum value is 1. Similarly, if we look at this particular box, so this box refers to this particular list. And this box tells us that the median value will be 3, the maximum value will be 5, and the minimum value will be 1. Then if we have a look at this particular box, this would tell us that the median value will be 7 for this list, the minimum value will be 4, the maximum value will be 9. So it's time to create a box plot. I'll add this comment over here, box plot. And after this, I'd have to create 3 lists. So I'll have L1, and inside L1, I'll just have all the numbers starting from 1 going on till 9. Then I'll have L2. Inside L2, I'll just randomly give in 9 numbers. And again, I'll have L3, and also in L3, I'll just randomly give in some numbers over here. Now, once we have L1, L2, and L3, I'd have to create a list of lists. So inside this, I'll just be passing in L1, L2, and L3, and I will store this in a new object called as data. So now that we have created data, I can just go ahead and build out the box plot. So I'll have plt.boxplot, and inside this, I'll just pass in data. Then I can just show it out to you guys. So we have these 3 box plots over here. So the first box plot represents this particular list. We see that the median value is 5, minimum value is 1, and the maximum value is 9. Then we have this second list over here. So for this, the median value is 5, the minimum value is also 1, and the maximum value is 8. So, and for this particular list, it seems that the median value and the 75% value is same. So for this, the median value is 8, the minimum value is 5, and the maximum value is 9. So one another geometry which is analogous to the box plot is the violin plot. So the only difference is to create a violin plot, we'll be using violin plot method instead of box plot method. And this is the difference between how these boxes and violins look. And we can, so normally if we don't set the show medians to be equal to true, we'll not have these lines or these indicators over here. So we'd also have to set this to be equal to true. So now here, I'll just copy this entire thing. I'll paste it over here. And instead of having plt.boxplot, I'll just have plt.violinplot, and I'm printing out the same data. And as you guys see, I have created this violin plot. And now if I want the median, so I'll have show medians, and I'll set this show medians to be equal to true. And as you guys see, I have added the medians as well. And after the violin plot, we'll have the pie chart. And pie chart again helps us to understand the frequency or percentage of different categorical values. So here we have 2 lists. The first list comprises of all of the names of different fruits. So we've got apple, orange, mango, and guava. Then in the second list, we've got the quantity of these fruits. So we've got 67 apples, 34 oranges, 100 mangoes, and 29 guavas. And if I want to represent this relationship of the quantity of these fruits in a pie chart, this is how I can do it. So I'll be using plt.pie. And here first I'll be passing in the numerical entity. So the numerical entity is this quantity, and I'll be passing that over here. Then I'll have the categorical entity over here, which is fruit. So I'm assigning fruit to labels. Then I can just go ahead and show out the results. And as we see in the result, we see that the maximum percentage is of mango and the minimum percentage is of guava. So I'll have to create 2 lists over here. I'll create the first list. I'll have fruit, and the first fruit will be apple. The second fruit will be mango. The third fruit will be orange, and the fourth fruit will be lychee. Now that we have created all of these fruits, I'll also assign the quantity. So let's say I have 53 apples. I've got 43 mangoes, I've got only 12 oranges, and I've got 97 lychees. So I've got these two ready. Now after this, I'd have to create the pie chart. So I'll have plt.pie. First, I'd have to give in the numerical object, which will be quantity. Then I'd have to give in the categorical object. So I'm mapping fruit onto the labels. Then I would just have to show out this pie chart. So plt.show. As you guys see, this is the resultant pie chart. So the maximum portion belongs to lychee and the minimum portion belongs to orange, because we have 97 lychees and we have only 12 oranges. Now we can also go ahead and change the colors of these different sectors and also add the actual percentage in these different sectors. To add the percentage, we'll be using auto PCT. So here, for this auto PCT attribute, I am using 0.1f. Now, what this basically means is the 0.1 basically means that I'll have the decimal values to one place. So if I have 0.1, this will mean I have decimal values to one place. If I'll keep it as 0.2, then I'll have decimal values to two places. And after this, I'm just adding this new attribute called as colors. And the coloring, it starts from the first label, which is apple over here. Orange, then I've got blue, which is for mango. Then I've got black, which is for guava. I'll copy this entire thing over here. I'll paste it over here. Now, to add the percentage, I'll be using auto PCT. And here I'll have to use %0.1f. Let me add %. And after this, I'll also have to set the color over here. So the colors, I'd have to give in a list of colors. So let's say for apple, I'd want to give in green. Then for mango, I'd want to give in yellow. Then for orange, I'd obviously want orange. And for lychee, I'd want pink. Now when I hit on run, let's see what would be the result. Let me change this to colors instead of color. So as you guys see, I have the percentage over here because I had used auto PCT attribute, and it seems that we have, out of all of the fruits, 47.3 of them are lychees, and this is the color indicated. Similarly, out of all of the fruits, only 5.9% of them are oranges. So we have created the pie chart. Then something which is very similar to pie chart is the donut chart. And to create this donut chart, we'll be using two pie charts over here. So the data is same. We have fruit and quantity. It's just that first we'll go ahead and create our first pie chart, which comprises of quantity and labels. And I am adding a new attribute inside this, which is the radius. So I am setting the radius of this to be equal to 2. Then I'll go ahead and create another pie chart. Here inside this, I'll just pass in. So first we'd have to pass in numerical entities. So I'll just have a list which comprises of only one element or one value, which is 1. And this entire value or this entire list comprises of only one color, which is white. And I'll set the radius to be exactly half of the original pie. So I'm setting the radius to be equal to 1. And as you guys see, this is the outer pie chart. This is the inner pie chart. So the outer pie chart has a radius of 2. The inner pie chart has a radius of 1. And since I've given a color of white, this is what I have over here. So you can give in any random number over here. That doesn't really matter. So you can give 1, 10, 5. It is all the same. It's just that keep the color as W, because since a donut, it just basically looks like a donut, we'll have to give in the white color. I'll copy this entire thing. I'll paste it over here. I'll set the radius for this to be equal to, let's say, 4. Then I'll have a new pie chart over here. I'll just give in a random value. Let's say I'll give in 5 over here. And after this, I'd have to set in a color. And since there is only one value, I'll just give in white color over here. And after this, the only thing which I have to set is radius, and I'll set the radius for this to be equal to 2. Let's hit on run. And this is the donut chart which we get. So as you guys see, the radius for the outer pie chart is 4, the radius for the inner pie chart is 2. Let me reduce this. Let me keep this to be 2 actually, and let me keep this as 1. And this is the resultant donut chart. So Seaborn is another visualization library which is built on top of Matplotlib. So if you want to work with Seaborn, then we'd have to import Matplotlib as well. So to import Seaborn, we'd have to type in import Seaborn as SNS. And since this is built on top of Matplotlib, we'd also have to import Matplotlib. So we'll have from Matplotlib import pyplot as PLT. And inside Seaborn, we have this method called as load dataset, and we have some built-in datasets inside the Seaborn library. And one such built-in dataset is the fMRI dataset. And I'm storing this in this new object called as fMRI. And then I'll have a glance at this first 5 columns of this dataset. So we have these columns. We've got subject, time point, event, region, and signal. Now, out of all of these columns, I'd want to make a line plot between the time point column and the signal column. So to make a line plot with the help of this Seaborn library, since I've given the alias for this Seaborn library as SNS, I'll type in sns.lineplot, and onto the x-axis I am mapping the time point column, and onto the y-axis I am mapping the signal column. And then I'll have a new attribute called as data. So basically I am building this line plot on top of this fMRI dataset, that I just go ahead and show out this line plot. So let's understand this properly. So if you look at this line plot closely, you would see that till the time point of 5 seconds. So let's say if this time point is in seconds, so till the time point of 5 seconds, the signal value is increasing. But from time point of 5 seconds to 10 seconds, you have the signal value to be increasing. And after 10 seconds, this sort of stabilizes and only increases to, so here if the value is minus 0.05, so from minus 0.05, it goes up to close to 0. So now that we are done with Matplotlib, let me go ahead and create a new notebook over here. And I'll name this new notebook to be equal to Seaborn. Let me rename it. I'll delete this. I'll name this as Seaborn Demo. And we'd have to load the required libraries. The first library is obviously Seaborn. So I'll have import Seaborn as SNS. Then I'd also need pyplot. So I'll have from matplotlib import pyplot as PLT. Let's just wait for these two libraries to load. And once we have Seaborn with us, we'll be working with the fMRI dataset. So to load the fMRI dataset, we have the load dataset method, which is part of the SNS library. So I'll have sns.load dataset, and inside this, I'll be passing in the name of the dataset, which is fMRI. And I will store it in this object called as fMRI, and let me have a glance at the first 5 records of it. So I'll just type in fMRI.head, and these are the different columns which are present, and I'd want to make a line plot between the time point column and the signal column. And for this purpose, I'd have to map the time point column onto the x-axis and the signal column onto the y-axis. sns.line plot, and onto the x-axis I am mapping time point, and onto the y-axis I am mapping signal, and the data is obviously fMRI. Then I would just have to show out the result. So I'll have SNS. I'll actually have to give in plt.show over here. Let's hit run. So we have successfully created this line plot, and as we had already seen, so till 5 seconds there's an increase in the signal value, from 5 to 10 seconds there's a drop, and then it sort of stabilizes. Now we can also add a new attribute or new aesthetic called as hue. So here we had only one line, and this one line, arbitrarily the color of this was blue. But if I want the color of the lines to be actually determined by a column, what I can do is I can map a column onto the hue aesthetic. So we have the event column and we are mapping the event column onto the hue aesthetic. So now the color of the lines would be dependent on this event column. And since we have two events over here, we have the stem event and we have the queue event. This blue color line represents the stem event and this orange color line represents the queue event. And if we look at this blue color line over here, you would see that till time point of 5 seconds, the signal value, it goes up till maybe 20 and then it drops down to a minus 0.1. And similarly, if we look at this queue event, you see that the peak is not so high. So for the stem event, it was almost 0.2, and when it came to queue, it is only 0.05. But you'd also notice that the drop is not so steep. So for the drop of the stem event, it came from 0.2 and it will drop down to minus 0.10. But for this particular signal Q, the drop is very small. It dropped from 0.05 to only minus 0.05. And also if you see the increase of it, so once it dropped, the increase of Q event is much higher when compared to the increase of this stem event. So this is the same set of commands. It's just that I am adding a new attribute called as hue and I'm determining the color of the lines on the basis of this attribute, and I'll be mapping the event column on top of this. So as you guys see, I have this event column and this is the same column which I'm mapping onto this hue aesthetic. Event, we see that we don't have the event column. So what I'll do over here is I will cut this out. I'll paste it over here. I'll put in a comma, and since this is a column, I'd have to put this in double quotes. Now when I hit run, so seems like we have an error again over here. I have two commas. Let me go ahead and delete this comma. And we have successfully produced these two line plots over here. Now we can also go ahead and change the style of how these lines look. So now if I want these lines again, or the style of these lines again, to be dependent on a column, I can just go ahead and add a column onto the style aesthetic. So the color is also being determined by the event column, and also the style is being determined by the event column. So it will be the same command, and I'll be adding a new attribute to this. I'll have style, and to this I am mapping the event column, and you see that the queue event is being represented with this dotted line and the stem event is being represented with this solid line. So now that we have created that, we can also add markers on top of it. So all we have to do is set the markers to be equal to true. Here in this command, I'll have this new attribute called as markers, and when I set this to be equal to true, you will see that, so I have markers now. When it comes to the stem event, the markers are solid circles, and when it comes to the queue event, the markers are crosses. So that was all about line plot with the help of the Seaborn library. Now we'll go ahead and create a bar plot with the Seaborn library. So to create this bar plot, we'll be actually needing the Pokemon dataset. So we'd have to start off by loading the Pokemon dataset. So we'll have pd.read_csv and we'll store this pokemon.csv file in this Pokemon object. And once we store it in this object, we can go ahead and create a bar plot for this isLegendary column. So this isLegendary column is a categorical column, and that is why we are creating a bar plot. And in this isLegendary column, we have two categories, 0 and 1. So 0 indicates that the Pokemon is not legendary, and 1 indicates that the Pokemon is legendary. And onto the y-axis, I am mapping the speed column. And from this bar plot, it is very evident that legendary Pokemons, or the speed of the legendary Pokemons, is higher when compared to the speed of non-legendary Pokemons. So now I'd have to go ahead and load up the required data set. So to load the data set, I would need pandas. So I'll just type in import pandas as PD. Now, once I have this, I need to load the CSV file. So I'll type in pd.read_csv, and inside this, I'll give in the name of the CSV file, which will be pokemon.csv, and I will store it in this new object called as Pokemon. And once I've stored this, let me have a glance at this. So I'll just type in Pokemon.head, and I'll show you all of these columns. So these are the different columns which are present over here. So against bug, against dark, against dragon, all of these columns basically tell us how does a Pokemon perform against these types of Pokemons. Then let me scroll it to the last. So here we have this is legendary column, which would tell us if the Pokemon is legendary or not. Then we have this generation column, which would tell us to which generation does this Pokemon actually belong to. Then this column tells us what is the weight of this Pokemon in kg. Then this type 1 tells us what is the primary type of the Pokemon. Type 2 tells us what is the secondary type of the Pokemon. And then we've got other columns as well. So now for this bar plot, we'll be only working with this is legendary column and then the speed column. So I'll be using sns.bar plot, and onto the x-axis, I would have to map is legendary, and then onto the y-axis, I'll be mapping the speed column, and the data onto which I'd want to build this bar plot is the Pokemon data set. Then I can just go ahead and show this out. And when I hit on run, you would see that I have successfully created this bar plot. And again, it is very evident that the legendary Pokemons, the speed of the legendary Pokemons is higher when compared to the speed of non-legendary Pokemons. So now we'll create a bar plot between is legendary column and weight in kg column. So is legendary column is again mapped onto the x-axis. It's just that here for the y-axis we are mapping weight kg column. And this time it is very obvious that legendary Pokemons, their weight is much higher when compared to non-legendary Pokemons. I'll cut this out, I'll paste it over here. And instead of mapping speed, I have the weight kg column. And when I hit on run, you would see that the weight in kg of a legendary Pokemon is much higher when compared to the weight in kg of a non-legendary Pokemon. Now, we can also go ahead and determine the color of these bars on the basis of a column. And we already know to do that, we'll be using the hue aesthetic or the hue attribute. And I want the color to be determined by the generation column. So this time I'll be mapping the generation column onto the hue aesthetic. And as you guys see, we have 7 generations over here, starting from generation 1 going on till generation 1. And since we have 2 different legendary status, so 0 indicates that the Pokemon is not legendary, 1 indicates that the Pokemon is legendary. For these 2 categories, I'll have 7 bars each. So for those Pokemons which are not legendary, I'll have these bars, these 7 bars indicating to which generation does the Pokemon belong to. Similarly, for all of the Pokemons which are legendary, I'll have these bars indicating to which generation does the Pokemon again belong to. And again on the y-axis, since we have mapped speed, we have the speed values corresponding to whether the Pokemon is legendary or not legendary. So the same set of command, I would have to use the hue aesthetic, and onto this I'll be mapping the generation column. And as you guys see, so this denotes all of those Pokemons which are not legendary, this denotes all of those Pokemons which are legendary. And it is very clear that legendary Pokemons, they have much higher weight when compared to non-legendary Pokemons. And we have the distribution of Pokemons which belong to the different generations with respect to both legendary Pokemons and non-legendary Pokemons. Now going ahead, we can also change how the different palettes look for these bars. So we will use the palette attribute. So we've got these three different palettes over here. So again, the bar plot is between isLegendary column and weight column. And it's just that instead of using a column to map it onto the hue aesthetic, we are using a new aesthetic called as palette, and we can directly use different predefined palettes. So first we have the Blues D palette with a capital B. This is how it looks like. Then we have the Rocket palette, and this is the resultant. And then we have the VLAG palette. Let me delete this hue attribute over here. And instead of that, I'll have palette attribute, and the first palette which I'll be using is Blues D. And as you guys see, this is the Blues D palette. Similarly, if I want maybe a more of red color, then I'll be using the Rocket palette. Then if I want maybe a light shade of bluish gray, I'll be using VLAG, and this is what I'll be getting. Now, instead of maybe using a palette or maybe mapping a color onto the hue aesthetic, I can just go ahead and use the color attribute and assign one single color for all of the bars which are present. So I'm using the color attribute and I'm mapping the orange color to both these bars. I'll remove palette, and instead of palette, I'll have the color attribute, and I will set the color of these two bars to be equal to orange, and this is the result. So we are done with bar plot as well. Now we'll go ahead with the next type of plot, which is scatter plot, and we have already learned that a scatter plot is used to understand the relationship between two numerical entities. And over here we are building the scatter plot on top of the iris dataset. So we'll load this dataset up, then we'll be using sns.scatterplot, and onto the x-axis I am mapping the sepal length column, and onto the y-axis I am mapping the petal length column, and the data onto which I'm building this scatter plot is the iris dataset. And again, it's very clear that as the sepal length of the iris flower increases, the petal length of the iris flower also increases linearly. So here I'd have to load up the iris dataset first. So I'll have pd.read_csv. I'll give in the name of the file, which will be iris.csv. Now that I have loaded this, let me show you guys the first 5 rows of all of the columns, and this is the resultant. And to create the scatter plot, all I have to do is use plt.scatterplot, and since I want the scatter plot between sepal length and petal length, and I want sepal length to be onto the x-axis, so to x I'll be using sepal.length, and on the y-axis I would need petal length. So let me give in the name of the column over here, which will be petal length, and the data which I'm using is obviously iris. Then I can go ahead and show out the result. So let me just keep it as scatter over here. And again, this has to be equal to small d and not capital D. Let me hit on run over here, and this is the resultant value. Now, as you see over here, we can go ahead and add in color and also change the style of this. So initially we just had a simple plot between sepal length and petal length, but now I want these dots to be determined, or the color of these dots to be determined by the species column. So that is why I am mapping the species column onto the hue aesthetic. And after that, similarly, I am mapping the species column onto the style aesthetic as well. So here, as you see, we've got 3 different colors: blue, orange, and green. The blue color is being determined with the Setosa species. Then we've got this orange color, which is for the versicolor species. Then we've got this green color, which is for the Virginica species. Similarly, we've got 3 different styles over here. For Setosa, we have solid circles. For versicolor, we have crosses. And for Virginica, we have solid squares. The same command which I've copied, I've pasted it over here. I'll add 2 more attributes. The first attribute will be hue, and onto hue I'll be mapping the species column. Similarly, onto style as well, I'll be mapping species column, and when I hit on run, So I'll have it as hues. Now when I hit on run, seems like we have an error over here. Let me check it properly. And this over here has to be just hue. Now when I hit on run, this is the resultant scatter plot which I get. And now let's say instead of having the colors to be determined by a categorical column, if I actually want the color to be determined by a numerical column, I can also do that. So here, since petal length is mapped on the y-axis and I want the color to be with respect to the petal length, I'll go ahead and map the petal length onto the hue aesthetic. And as you guys see over here, as the value of petal length is increasing, the intensity of these points is also increasing. So here on this lower left side over here, we have all of this very light shaded circles, and at the top right you have this high intensity or high intensely colored circles over here. I'll copy this, I'll paste it over here. Now I'll want the hue or the color to be actually determined by petal length itself. Let me keep the L to be capital, and when I hit on run, you would see that as the petal length value increases, the intensity of the color also increases. Let me just go ahead and also add the style over here. So this time the style will be determined by the species column. And you would see that we have three different styles. For Setosa, this is Setosa, you have solid circles. For versicolor, you have crosses. And for Virginica, you have solid squares. So this was about a scatter plot. Now we'll go ahead and make a histogram or a distribution plot. So a distribution plot, you can consider this to be a combination of a frequency curve and a histogram. And we've already worked with histogram when it came to Matplotlib. We know that a histogram is used to understand the distribution of a continuous numerical value. So for this, we'll be using the diamonds data frame. So we'll load up this diamonds data frame, we'll store it in this diamonds object, and then we'll have a glance at it. After that, to create this distribution plot, we'll use dist plot, and inside this, if I want to understand the distribution of the price column, I'll just pass it over here. So I'll have diamonds of price, and as you guys see, this would show us the distribution plot. And as I've told you, the distribution plot is a combination of a histogram and the frequency curve over here. I'll just add this comment and I'll add distribution plot. Now over here, to create this distribution plot, I would need to load up the diamonds data set. So I'll have pd.read_csv, and inside this I'll be passing in the diamonds.csv file, and I will store it in this new object called as diamond. Now that I've loaded this data set, let me have a glance at the first 5 records of this. So diamond.head, and these are the different columns which are present. So I've got caret, which obviously tells us about the caret of the diamond. Then we've got the cut type of the diamond. We've got color, clarity, depth, table, price. So this is price of the diamond in US dollars. So the price would mostly range from around $300 to around $18,000. Then we've got X, Y, and Z. X over here denotes the length of the diamond in millimeters. Y denotes the width of the diamond in millimeters, and Z denotes the depth of the diamond in millimeters. So once this is clear, I'd have to make a distribution plot, and since distribution plot is used for continuous numerical values, I'd want to make a distribution plot for this particular column. So I'll have sns.dist plot, and inside this I'll be passing in diamond. I'll have square braces over here. Inside this I'd have to pass in the column which is price, and I would just show this out. I'll have plt.show, and you would see that I have created this distribution plot over here. Now in the distribution plot, let's say if I want only the frequency curve without the histogram, that also can be done. It's just that in the same command, I would have to set hist to be equal to false. And when I set hist to be equal to false, I'll only get the frequency curve. I'll copy it, I'll paste it over here, and I'll add a new attribute called as hist, and I'll set this to be equal to false. And when that is done, you would see the difference. So this was a distribution plot which had both histogram and the frequency curve. Now this is a distribution plot which comprises of only the frequency curve. Now similarly, we can go ahead and add a new color to this, and to add a new color, we'll just use this color attribute and add this. So this was the distribution plot which we had created, and to this, if I want to add color, I'll use this color attribute, I'll assign it red, and you would see that I have assigned it the red color. Now if I want a distribution plot without the frequency curve, which would mean I'd want only the histogram, then here I will set KDE equal to false. So in the distribution plot, either we can have both the histogram as well as the frequency curve, or we can just have the histogram, or we can just have the frequency curve. To just get the frequency curve, we'll set hist to be false. To just get the histogram, we'll set KDE to be equal to false. And we can also go ahead and vary the number of bins which are present. To vary the number of bins, I'll use this attribute called as bins, and over here I'm setting the number of bins to be equal to 10, and I'm just setting the color to be equal to green. I'll select this over here, I'll paste it, and I'll set KDE to be equal to false. And when I do this, you would see that I have only the histogram without the frequency curve. Now if I want to change the number of bins which are present, so since there are 150 records, I'll have 150 bins, but instead of having all of this, so let's say if I want only 50 odd bins over here, I'll set 50, and as you guys see, I have only 50 bins. Now let's say instead of 50, maybe if I want only 10 bins, so you will see that I have only 10 bins. Now let's say if I want only 5, that also something which can be done. I'll set the value to be equal to 5, and we have only 5 bins over here. And after this, let's say if I want to plot it on a different axis. So till now we've been creating this distribution plot where on the x-axis, or basically this was based on the x-axis, but instead of having it to be based on the x-axis, if I want to map it vertically, then I would just have to set vertical to be equal to true. I'll have the same command over here, and here I'll set vertical to be equal to true. I'll remove this KDE equal to false from this. I'll also remove this particular attribute from this. Now if I hit on run, you would see that I have mapped this distribution plot onto the y-axis. Next, we have a new geometry called as a joint plot. So this joint plot is a combination of a scatter plot and a histogram. So as you guys see over here, I have a scatter plot in the center, and I have a histogram at the top side and the right side. And I'll be creating this joint plot on top of this iris data frame. So once I've loaded this iris data frame, I want to create a joint plot between sepal length and petal length. So I just created a scatter plot. So for scatter plot, we have just used scatter plot method. For joint plot, it's just that we have to use this particular method. We are passing in the same columns. Now, when it came to scatter plot, we had only this particular part. But when it comes to joint plot, here what you see for sepal length, you would have the histogram of the sepal length column as well. Similarly, for petal length, you will have the histogram for petal length column as well. So this is an interesting point about joint plot. We already have loaded the iris data frame. Now I'll have to use sns.jointplot, and onto the x-axis I'll be mapping sepal.length, and onto the y-axis I'll have to map something. So onto the y-axis I'll be mapping petal.length, And that is pretty much it. I actually have to give in the data as well. So the data on which I'm making this is the iris data set. Then here I'll have plt.show, and when I hit on run, so seems like we have an error over here. So sepal length, so L has to be capital. Let me make it capital L. And you would see that I have successfully created this joint plot where I have the scatter plot in the center, and I have corresponding histogram for sepal length on the top, corresponding histogram for petal length on the right side. And over here, if I want to change the color, that is also something which can be done, and we've already seen this throughout. So all I have to do is use this color attribute, and I have to give in a color for this. And if I like the olive color, that is what I'll be going ahead and mapping it onto this attribute. I'll add this color attribute, and I'll have olive. And as you guys see, I have mapped the olive color for this joint plot. Now for this, if I want a regression line through the scatter plot and also through the histogram, I'd have to use this new attribute called as kind. And for this new attribute kind, I am assigning this value reg. So as you guys see, I have this regression line which is passing through the sepal length values and the petal length values, and also it is passing through both of these histograms. So here I'll have kind, and I'll have the value reg set for this kind attribute. Let's wait for the result, and you would see that I have added a regression line which goes through the histogram and also goes through the scatter plot. Once I have done this, let's go ahead to the next geometry, which is a box plot. And to create a box plot, we'll just be using this box plot method, and we'll be creating this box plot on top of the churn data frame. So we'd have to load this data frame first. So this data frame tells us about the different features of a telecom company, and on the basis of this features, we'd have to find out if the customer will churn out or will stick to the same company. So here we have the churn column and the tenure column. The churn column I'm mapping onto the x-axis, the tenure column I'm mapping onto the y-axis, and obviously I'm building this box plot on top of the churn data frame. One interesting attribute about a box plot is that box plot can be mostly used to understand how does a categorical value change along with a numerical value. So that is why here we have mapped this categorical column churn onto the x-axis and this numerical column tenure onto the y-axis. And we see that, so this what you see is the median value which we have already seen. So when it comes to people who do not churn out, it seems that those people who do not churn out, their median tenure or their tenure in general is longer than those people who actually churn out. So I would have to load this data frame first. I would have to store it in this churn object. So churn is equal to pd.read_csv, and inside this I'll have churn.csv, and then let me have a glance at the first 5 records of all of the columns, and these are all of the columns. And for all of these columns, I'd have to make a box plot between this tenure column which would go on the y-axis and this churn column which would go on the x-axis. SNS.boxplot, and onto the x-axis I'd have to map obviously the tenure column. Onto the y-axis I am mapping the churn column. Then I'd have to use the data which is churn, and I'd have to show it out. So I'll have plt.show. So I've actually made a mistake over here. So tenure will go onto the y-axis and churn will go onto the x-axis. Now we get this box plot, and we've already seen the inference. It seems that those people who do not churn out, their tenure seems to be longer than those people who actually churn out. And now this time we'll be creating a box plot between the internet service column and the monthly charges column. So we have the monthly charges column onto the y-axis and the internet service column onto the x-axis. And we've got these three different categories in this internet service column. So the internet service can either be DSL, fiber optic. So this no means that the people don't have or the people haven't subscribed to internet service. And it is very clear that those people whose internet service is fiber optic, they would have the maximum monthly charges. Similarly, those people who do not have internet service, their monthly charges is minimum. So when you compare this box to these two boxes, it is very evident that people who don't have internet service, their monthly charges are very, very low. I'll copy the same command over here, but on the y-axis, I'll have monthly charges, and on the x-axis, I'll have internet service, and this is the resultant box plot which we'll be getting. Now we'll go ahead and make another box plot between the contract column and the tenure column. Tenure column would go onto the y-axis, contract column would go onto the x-axis, and we can have three different types of contracts: month-to-month contract, 1 year contract, and a 2-year contract. And if we look at the tenure of it, so let's actually look at the median values of the tenures. So it seems that if the contract is of month to month, then the median tenure is the lowest. Similarly, if the contract is of 2 years, then the median tenure is the maximum. And we are setting a palette over here. So again, we can have different palettes. So the palette which I'm using is equal to set 1. Onto the y-axis, I'll be mapping the tenure column. Onto the x-axis, I'll have the contract column. Let me write in contract column over here. And the data will obviously be the churn data set. And what I'd have to do is I'd have to use a palette, and the palette which I am using is equal to set 1. And this is the resultant box plot. Now you see these boundary lines over here. If we want to change the thickness of these boundary lines, we can do that with the help of this line width attribute. So here I am setting the line width to be equal to 3. If you compare this particular box plot with the earlier box plot, it is very clear that the thickness has increased. The same code, I'll actually have tenure and contract over here. Onto the x-axis, I'll be needing contract. And I will use this line width, and I'll set this to be equal to 3. And you would see that the line width has increased substantially. And after this, let's say if I want to change the order of how these boxes are present. So here, initially the boxes were present in the order of month to month, 1 year, 2 year. But instead of this order, let's say if I want 2 year first, followed by month to month, then after that, if I want 1 year, then I can use this attribute called as order, and inside this I'll pass in the list which will comprise of the order in which I would want these boxes to be present. So here I'll remove the line width, and instead of line width, I'll use this attribute called as order, and first I'll have 2 year. After that, I'll have month to month. Then finally, I'll have the last box, which will be 1 year. And you would see that I have changed the sequence. Now, if you want to add colors on the basis of a column, which we've been doing throughout, that can be done with the help of this hue attribute. And I want the color of all of these boxes to be determined by this payment method column. So here I am mapping this payment method column onto this hue aesthetic. And as you guys see, I have these 4 different payment methods. I have electronic check, mail check, bank transfer, and credit card. So electronic check. So this particular box, or wherever all of these boxes where the color of the box is purple or dark blue, that denotes electronic check. Then we have the box where the color is orange, that would denote mail check. And if the color of the box is green, that would denote bank transfer. And if the color of the box is red, that would denote credit card. So here, I'll add this attribute called as hue. And I want the hue to be determined with the help of this payment method column. And you would see that I have 4 of these over here. So I have 4 boxes with respect to these 3 different categories.
As you might already know it, right, machine learning is one of the most popular applications there is of the entire world of data science. When that becomes the case, it is vital that you know everything there is to know about machine learning. So in this session, we are going to check out a lot about the same. First of all, we're going to check out why you require machine learning, and after you understand why you require machine learning, we're going to take a look at the types of machine learning algorithms that are out there, what is the actual process of how machine learning works. Once you understand this process, we're going to check out the usage of Python for machine learning, and we're going to check out the top 5 machine learning algorithms that you must know as a person who's proficient, who's an expert in the field of machine learning and data science, right? And of course, at the end of it, we're not going to be just checking out theory of these concepts as always. We're going to make sure we balance this theory with enough amount of practicals. I'm going to have a code walkthrough session where we're going to check out every single individual element practically, as I've explained to you theoretically, and we can proceed with the best way that you guys can understand these concepts, right guys? Now, first of all, as I just mentioned, right, machine learning is one of these concepts which form to be the most important aspect of data science that there is. When you think about how you can get to artificial intelligence, right, artificial intelligence and data science go hand in hand because AI is the biggest application of data science there is. But to get from data science to AI, you require machine learning in the middle. That is why it is the most important stepping stone that adds so much value, right? So what are we doing with machine learning? With machine learning, the goal is very simple. So we make sure that, we get the machines to understand data on its own, to learn on its own, and eventually give us a solution without us having to intervene during this entire process. Now, it is very, very easy to say that, hey, machines are very intelligent, they understand a lot of things. But as I've been mentioning in the previous modules, your machine can only understand zeros and ones at its most functional level. Everything apart from that is just added for our convenience of how we can communicate with the machine better, right? So if you show a picture of a cat or a dog to your machine, there is a very good chance it will not understand anything unless it is trained or unless it is told that, hey, what you're seeing is a picture of a cat, what you're seeing is a picture of a dog, right? So what is the goal if it is naive at this level? Well, the goal is to make sure that our task in many cases can be simplified to its most easiest way possible by getting the machine to do work for us, right? So making the machine think like us, making the machine think like human beings is the primary goal here. Now again, if you've been wondering about where the machine learning data comes from, where it learns, again, there are numerous data sets to singleton problems, customized problems. There's so many ways where you can collect data, as I've been already telling you since module number 1. You can collect data from multiple places and then have work on it, right? So here in the case of machine learning as well, the same thing applies. Data comes from a variety of places, it gets stored, and eventually then a solution is derived based upon the data at hand, and after it goes through an algorithm and all of that. So the first question you really should ask yourself is, why is machine learning required in the first place? Why is it the biggest thing in today's world, right? First of all, you have to understand that there's hundreds and hundreds of reasons. We can have a discussion hours together just talking about the advantages of machine learning. But to give you a clear and a concise picture of what you can expect, well, here are some of the important pointers. First of all, the most important thing is that it will help reduce production cost to a very, very big extent, right? Now, it is not only just production cost, it is everything right from production till delivery of a product to the customer, right? Machine learning can sit in all of these different phases of product manufacturing and delivery in a way where you thought it was not possible before, right? From material procurement, right from actually processing it, quality control to delivery, supply supply chain analysis. You can do everything when it comes to production here. The next reason why it became really popular is that you already know we generate a huge amount of data every day, right? With machine learning, the advantage here is that you can process all of these very easily, in a simple fashion, where you do not have to break your head to go through a lot of data, right? That's the advantage. The next thing is individuals, startups, multinational corporation, whoever you are at the end of the day, you can derive some key insights about your business in a very clear and a concise way if you go on to make use of machine learning. It simplifies your tasks not only in a way where it tells you that you've gone wrong here based on the past data, but it can also use past data and present data and give you a forecast into the future. It can tell you, hey, down the line, your company can sell these many products. It is forecasted that you can sell all of these products. So imagine, probably a couple of years before, maybe 20-30 years before, if someone told you can use your computer to predict the future, they would still treat it as a joke, right? Now it's not so much of a joke. Data is the new oil. It is packed. It's a treasure. You can use it to derive all of these insights, and it's a beautiful thing to do it as well. Again, we're going to see all of these practically in this module. The fourth point is what I just mentioned, right? You can find out hidden trends that are present in data. Now, let's say data, think of data as maybe a bowl of rice, right? If you just look at a bowl of rice, you really cannot make any sense out of it. But let's say that there is little snippets of gold hidden inside this bowl of rice. So if you put your hand, dump in, if you churn through the rice, and if you put in your hand, do the hard work, and then you can pick up these tiny figments of gold which was not visible to the naked eye, right? This is exactly how data is. It's like playing treasure hunt with the data. You will know that there is something at the end of the tunnel, but to get to that you have to work. That work takes extreme amount of processing, and that is why we require machine learning. So I hope I was clear with why you guys should definitely look at learning machine learning, right? Now, the next thing after you understand why machine learning is that you have to look at the different types of machine learning, because if you do not understand the fundamental concept of how machine learning is divided, it becomes very difficult later down the line. So guys, there are three different types of machine learning of, how a machine itself learns in this domain. It is supervised learning, it is unsupervised learning, and it is reinforcement learning. Now, these three learning methodologies, right, they work in very different ways. Each has its own application, each has further subdivisions and a lot of things, but these are extremely important. These are foundational for everything that we are going to do, go ahead with this in this module. So make sure you're putting an ample amount of concentration for these slides, guys. Right. The first one that we are going to check out is supervised learning. Now, think away from data science, think away from machine learning for a second here. When someone says supervised learning, or that you are learning with some supervision, what's the first thing that comes into your mind? Because for me, it's probably a child who is studying for an examination, and there's a parent who is supervising and making sure that, the child is not playing games but is actually studying. Supervision, right? Keeping a control. Now, in the case of machine learning, things work similarly to the analogy that I just mentioned to you. Here, however, it is not the machine itself governing. It is the data which is governing. It is the governing entity in a way where the machine itself knows what data it is seeing. It is not literally being supervised, but it understands the data as if it were supervised. That's the difference here, guys. So you have three images on your screen right now. Let me use those examples to explain supervised learning for you. You have the image of a flower, you have some dumbbells, and you have a car here. Now, you as a human being is probably taught from a very young age to see not one, not 100, but 1,000 pictures of flowers to say it's a flower, right? You will not see a flower and call it an aeroplane. You know that is wrong. You have been trained over the years again and again and again. You see a picture of a dumbbell, right? There's a good chance it can be slightly confusing because you might have never used a dumbbell, or if you have, it is very easy to spot it, right? Now car is definitely a popular thing that you've seen, you've known. You would have seen thousands of cars in your lifetime, hundreds of colors, hundreds of models, all of these. So as soon as you look at the picture that I've put in here, there's a good chance that you can say, hey, it's an orange color, it's this brand, it's a coupe, it has this brand sport wheels, it comes with this engine. You can actually go on to tell the model just by looking at that image. But if you show the image to a computer, no, it will not understand any of these, right? You have to be very clear about that. So to bridge this gap of us telling the machine what it is seeing, right, the advantage of supervised learning is we give the labels for the data. If the data is the image of a flower, we give a label. We tell, hey computer, here is the image of a flower. We specifically mention that it's a flower and then give the image to the machine learning algorithm. So at the end of the day, the machine learning algorithm already knows what it is seeing. So it uses that to learn and later predict other images which might be of the case. Now this is just one example of supervised learning that I'm giving to you. But having these labels below that says this is a car, this is a dumbbell, this is a flower, right? That is very important for supervised learning. Now, with unsupervised learning, you don't do this. I'm going to explain that in a second. But before that, here's another important concept that you definitely should know about when it comes to supervised learning. See, supervised learning is a very simple form of how we can have an input. How can we apply a function on the input to eventually transform and arrive at a solution, right? So if your input variable, as we call it, is considered as x, applying a function on it becomes f of x. If you assign this to another variable y is equal to f of x is what we get. This is the foundation of supervised learning. We are trying to map the output as a function of the input, right? So we have the input, you're doing some transformation on the input which eventually takes you to the output, right? So whenever there is a common discussion, y is equal to f of x, now you know what y is equal to f of x means. You have an input, you apply a transformation, you apply functions on it, you do a lot of things to the input to take it from its raw form to a processed form, and the processed form itself is considered as y, which is the output variable in this particular case, guys. So this is a very, very important thing about supervised learning that you should know about. But then, did you know that supervised learning is further branched into two things called as regression and classification? Now, first of all, machine learning is divided into three things: supervised learning, unsupervised learning, and reinforcement learning, right? Now, supervised learning branches into two, where it's called as regression on one side, classification on the other. Now, if you've been wondering about what regression means, again, regression is a concept which I have already discussed previously, where you take in data from the past and you try to predict what might happen in the future. Or let's say you take data from the past and you understand why we are at this point in time today, right? We're going to be discussing a regression use case practically as well, so make sure you stick around till the end of this module. So regression is a very simple concept. Again, we're going to discuss it with an example. But if you're looking at classification, right? Classification is a simple concept which you've already used. Regression is something which you might have used in a casual conversation, but classification is something which you know you have done. Let me give you an example. If I give you, a ripe apple versus an unripe apple, or let's say I give you 3 apples or 2 oranges, I mix it and I give it to you. I say, hey, based on the shape of the apple, based on the shape of the fruit, why don't you split it out and classify it differently? Well, an orange is a round fruit, right? So you just take it and you move it to another place. On the left, you keep an apple. The apple has a very unique shape, right? So you put it on the left. Now, if I said, hey, why don't you classify it now based on the type of fruit? Now, there might be a case where there's a defect in the apple and it is now round, right? There are certain chances that it is almost round, you can get confused. But if I say, classify it based on the fruit only, you will know no matter what size or shape the apple is, push it to the left. No matter what size or shape the orange is, push it to the right. That is a simple way of classification here. Now, let us take a look at supervised learning. Supervised learning is one of these methodologies which is a direct contrast to, unsupervised learning is one of these, types of learning which is a direct contrast to supervised learning. Here, the entire goal of the machine learning algorithm is not us telling what the data is, but it figuring it out on its own. So the entire usage of unsupervised learning is based upon how the machine learning algorithm itself can find some sort of hidden structure or pattern that is present in the data without us specifically telling it, right? Now, take a look at the same three images I have on your screen. Flowers, dumbbell and car, but this time I have not labeled it, right? That is done on purpose because here in unsupervised learning, you do not label the data. You just give it an input variable and let the machine learning algorithm figure out on its own. Now, there is a very, very good chance that now there's a question in your mind saying, okay, so if you're not helping the machine, is unsupervised learning a complex procedure compared to supervised learning? In many cases, the answer is yes, because here, it is not just cross-referencing what it has learned to what it already knows, but here it has to first of all learn in a very different way and then work on cross-referencing. So it definitely takes a good amount of computing time, computing power, and of course the way the machine learns, the way it uses algorithms to already know that it only has the input to get to the output and find a structure is very, very different compared to supervised learning. So I hope I was clear in that point, right? Now, if you're looking at grouping, another very important thing that you have to know in unsupervised learning is that there's two groupings just like how we had for supervised learning. But here, instead of regression and classification like how we had in supervised learning, in unsupervised learning, we have clustering and association. Now, clustering is a fantastic example which again you would have used in your real life anyway. If I give you 3 erasers, 2 pencils and 5 pens and say, can you group all of these things separately and keep it into 2 or 3 piles? Can you or can you not do it? You can do it in a very simple way because you know what a pen looks like, you know what an eraser looks like, you know what a pencil looks like, and you know how to club it and group it and keep it separately, right? Does the machine know this? No. But if you train it, can it understand this? Absolutely yes. That is the entire point of using unsupervised learning, right? So that is a simple example of clustering. Now let us take a look at a simple example of association. Again, association is something which you have used but you might not know you've used. Maybe you're on the Amazon's website, maybe you're buying your favorite thing, maybe you just bought a new mobile phone. Now as soon as you buy a new mobile phone, as soon as you add it to the cart, there's an option below which says people who have bought this mobile phone also bought this. It may be a screen guard, it may be a case, it may be an earphone, whatever accessory, right? So it is recommending something to you. It is saying, hey, people who bought this also bought this. So it is trying to map something. People who buy this phone have a good chance of buying the protective case for it, tempered glass for it, all of these things, right? That is association. Here's another example. Every time you finish watching a TV show on maybe Netflix or Amazon Prime, at the end of it, there is a good chance it recommends a very similar TV show for you. Now, if you watched a horror movie, the next recommendation is going to be a horror movie or a thriller or something like that. If you watched a comedy, a situational comedy, sitcom or anything like that, after you finish an episode or after you finish the TV show itself, the next one it's going to recommend to you is something similar, because here Amazon, Netflix and all, they're trying to understand what your preferences are, what you like watching, and eventually customizing their platform so your viewing experience is amazing, right? That is association. If you've been wondering, association is used not only in these 2-3 cases but almost everywhere that you can think of. Everywhere where there's customization, where there is a goal to make sure that customer retention is high, will use association, and even in fact a concept of clustering very popularly as well. So it becomes very, very vital that you understand that unsupervised learning is among the most popular algorithms or the types of learning there are in today's world. Right, now that we checked out supervised learning and unsupervised learning, let's get to the third type of machine learning. Here we're going to take a look at reinforcement learning. Now, reinforcement learning is a very, very fun algorithm because again, here's an analogy in real life to simplify what it means. Okay, so how many of you guys have either pet cats or pet dogs at home? It works better with dogs and less with cats because I personally am a owner of both, so I know that it just works amazingly well with dogs. Right, here's the example. Have you ever had your dog trained professionally? Right now, a simple training, it usually starts out with sit, stand, give me a handshake, all of those instructions to your dog, right? Now, your dog does this. Your dog is trained in a way where if it gives a handshake, it gets a tiny reward. It gets a biscuit. It gets a treat, right? So your intention here is to get the dog to give you a handshake. The dog's intention is to train itself in a way where if it gives a handshake, it gets a treat. It gets a nice thing to eat, right? Your happiness lies in getting the handshake. The dog's happiness lies in getting the biscuit. It's two different things. But at the end of the day, your purpose of getting a handshake is being solved, right? So that's the thing. With cats, I've seen that if you ask a cat for a handshake, they just meow and run away and they don't care absolutely. Or I don't know, just is it my cats or something like that? But that's the most common thing that I have seen, right? So there's a reward which is waiting at the end of learning. Now, if the dog does not give a handshake, and if you say, hey, give me a handshake, and you extend, you try, but it runs away, it is not getting the treat. It is missing a treat. It is intelligent enough to understand that it has to work towards something, be it a handshake, be it sit, stand, roll over, whatever it is, to get that treat while it is being trained, right? Exactly the same thing here in machine learning as well. When a machine learning algorithm learns, here we are trying to make sure that it is learning based on its own feedback. It will use its feedback in a way where either it has to work towards the rewards. In case, if it is learning right, it will be given a reward every position of the way. If it is going away from the solution, if it is doing something which does not add value to the solution, it is punished or it is penalized. Of course, guys, this is just an example with machine learning. There is no penalization or there's no punishment with real pet dogs. It was just an analogy, so that's an important thing you have to note, right? In machine learning algorithm, the penalty or the reward is just mathematical numbers. It's +1, -1, all of these things which will eventually not hurt anything, right? So keep it at that. What happens here is exactly that. If it's going towards the goal, it is given a quick reward and it knows that it has to maximize the number of rewards it gets. If it is learning something which is not useful to the reward, it gets to the goal, it gets penalized and the rewards keep coming down. So the goal is to maximize the number of rewards, and it does this by looking at its previous steps, previous learnings, previous iterations. So that is how reinforcement learning works. It's a really fun way to work with machine learning. I absolutely love working with reinforcement learning. But again, in the most simplest way, it is okay to implement for a simple solution. But if you have very complex solutions where you have to use reinforcement learning, the implementation does become tough, guys. So that's one thing you should know about. Right, so next up we're gonna check out how a machine learning model actually goes on to learn. What is the procedure that a machine learning model uses to learn, right? Now guys, you see a term that I'm using here, machine learning model. It is very different from a machine learning algorithm. See, once you have the data, you create an algorithm. You use this algorithm along with the data to get your result, right? But after it has seen the data, after it has learned and trained, it is no longer called as a machine learning algorithm. It is called as a machine learning model. So whenever someone says model training, model has trained, they never say algorithm has trained. Algorithm will be used for training. That's it. So after something gets trained, it is called as model, guys. Make sure you keep this in mind, right? So how does a machine learning model learn? First of all, for a machine learning model to learn, it requires data, right? Again, I'm going to give you a real life analogy here, but let us talk about machine learning aspect first. You have certain data, one chunk of data that which you're going to use for this particular solution. You're going to split it into two actually. One batch is called as the training data. The other batch is called as the testing data. Training data is everything that you push to the machine learning algorithm so that it learns, so that it uses it to understand what is going on. Next, to verify if the machine has learnt anything or not, you are going to use another set of data which the machine has never seen before to eventually go on to see if it has learned something, if it can do things in the correct way or not. So training data is used to train, testing data is used to verify if it has learnt or not. So usually in the common usage, data is split into 70% of training data, 30% of testing data, or 80% of training data, 20% of testing. There's a very good balance here in a way where majority of the data gets to the training, because more the data the machine can train better. And of course you can get away with a small amount of testing data to verify if it has learned something or not. But then again, this depends on the type of solution, the type of algorithm, the type of learning that eventually has gone into usage, right? So it's not always the case where if you just use 70% of training data and 30% of testing data, that you will get the correct solution. This is open to experimentation. Sometimes you'll use 70 on the same data set. If you go on to use 80-85% of training data, it will give you an exponentially better solution, because it might have learned something new in that aspect of data which you hadn't given it before, right? So it's very important. Now coming to the analogy, this is literally like how you would write an examination in school or college, right? First of all, you would have been given a textbook or any other study material where you're going to use it to learn nicely, and after that there's going to be an examination where people are trying to evaluate, they're trying to verify if you've learned something or not. Well, training data, testing data, exactly the same thing, right? Now I hope you have complete picture on the data side of things. But to talk about the entire life cycle of machine learning, right? Well, here it is. Whenever you are solving any problem, be it a real life problem, a hypothetical problem, whatever it is, what is the first thing? The first thing you have to understand is that there is a problem that you have which you know machine learning can be used to solve it. The next thing is you understand the problem itself in a way where your thoughts are aligned towards using the domain to solve the problem, right? So once you understand the problem statement, once you understand the business problem completely, then the second step is, okay, so now I understand the problem. Next, I need data to go on to teach my machine learning algorithm and use it to train, right? That is exactly what goes on here as well. After you understand the problem, you start data acquiring, you start gathering data from multiple different places. Data can be stored on your server, on your cloud computing platform, it can be on your pen drive, it can be social media data, it can be competitor data. There is no end to bringing in data from any different source of choice, right? So it's very vital that you understand that you can bring in data from multiple ways and eventually use it. Now, the third thing which we already discussed in the module number 1 is data cleaning, right? I have been mentioning so much that data cleaning is very important. If you do not clean your data, if you feed incorrect data, your machine learning algorithm is going to learn things wrong. If I show it a picture of a cat, but if my data that I've given it says it's a dog, your machine learning algorithm is going to say, hey, it's a dog. Well, as soon as you look at the image, you're like, okay, that's not a dog, that's a cat. Because you know right. You've been taught right from your childhood. Your machine learning algorithm, that's not the case. If the data is incorrect, it will definitely lead to a very inaccurate result, which is going to be a huge waste of time. So it's very vital that data is cleaned. Now, once data is cleaned, you can actually hunt into the data even before applying machine learning algorithms to get, a good amount of insight. It's called as EDA, or exploratory data analysis. Exploratory data analysis is very, very, very popular because, again, no matter where you can think of it, right? See, you have data which can give you so much insights. If you're exploring into it and picking out insights out of it, that is literally nothing but exploratory data analysis. Again, it's completely a domain of its own. It's a module of its own. We're going to be discussing it in detail. But for now, you have to understand this, right? You can get a chunk of information, right, without even performing any machine learning operations. But once you go on to have this basic analysis done, you want to delve deeper into teaching your machine learning. That is when you will bring in a machine learning algorithm. We already saw the 3 types of learning. What were they? Supervised learning, unsupervised learning, reinforcement learning. So you're going to use one algorithm or one or more algorithm with this particular type, whatever you think is the right for the solution, and eventually you're going to apply the machine learning algorithm on the data. It is eventually going to train and it's ready to be verified. You fit the data, you verify if the machine learning algorithm has learned anything or not. That is the step where I'm saying predict your model accuracy. To see if it's accurate or not, first of all, you have to find what's the correct thing, and eventually what you predicted would be right. So once you mix and analyze the differences that exist between what you predicted versus what actually is the reality, you will get an accuracy difference. That accuracy difference will eventually tell you how well your model has learned or not. You can repeat step 2 to step 3 again. You can repeat the entire process to make sure your data is better, it is cleaned better, you're using a different test train split. You can do a lot of different things until you get to the last step, right? So once you experiment, you will have different models which will use different sets of accuracy to learn. So you will have this idea. After which, right, the last thing that you will do is deploy the model. When I say deploy the model, it means that I have the solution for the problem ready, and now I'm putting it out there so that I can actually and eventually, solve that problem, right? That's the process of model deployment. Maybe it is going on a server where you're trying to implement ML on your website. As I told you, right, Amazon, Netflix. So when they code it in the background, they've done until predict your model accuracy step. After that, as soon as they put it on their website, as soon as things go live, that is when they have deployed it. That is when it is actually working to provide a solution, right? So that is something that you should know about. Right, so guys, this is the entire architecture of how a machine learning model learns and works. I hope I was completely clear on this aspect. Next, the important thing that you already knew about from the last module that we checked out is Python is the most important programming language we have whenever we are working towards machine learning, right? It is very, very, very vital that you, of course, you can use multiple different languages for machine learning, but you have to find the simplest and the easiest way to do it so you don't break your head about complex syntax, but rather use your time effectively to eventually drive a good solution, right? That is where Python comes into the main picture. Python is a very, very powerful programming. As we have discussed already, it is the most popular language out there. But for machine learning, it is the number one language. It is always preferred no matter what. Why? Because it gives you a high level syntax where you can again spend time on logic rather than the syntax itself. It's very easy to work with. And personally, if you ask me, the biggest reason why it's popular is now when you think about machine learning, if you've never looked at machine learning code, there's a good chance you might think, okay, so if I have to teach my machine, train it and get it one step closer to artificial intelligence, it might take a huge amount of code. Guess what? With Python, that's not the case. A tiny amount of code that you write can have a huge impact, as I'm going to show you practically now. It's a very important thing, right? So you don't have to write 100 lines of code to see a tiny output. You write that tiny line of code to see a huge output. That is the power of which Python adds to this field of machine learning, guys. So that's an important thing. And of course, working with Python is amazing. You have multiple ways. You can install Python from the Python website. You install it via Anaconda. You can have an IDE, an integrated development environment like PyCharm, or you can use a very simple Jupyter notebook on the Google Cloud platform called as Google Collaboratory. Again, all of these are free to use. So eventually at the end of the day, working with it, setting it up and starting to use is easy, as we have already discussed in the previous modules, right? Here are some of the important libraries which you're going to require for machine learning as well. First of all, to store data, to array processing data, manipulate it, and eventually work with complex numerical computations and data manipulation operations, you require NumPy and Pandas. NumPy and Pandas we covered in the last module to a good amount of depth to show you all the operations which you're going to require, right? Again, we're going to use all of these now as well. But then one important library that is very, very important for machine learning is scikit-learn. Scikit-learn is a beautiful library which is meant for machine learning, which is built so that machine learning can be worked around with in a very, very easy fashion, right, guys? So after these three libraries, again comes data visualization libraries. You have Seaborn, you have Matplotlib. We're going to discuss all of these in the data visualization module in depth again, right? Now, whenever you're taking a look at the traditional way of how one can go on to program versus how a machine learning algorithm learns, there is a huge difference which you may or may not know. So when you compare traditional programming, how does it differ with machine learning, right? Here is it. Here it is. It's a very, very important difference. Look at the left of your screen right now. I've put in traditional programming, right? In the case of traditional programming, what usually happens is you have data and you have a program. Your program uses the data, it's a compiler, whatever it is, and eventually gives you a simple output to work with, right? You have input, you have the computer program. Input goes into the program. Eventually, what you get is an output at the end of the day. With machine learning, that is not the case. You have data and your machine learning algorithm already knows what the output is. It will know where it has to get to. It's not like there is no light at the end of the tunnel here. It already knows that, hey, using this data, I have to get to this output. So how can I get from this data to this output is how machine learning works. The entire process of it learning to go from understanding the data to get to the output is where it's called as a machine learning model, right? So every time we talk about machine learning, it can be very confusing, saying, hey, you have an input, you have a program, you get to the output. No, with machine learning you already have the output and the data in the previous stage itself, and the process is what is it's what we are after basically when we look on to this domain as well, guys. So this is a very, very important difference which you should know about if you're looking towards learning machine learning, no matter what level, basic level, intermediate level or advanced level. This is a foundational concept which you guys should know about, right? Now that we looked at a lot of things, it is high time we check it out all practically, right? So here are some of the machine learning algorithms which will add a ton of value to not only your career but to your entire learning in the field of data science as well. Of course, all the algorithms that I'm about to discuss right now are the most popular ones out there. They are the trending ones for this particular year. People who are hiring, right? Companies who are hiring right now for machine learning jobs or data science jobs will ask in the job description saying, you may or may not know one or two algorithms, but all the algorithms that I'm about to discuss usually are in that list which says it's a compulsory requirement for you to understand. So when the recruiters themselves say that you require these many machine learning algorithms, the knowledge of it, well, it becomes vital that we cover it and teach it for you, right? So here are some of the algorithms that we're going to be discussing, guys. First of all, there are many different algorithms that you can look towards and work with. There's linear regression, logistic regression, again, regression, right? We already discussed this as supervised learning. You have the naive Bayes algorithm, you have the KNN algorithm, you have SVMs, support vector machines, you have random forests, and you have many different types of algorithms, which eventually has its own way, uses its own protocols, uses its own way of learning to eventually get to the result. But to simplify things down and not pick up all complex data sets, let us work one by one into the top machine learning algorithms that you have to learn, guys. We're gonna keep it very simple. We're gonna take a look at simple data sets. I'm gonna explain what each line of code means so that you completely understand, right? So first of all, we have linear regression here. Again, what is regression? To roll back on the same concept we checked out, we are trying to model an input variable by applying a function on it and eventually calling it an output, right? An output is a function of the independent input variable. So when I say input variable, when I say independent variable, it means the same thing. When I apply a function on the independent variable, it becomes a dependent variable on the outside, and that is your eventual y is equal to f of x. Y is the dependent variable, x becomes the independent variable, right? So there's another question which I'm usually asked a lot when I talk about linear regression, no matter where I go, is why is it so popular? Why do I have to know machine learning if I'm if I'm looking towards machine learning or if I'm looking towards data science as well? Well, the first thing that I can tell you, it is extremely popular because it will give you this cause-effect relationship which the real world requires a lot, right? Now, to simplify things, just let's look up at the sky right now if you're sitting outside or something, or maybe just look outside right now. How is the weather? If I ask you a question, what will you do? Right? You look up at the sky, you look at if there are clouds, if it's not cloudy and all of that. If there are black color clouds and you know that there are possibilities of rain, you might get a hailstorm, you might get snow and all of these things, right? If there are a good amount of clouds, right? Of course, weather changes rapidly. That's not the point here. The cause of the rain is what? Clouds. But what is the eventual effect? The effect is rain, right? Clouds cause rain. The effect is rain, the clouds is the cause, right? So that relationship, I just give you one example. You can think of hundreds and hundreds of examples like this. So this is eventually what is used in today's world as well. That's why it is very popular. So what we are going to do is we're going to head to Google Colab. We're going to practically check out how we can implement a simple linear regression model by using a very popular data set. It is the Boston housing data set, right? Now with this data set, what we're trying to do is this consists of all the details of the houses in a locality in Boston. We are trying to see if our machine learning algorithm can predict the prices of the houses based on a multivariable assessment going on. It's called multivariate analysis. We're going to use multiple variables to see eventually to train our machine learning algorithm saying, hey, do you know why the prices are like this and how accurately can you detect these prices? That is the question we are going to get an answer for right now. Alright guys, we are now here at Google Colab. As I told you, Google Colab, we have used this in the previous module. It's a free Jupyter notebook hosted on the Google Cloud platform. You can just type in your Python code, hit the play button and you're done. You do not have to install a lot of these popular libraries that we're going to be working with, right? So again, the first step is to make sure we import all of these all the data sets that we're going to be using for algorithms. Of course, you can do it step by step, but to simplify everything, let me quickly go on to import all of these. There's a simple upload button here. With the upload button, all I have to go on to do is just put in our data sets that we're going to be using. It will upload it one by one, and so that we don't have to do it every single time here, right? Again, let the circles finish. It means that it is uploading. Alright, perfect. So all of my data is now uploaded. Let me zoom in on my screen to the max where you can see all the data. Right. Now guys, with linear regression or any algorithm that we're going to use, the first step is what? We're going to be importing all the libraries that we have to use, right? Look on your screen. We are importing NumPy, we are importing Pandas, we are importing sklearn. NumPy and Pandas, I told you it's going to be very important for machine learning. We are using it right now. Scikit-learn or sklearn as it's called is a very important library for machine learning, right? So after importing the libraries, the next step is to import the data set so that we have a workable data set that we can work with, right? So here, as you can see, pd.read_csv means pandas, where we're trying to read a CSV file, calling it the housing.csv, where all the data of the Boston housing data set is present. Let me go on to hit play, and it prints us a lot of the row and column values that are present, right? It's printing us 5. Let's see if we can print 10. Now, boss1.head, boss1 is of course a variable that we just created. .head is a method. If you do not pass any parameters to it, it's going to only output 5. Now in the bracket, if I put 10 and if I hit execute, it's going to give me the first 10 rows worth of data, right? Now there's so many different things here that are talking about the prices of the house, the crime rate that's present, right? What is the age of the house? So whenever you're trying to find the value of a house, what will you look at? How convenient it is from the nearest supermarkets? How old is the house? What's the tax ratio? How many floors does the house have? What is the area footage? You look at a lot of different things, right? So all of these are, each of these columns that you see here are eventually individual attributes that contribute to the price of a house as well, right? Even crime rate. Crime rate is a very important thing that you look at whenever you're buying a house. You'll see if the area or locality is shady or not. If it is shady, maybe the house is worth a lot less, correct? So that's an important thing here. So all we are trying to do at this point is to import the data set, import the libraries, print the first 10 for your reference, right? The next step after importing the data is to clean the data. Now to clean the data in this particular data set, all of what we require is numbers, right? For example, look at the age column. If I ask you what your age is, will you say my age is orange, my age is apple? No, that's a nonsensical answer to a question, right? If I ask you your age, I am 100% certain that the answer you're supposed to give me is a number. Now, sometimes it so happens that in the data set, right, it will not be a number, it will be something else, something meaningless. You have to remove all of those, because if you do not, your machine learning algorithm is going to use those nonsensical data entities to learn everything wrong, as I mentioned, right? So the next step we're going to be using a function called as isNA. Is basically a function which says, is it a number? We're going to be basically using this method to see if we have any characters where we have to have numbers, right? NaN stands for not a number. We are trying to find values which are not numbers, in the sense they are characters, string and all of that, right? Thankfully, this is a data set which is already pre-processed and cleaned. So no matter which column you take a look at, all the values are 0. It is saying that, hey, everything here is a number. There is no character or there is no data which can throw your machine learning algorithm off. This is a good thing. The data is clean. It is already pre-processed. The next step of the way is to make sure we can clean the data. The next step of the way is a very simple one where we actually try to split the data, as I mentioned, right? We're going to split it into training and testing. That is exactly what we are doing with these 3 or 4 lines of code. But here, I've mentioned that, I want to split it 70% of training, which means that 30% of the data is going to go for testing. How do you know? What do you see on your screen that says it has to be 70% for training, right? Look at this variable which I use for test train split methodology. It says test size is equal to 0.3. Now, when it says test size is equal to 0.3, I am telling it, hey, what I want to use for testing later is 30% of the data. 0.3 means 30. So what is the remaining? If you have 30, it's 70, right? That becomes training. What if I put testing data as 20.2? If it is 0.2 or 20%, it means 80% of the data is being gone for training purposes, right? Now, if this is 0.5, it means 50% of the data for training, 50% of the data for testing, right? However, I have found the sweet spot to be somewhere around 70% for training for this data set. So let's check out what goes on. The next thing we're going to do is, since we are checking out linear regression, right? LR equal to linear regression and LR fit equal to X train and Y train. So we are trying to model the data in a way where it uses, no. So what we're trying to do here is we're trying to model, get the model to understand the data that we have been checking out in terms of the training data. Now, if you were a person who thought you required 100 lines of code to train a machine learning algorithm, you have 3 important lines where the machine learning algorithm actually does the learning process, right? The model fitting, when you say fitting the model, it means to actually use the data to learn. And later you're going to be predicting it based on the testing values which I mentioned. As you can look at it, the parameter we send for predictions is also the testing data set rather than the training data set, right? If you just send the training data set again, what happens is that it already has seen that data. It will tell you 100% accuracy because it knows everything that it is seeing. If I give you a textbook and if I ask you, hey, write an examination based on this, where there are direct answers in the textbook, you do not have to spend a lot of time to learn it. It doesn't make sense. You can get 100 out of 100, right? But if I give you something else where you have to use your processing power to do it, that is exactly what we're trying to do. So with these 3 or 4 lines of code, our linear regression algorithm has learned everything it has to learn. Next, we have to see if it has learned or not. That is where we use error rates to actually go on to see if it has learned something. Now there's an error rate called as MSE or mean square error, which is again a concept of its own, which we are going to use to predict if the machine learning algorithm has learned anything or not. So let's see what error we get here, right? So it will be somewhere around 5-ish. Okay, yeah. The error that we see for using linear regression is 5.54. Now, if you are wondering about what this number means, hold this number in your thought for a second, because we're going to use the same data set for another algorithm. That way you will understand what happens if you use the exact same data but 2 different machine learning algorithms, right? Which one learns more accurately? Again, we're going to be checking this data set out in the next machine learning algorithm that we will discuss. Of course, not the exact next one. We're going to be checking out the third one. But now, moving to the second machine learning algorithm that we're going to be checking out is naive Bayes algorithm. Naive Bayes algorithm is a very, very popular algorithm that is, again, not just popular just because how it works, but rather the usefulness of naive Bayes as well, guys. Now, naive Bayes is an algorithm which works based on the Bayes theorem. Now, Bayes theorem is completely based upon the concepts of conditional probability, right? Conditional probability talks about the probability of one event occurring if another event has already occurred, right? P of event 1 occurring given that P of E2 has already occurred. That is Bayes theorem. So naive Bayes uses the concepts of conditional probability to work. It is again a type of supervised learning, just like how linear regression was. And here it is called naive because there is no codependency in between these attributes. So each attribute does not use itself or use the other one to get to the output. So since you don't have have the dependency, it's more like a loner entity which sort of learns to, which sort of tends to not learn efficiently. But it's not efficiency, but it's the way it learns. That's why it's called as naive in real life, guys. Again, it's a funny way to name it, but yeah, it does work. And now, it is very, very popular for two important things: is social media marketing and product management. So whenever you have a supply chain analytics problem, or whenever you're trying to market something on social media, you want to analyze the impact of your marketing, right? Naive Bayes is very, very, very popular in those cases. Again, there's many types of naive Bayes algorithms that we're going to be checking out. There's the multinomial naive Bayes, there's Bernoulli's, there's Gaussian. We're going to pick up one of these to make sure that you understand naive Bayes in detail. Of course, to do that, we are going to be using the social network data set, guys. So let's quickly get back to our Google Colab. Let me minimize linear regression and check out machine learning with naive Bayes algorithm, right? Perfect. Again, guys, what is the first step whenever we go on to work with anything? We import all the libraries, NumPy, Pandas, and scikit-learn, right? As soon as I click play, all of the libraries are done. The next thing is we're going to be importing the data set. In this data set, right, the salary data that we're going to be working with now, I have already pre-processed into training data and testing data separately myself. So I do not want the machine learning algorithm to again split it. Of course, I can manually define and get it to read and input two files. Salary data underscore train is the training data set. Salary data underscore test is the testing data set, right? So as soon as I go to hit play, let us check out what the data set itself is. So here there are a lot of different columns of how the data is working with, right? So whenever you're looking at salary data, we're trying to see what adds the most value to the salary, right? The working class of the person, the age of the person, education, marital status, occupation, relationship, the race, the sex, the capital gain that they're holding. Does that have an impact on having a high salary? So what value, what attribute here adds a lot of value to eventually having a high salary is what we're going to check out, right? So as you can see, we're trying to check out all the education that the person has and the eventual salary that the person might have. What is the salary range that they're getting? Which country are they native of? How many hours per week they work? So all these data we're going to be using to teach the machine learning algorithm, right? So to go on to use naive Bayes, the next thing we're going to be using is a concept called as a label encoder. Now, all of these values that you see, right? Relationship, not in family, husband, white, male, female, married, spouse. All of these are what type of data? Categorical type of data, right? But to make sure our machine will not understand husband, wife and all of that unless you teach it, right? To simplify all of these things, we're going to convert every single categorical variable we have into a numerical data, and just to do that, we're going to use something called as a label encoder. That's the entire process. All we're trying to do is convert categorical data into numerical data here. Once that is done, all of these get encoded into a numerical data format. It becomes variables of its own. Then we actually go on to assign it testing phases and training phases. That is literally what we're doing. 13th column is the last column for salary, right? So we're trying to add these encoded variables and assign them, saying, hey, what is your impact on the salary, right? As I told you, there's three types of naive Bayes classifiers that we're going to be, that we actually have, which you can use depending on your application. Here we're using Gaussian naive Bayes. Gaussian naive Bayes is mostly used for continuous data, right? Now the data is continuous here. Salary is a continuous thing which will change based on your experience, right? The first salary which you might have got after graduation is very different from the salary you have after 10 years of experience. So it's a continuous graph that rises up and up. So if the data is continuous like this, you're going to be using Gaussian naive Bayes. But if your data is, let's say, binary data, if you want answers such as yes or no, true or false, up and down, all of these answers, which there are only two possibilities, binary outcomes, you're going to be using the Bernoulli's naive Bayes classifiers. And there's another one which is called as multinomial naive Bayes. Multinomial naive Bayes is extremely popular for text classification, speech recognition, all of these things. We're not doing any sort of speech recognition here, nor are we having a binary outcome, right? Hence the reason we're going to be using Gaussian naive Bayes. Now, as you can see, as soon as I ran one line of code, model fitting is actually done. The next thing all I have to do is predict by passing it the testing data to see if it has learned something or not. And since that is done in 2 lines of code, the next thing I'm going to go on to do is print a confusion matrix. Guys, a confusion matrix is a very important important concept which we already checked out in statistics, right? True positive, true negative, false positive. All of these values, as you can see on your screen, the most concerning numbers will be the true positive values and the false negative values. These has to be the highest because at the end of the day, if these are the highest, it means your model has learned really well. We do not want false positives, or we do not want false negatives, because these are sort of the values which your machine predicted wrong based on all the values out there, right? Now, if you do not understand confusion matrix, again, I have an accuracy metric here at the bottom which says, hey, I have an 80% accuracy rate of detecting things correctly and making sure it matches up to what we predicted at the start as well. So for every 100 elements of data it sees, it can predict 79 or 80 of it perfectly. That is what our machine learning algorithm is trying to say to us, guys, right? That was naive bias. Next, we're going to take a look at the KNN algorithm. KNN algorithm has a full form. It's an abbreviation. It stands for K nearest neighbor algorithm, right? Now, let me give you an example to explain what KNN algorithm means or how it works. Let's say you want to visit your friend's place, who stays nearby to you. Is there only one road ever that you can take to get to your friend's place? There's a good chance that you can take very inefficient routes to eventually get to his house. You can take one route, two route, another crossroad, whatever it is, right? If your friend stays in the next street, the most inefficient way to go to his house is probably fly to America and fly back and directly go to his house, right? That's a possibility. It is stupid, it is meaningless, I understand, but it is a probability still, right? You cannot say it's stupid in the case of machine learning because it does not understand that it is stupid. You have to teach it that, correct? So here what we're trying to do is we have certain data. As soon as we put new data there, we try to index it based upon whatever data points are nearby to it, and from then we map an association saying, okay, so it is closest to this data. It may be the same data or similar data as well, right? So again, that's a very important thing. KNN algorithms are a type of lazy learners. It means they do not really take a lot of time to execute. They do not want a lot of computing power to go on to learn and execute as well. But then to go on to practically check it out, first let me give you a theoretical example to make sure you understand these things properly, right? Now, what we're going to actually do is we're going to try to predict if the person is a male or a female based on their height and weight. Now, it's usually a common survey or a statistic saying that, male or guys weigh more and they are usually taller than the female population. Of course, it might not be the case in every single country or every single place, but the usual statistic is somewhere like this, right? Guys are taller and they are heavier in the build because that's how human bodies eventually work. In that particular case, can we predict if we just have height or weight of a person to see if they are male or female? Well, here are some of the things. I have heights of, these many people, 7 people. I have weights of 7 different people. And eventually I have the gender also, that if you have this height and weight, that person is a male. Now, this is accurate data. This is the data that I've collected from 7 or 8 different people. Now, if I have to teach my machine learning algorithm using KNN, saying, can it predict if it's a male or a female? Here's a graph. This graph is very simple. You remember seeing this chart, right? This chart with just its height and weight in the x and y axis. We have just put the data out there. As you can see, we had 7 data points, right? 3 of the data points are female, as you can see in the pink rectangle, in the pink triangles. Then 4 male data we had based on the green circles you see on your screen right now. As soon as you look at it, you can sort of say that height and weight of the females are slightly less compared to the height and of course the weight of the male population in this example, right? Now, what I will do is, there are 7 people here, I'm going to add another 8th person. I'm not going to tell if it's a male or a female. I just know that this person has a height of 190 centimeters and a weight of 100 kilos. If I put it and map it in the graph, the blue color rectangle you see right now is where that person will be put if the weight and height are matched with what everything else is put, right? Again, you as a person can look at this graph and say, okay, this new person added here is very similar to the guy's weight and height, so that he might be a guy, right? If it was somewhere here, you would say that there's a good chance it's a girl. But for our machine learning algorithm to do it, we have the value of k. K is us saying that, use the 3 nearest neighbors to map a pathway to the new person who was added. If k is equal to 3, as you can see, these three green dots are the nearest neighbors to this particular rectangle, to the new data, right? So if k is equal to 3 and if all three are pointing to the same guy and all the three closest points are guys, your machine learning algorithm can say, hey, I have a 90%, 95% accuracy of saying that the new person you added is a guy. That is how it learns, right? Now let's put k equal to 5. If we put k equal to 5, we are finding out the 5 nearest neighbors, right? 4 of them are guys, 1 is a female here. Now, 4 of them are guys, but 1 is a female. Can it still say it's a female? No, right? Why? Because the majority of the neighbors are still male population, right? So that is how we accurately say, hey, the data we have here, the new person you added is a male, right? Now, if you've been saying I took k equal to 3, I took k equal to 5, both are odd numbers. Why did I only pick odd numbers? Well, you can use even numbers also, but the general way of working in the KNN algorithm is that if you pick the k value as an odd number, the number of neighbors that you have to track and index, you will use it as an odd number if you only have two classes in comparison, right? Here we only have two classes, male and female. That's it, right? We're only considering these two populations for this example. So since it is only two classes, it is vital that we go on to use this value, which is, an odd number, guys, right? The next thing we're going to check out is, again, as I told you, right, we're going to be checking the same Boston data housing data set. With linear regression, we got an error rate of somewhere around 5.4 or 5.5. But what is the error rate we're going to get if we use KNN algorithm, right? So let me quickly minimize the naive Bayes algorithm and let me open up KNN algorithm. Perfect. So again, this code is the exact same thing that we checked out while we were working out with linear regression. All we try to do is import the data set, import the data, import the libraries, print out the first 5. Next, we're going to be removing all the NaN values. As I told you, the data is already clean. Again, this was the exact same thing that we checked out. We're going to be splitting the data into 70-30. We checked out the exact piece of code. But the next thing is what we didn't check out is where we are trying to load the KNN model and use it, right? These 4 or 3 lines of code that you see is where we're actually going to use the KNN algorithm, right? So again, 3 lines of code. But if you see in the bracket here, I've put a parameter 3 for KNN regressor, right? This is me telling the machine learning algorithm, hey, use k equal to 3, right? As I showed you, as soon as I run this again, it's going to use the training data to learn. It's going to use the testing data to see if it has learned and all of that. 3 lines of code. Now, the next thing is, how do I know for sure that for the Boston housing data set that k equal to 3 is the most accurate value? K equal to 10 may give me better solutions, right? To make sure that I'm tuning all of these values and tweaking it to get my model to learn accurately, I'm going to do hyperparameter training. I'm going to do hyperparameter tuning. In hyperparameter tuning, what happens here is that I just print, since it's a small data set, I can just get the machine learning algorithm to work for multiple k values, which is exactly what I've done here. I have got the k value from 1 to 49 to see where the k value is, the error is the lowest, right? So k equal to 3 is what I said will be the lowest. It's 7.01. But hey, check out k equal to 4. K equal to 4 has an even lower error rate. So what it's trying to tell me is, for this data set, for the Boston housing data set with this algorithm, you will get the most accurate output. You will get a lesser error rate if you use k equal to 4. I wouldn't know this until I did it, right? Hence the eventual purpose of mapping out all the k values out here, guys. And of course, the last step is for us to always print the mean squared error. In this case, the mean squared error is 7.014 for k equal to 3, correct? It was 5.5 for linear regression. For the exact same data set, it is 7.01 here. What does that mean? It means that our machine learning algorithm for that particular Boston housing data learned better in the case of linear regression rather than using KNN on that data set, right? Now, once you use multiple algorithms, this is the clarity that you get, which is a beautiful thing. So, right, guys, next up, we're going to check out support vector machines. Support vector machines are very complex entities in the world of machine learning, because here the way that they learn itself is very, very different. They use multiple unknown parameters and they use a technique which is called as a black box techniques, because there are so many unknown parameters, so many things going on in the background, that that it uses to learn, right? But then there are certain basic things that it has to work with is linear data and non-linear data. So in the case of non-linear data, since it is very difficult to train, it actually separates this data by making use of something called as kernel tricks. And all of these parameters which eventually come after kernel tricking is usually tested and tuned by making use of kernel functions. Now there are multiple kernels that we can use as the polynomial kernel and the RBF kernel, the radius basis function kernel. Each kernel has its own way of working, right? So what happens with the polynomial kernel is that with the polynomial kernel, the data gets transformed into a higher dimension and eventually it works into its non-linear classes. But with the case of radial basis function, the RBF kernel, here we have a parameter called as gamma, and we continuously tune this parameter rather than changing any dimensions, which eventually gets us to our results. That is how we're going to be using SVM, guys. So until we keep scaling these gamma values, RBF will go on to give us different outputs, and we find the best one and we usually hold it there, right? Now coming to the advantages of SVMs, the most important thing is that it is very, very flexible to work with a variety of data, be it unstructured data, structured data, semi-structured data, whatever it is, right? Unstructured data is images, music, videos and all of that. Structured data is everything that we checked out, right? A nice CSV file with rows and columns worth of data. Semi-structured data, there's again multiple types of data based on the usage as well. So one advantage with SVMs you have to understand is that overfitting is not present, or it's very less here compared to all of the other models out there. So overfitting is a situation where your machine learning algorithm is learning so deeply with so much focus that it starts picking up noise in the data rather than useful stuff. So using its noise, it will not learn anything at the end of the day which is accurate, right? The data is going to be completely inaccurate because it hunted so deep into the data, it found noise rather than useful information. That is overfitting. In the case of SVMs, overfitting is less. But to talk about the disadvantage of SVM as well, one thing is that the training time will be a lot more if your data is huge. All the data sets we've been using now are very tiny figments of data, so it's working beautifully well. There are some cases where your machine learning algorithm can train for hours together, if not days together as well, if you use SVMs, right? The reason why SVMs are popular today is because they have a huge impact in the world of healthcare and in the world of banking sectors and in the case of banking sectors as well, guys. So it's a very popular thing. Let's actually check it out practically now. Let me just minimize KNN. Perfect. Let me open up SVM. And what's the first step in SVM or any algorithm? I can zoom in a little more. Perfect. Is to import all the libraries, importing NumPy, importing pandas. Now here I have another library called matplotlib. Matplotlib is used for data visualization to create beautiful looking graphs, right? Done. The next thing is to import the data set. Here we're going to be using the social network advertisement data set. So what we're trying to do is, if you advertise something, right? If you're advertising a pen or a pencil, and you know the salary of the people who may or may not buy the product, right? What is the probability that a person will buy the product if their salary is somewhere around that, right? So using salary to see if a person of this salary can afford your product or not. Now, if there's a very expensive car like a Ferrari or a Rolls Royce, there's a good chance the common man cannot be able to afford it, right? So advertising that to a common man might be considered as a waste of money as well. So to check if the person of this salary band can afford a product like that is what we're going to try it out. But with this data set, as you can see, we have a user ID, we have the gender and age, estimated salary and purchase. Now, what are we concerned about? We are using the salary to see if a person purchased or not. So we do not require the age. We do not care about if a male bought it, female bought it, or whatever it is. So we can drop all of these columns, user ID, gender, age. I do not want. I just want salary and purchase, right? So I'm going to filter all of these columns out with just 2 lines of data. The next thing, again, we're going to be splitting the data. This time not 70-30, but 75-25. 75% goes for training, 25% goes for testing, right? As soon as I click this, that is exactly what I did. Now the data is split up. Next, we're going to be using a scalar called as the standard scalar for normal distribution. The normal distribution is a bell curve which will add meaning to the data so that we can plot it and derive some meaning out of it, right? So by using a standard scalar, all we're trying to do is we're trying to use the training data, map it and verify it against the testing data by using normal distribution. Again, distributions are are a very important part of statistics, the concept which governs the world of data science, guys, right? Next, as I told you, there's polynomial kernel and there's RBF kernel. In this particular case, we're going to be making use of the RBF kernel, 3 lines of code. Your model, the SVM has learnt it completely, and at the end of it, if you're trying to print the confusion matrix, again, confusion matrix, we discussed this in the last module: true positive, true negative, false positive, and false negative, right? So again, I didn't say it in order. There's an order of which the values goes on. You guys are supposed to tell me the order because we covered it in detail. The values I am concerned with are 64 and 29, that they're high. That's perfect. We have 4 and 3, which the model got incorrect, or it predicted in the wrong way, which is absolutely okay. Again, here is where the statistics come into the picture, right? You remember we calculated precision, recall, F1 score and all of that. Guess what? We calculated it here again. Of course, we're not doing it manually anymore. We have classification report which will give us all the details. So we have the precision value if the person bought the product, the recall value if the person bought the product or not. We have the precision, recall and F1 score if the person actually bought the value. 0 means the person didn't buy it. 1 means our prediction based on if the person actually bought it, right? Pretty simple when you look at it, but it's a beautiful concept of how support vector machines work. Right, guys. Next up, coming to the 5th algorithm, the last algorithm that we're going to be checking out in this module is the random forest algorithm. Random forest. When you say forest, what is the first thing that comes into your mind? It's a group of trees. It's a collection of trees, right? Here also it's a collection of trees, but not just trees. It is decision trees. Hence, once you have multiple decision trees, you just call it a forest. In this case, it's called as a random forest algorithm as well, right? One thing you have to know about these decision trees is that they have very high variance and very low bias. This is the exact opposite of what we need. We need low variance in our data and very high bias of learning, correct? To make sure that we solve this problem, we just group all of these trees and create a forest. That is how we solve this problem of decision trees having very high variance and very low bias. So what we do here is we take in data just like a real tree. A tree is going to have branches, it's going to have multiple branches, it's going to have leaves, right? So one important node will be our input. From there we create all our branches, and every single leaf at the end of the day, or the end nodes, are called as leaves. They will be the output in this case, guys. That's why the name random forest algorithm. So how do you go on to pick data when you're working with random forests, right? If you are considering 2 samples here that we've represented by 2 colors, the red and the blue color that you can see, we have multiple columns, right? In the concept that we have called bagging, we compulsorily pick data from all the columns out there to train the machine learning algorithm and to teach it. As you can see, all the pink ones, everything is picked, blue ones, all the columns are picked. But in the case of random forest, what happens is that we do not pick up all the columns. We just randomly pick up a couple of columns to actually go on to build decision trees and eventually get our model to learn, right? So that is exactly what we are going to check out here. The advantage of random forest algorithm is that it works amazingly well for classification problems and regression problems, which we already checked out. But if your data is not clean, and if you're a person who doesn't like to clean data, again, it's a very hectic task. Guess what? With random forest algorithm, sometimes if your data has missing values, random forest algorithm has the capability to automate it and fill it with zeros, ones, or whatever it is that it thinks will not hurt for learning. So it can automate itself, learn and fill in data wherever it is missing automatically too. But then one disadvantage of random forest here is that it will require a lot of computation power if you're looking to build very complex trees and forests, guys. So that's an important thing that you should know about, right? So let's quickly check it out practically now. So with random forest, again, the first step is pretty simple. Import the libraries, import the data set, print the first 5 elements of the data set, right? Now, let me actually go on to print 10 instead of the first 5 because I want to show you something here. Right, now that you see the data, I have 3 tabs here, 3 columns: position, level and salary, which I think is self-explanatory, right? A junior consultant is a level 2 employee who gets an average salary somewhere around 50,000 rupees. A CEO is a person who's a level 10 employee, the maximum level you can obtain, and he gets a salary of somewhere around 10 lakhs per annum, per month, whatever basis, right? We're not concerned about the duration of this particular salary. But look at the growth with the level. A person who's a business analyst is a level 1, junior consultant level 2, senior consultant level 3, manager 4, country manager 5, region manager 6, senior partner 8, 9, 10, right? So what I will try to predict is the average salary of a person who has the level of somewhere around 6 or 6.5 based on all these data. Again, to do this, I only require two columns, level and salary. I do not require position, right? So I'm just going to remove the position column, use only the level and the salary here. Here I'm going to be using 10 different trees. As I told you, a random forest is based upon multiple trees. Here I'm going to be using 10 different trees. N estimator is equal to 10 means that I want 10 trees to create one forest, right? As soon as I go on to click this, the model has actually learned the creation of the forest is done. So the next thing we're going to do is predict the salary of a person who has level greater than 6.5. So instead of just telling you that in a verbal way or to show it to you in a number, I want to show it to you in a graph. Now here is a very beautiful visualization, guys. What is the, as you can see, the salary, I have it on the y-axis, the position, I have it on the x-axis. The position we're trying to find is 6.5. So it might be somewhere here, right? Now if I go to the left of that point, the salary is somewhere around 0.2. Hey, the salary we were checking out was in the thousands. What is this 0.2? Look at the legend on the top. It says 1E6. 1E6 literally means multiply that number, whatever you get on your salary, by 10 lakhs. 0.2 into 10 lakhs is what? 2 lakhs? 2 lakhs for a person who has an average salary of 6.5. Let's take a look. See, for a person who has a salary between 6 and 7, the average salary can be considered as 2 lakhs as well. This is what a machine learning algorithm learnt and predicted for us. So when you have a result in a graph like this, which is very nice to look at, it adds a lot of value to your learning, guys. So this was the top 5 machine learning algorithms that you have to learn. Again, to reiterate, with data science, there is so much content online out there. Do not be overwhelmed. Take it slow, take it easy, talk to subject matter experts. I am a subject matter expert in data science, as you might have figured out by now. If you do not use a structured way of learning, right, you definitely will quit because things can get complex if you're learning. Now, keeping all of this in mind, we put out these tutorials to make sure you get the right amount of knowledge, guys. As I told you, there's so many places where you can learn free content, especially here at Great Learning Academy, where you have access to 200 plus courses in multiple different languages taught by multiple different subject matter experts. You can learn for free, enroll for free, get a certificate of completion absolutely free by not paying us 1 rupee as well. So that's an important place that you have to be, that you definitely should check out. Then we have Great Learning YouTube channel and Great Learning blogs, where again we put out a wealth of different content. So it is very vital that you subscribe to the Great Learning YouTube channel and hit that bell icon so that you're in touch with the channel, and blogs for all of you readers who absolutely love reading. Right, guys, then if you're very, very serious about your education, if you want to become a complete expert in this domain, to get a job, to switch your career, whatever it is, right, make sure you take a look at the specialization and post-graduation offerings we have here at Great Learning. We have multiple PG programs, MTech program, MS programs, certification offering programs, which is done in collaboration with some of the most prestigious universities and Ivy League schools, around the world. So you will have subject matter experts, professors from these renowned universities teaching you as well. Texas MECOM, Northwestern University, Stanford, Great Lakes, PES, multiple different universities as well. So if you want to be handheld right from being a beginner all the way to becoming a complete expert in a domain, make sure you spend some time. Head to the greatlearning.in website to check out our specialization and post-graduation offerings. Right, guys, on that note, you have reached the end of this module. Welcome to module number 9. Now, as the name states, deep learning is such a fascinating concept that all of you guys should definitely know about if you are considering a career in data science. Now, even though deep learning forms to be, in the way of getting towards artificial intelligence, it is a destination that you have to get to before you have the product, which is at the end of the day achieving artificial intelligence, right? Being a goal of data science. To get there, you have to know this particular module, guys. There are so many things we are going to talk about in the case of deep learning. There's multiple things which you guys should know about. So let's get started with it. Let us understand this very, very important module of deep learning. But then, guys, if you already know what deep learning is, take a second, pause the video, head to the comment section right now and just type it out and let me know what you think about deep learning, right? We can have a conversation, of course, in the comment section. And if you have any questions at any point of time, time during this full course tutorial, make sure you're putting down your queries in the comments of this particular video. I'll be more than happy to answer them. Right, guys. Now, if you are curious about what are the particular takeaways, at least in this particular module as of now, we are going to be covering, an introduction to deep learning first. It becomes very vital that you know what we are trying to achieve with this domain, right? If you do not know what the goal is, then it doesn't make sense to even know why we have to use it. So I'm going to give you the goal first. I'm going to try to tell you what, we are going to achieve. Later, the curiosity is going to build saying, why do we require deep learning for this? Can't it be done using anything else, or what are the practical applications of deep learning and all of that? As you can see, I am going to be answering all of that as well. And then deep learning in its name itself sounds very, very similar to machine learning, right? Machine learning, deep learning and all of that, but you have to understand there is a good amount of difference that exists between these two concepts. Now again, I'm going to be talking about this in depth when we get to the session, but right now it is vital that you know that there is a difference that exists. It's a very important difference, and that you will get to know when you finish learning this module. Right, guys, the next thing we're going to take a look at after that is we're going to be checking out certain important deep learning use cases that we have around us that are revolutionizing the world as we speak of it. Now, as you can see, with every single module, we have taken an approach where we cover theory, where we cover practicals as well, and I'm giving you real life applications of it too, right? That real life applications should be, piquing your curiosity in a way that you would want to find out more applications. So when we come to that section, we're going to check that out. And lastly, in this particular module, we are going to be discussing the top libraries that are available for deep learning when you go on to make use of Python, which of course is what we are doing throughout this course. Right, guys. Now, without further ado, let us actually dive right into the introduction to deep learning to understand what it is. Again, if you know what it is, head to the comment section and do put out your views on there. We can have a conversation there as well. But to tell you about this domain itself, let us start with a quick did you know. Now, deep learning is such a fascinating concept that I was, many years ago when I started my career, and even before me starting my career when I was still studying, this concept came to be told to me by one of my professors, where I had to research about it and put out a thesis on deep learning. Now, in that particular case, I did a lot of research, and this domain was so fascinating that ever since way back during the college days till now, I have been hooked onto this domain. It's my favorite domain in the case of in the case of data science, which of course again a lot of people agree with me. It's the gateway to artificial intelligence and all of that, right? So I'm sure you guys will appreciate this as much as me, right, guys? So the first point that we have to discuss is this is a concept. Deep learning is a concept where I told you that we're going to get towards artificial intelligence, right? What I mean by that is actually that we're going to take machines, train them in a way where their thinking, their behavior, and the output that they give when we furnish it with an input is going to be very similar to what a human being would do. Now, to do that, it takes this kind of a human-like thinking approach which you have to impart to your machine. Now, me and everyone else who are watching this video, right, human beings, and of course all the algorithms and all the artificial intelligence models in the back end of the video platforms that you're watching this as well, you have to realize that as human beings, we have billions of neurons which are like supercomputers on their own, and there is a connected network in between all of these neurons which make us the being that we are, right? Our conscious is the experience that we are living in. Now, to take these power of billions and billions of neurons and to make your computer understand it, which at the end of the day your computer can only understand zeros and ones to its fundamental level, as I've been explaining, it is a very tough challenge. But these days, with the amount of data that we have, with the immense amount of algorithms and computing power, we can combine all of this together and make sure that our machines can behave as humanly as possible, right? So that is one thing you're supposed to know. The second thing is deep learning is used literally everywhere around you, even though you might, not be aware of it. If you're watching, a video on an online platform, there is a lot of AI related models working there. Are you using social media? I'm sure, all of you, if not most of you, would be using one form of social media or the other. Well, deep learning algorithms are at play there, even though you wouldn't recognize it at first. And then it is not only this, right? It is as simple as you looking at your mobile phone, asking the Google Assistant, asking Siri, asking Alexa, Cortana, whatever are the new personal assistants we have in today's world, right? You are literally talking to your computer and your computer is talking back to you in a human voice. How amazing is that, right? That is what deep learning is all about. The output of this, the applications of it, as you're going to see, we will discuss, is extremely trending right now. There was a time when people thought, hey, you know what, you cannot have your mobile talk to you or order a pizza for you as well automatically without you having to do anything. Now all of that are a piece of cake. It can be done very easily, right? So when people said it couldn't be done, all the way to now that, hey, it's not really a tough thing, it can be done easily, the world has grown a lot in terms of how we can repurpose deep learning for other use cases as well, guys. So it's an extremely trending concept, and if you are proficient in this, your foundation as a person who's looking to become an expert in data science will be strengthened a lot. So I suggest you pay a good amount of attention to understand deep learning. So with that, you should have a question saying, okay, what exactly is deep learning, right? Deep learning is one of these subsets of artificial intelligence. Now, artificial intelligence is an application of data science, right? It's a domain in which we use this subdomain or the subset to get us to a solution. Right now, in AI itself as a subdomain, inside it we have machine learning and deep learning. Now, machine learning is a simpler version of deep learning, but the differences don't end there. We are going to discuss about it because the working is extremely different in these both cases. But as of now, you have to understand that deep learning is a way that we train our machines so that they become self-sufficient on their own in terms of learning and giving us a result which is almost human-like. Now, I cannot say 100% human-like, because if that was the case, then it would be very difficult for us to differentiate between a machine and a human being, right? We haven't gone to that extent yet, but we are getting really, really close to that point. Now, way back in the day, there was a test conducted called as the Turing test. It was named after the very famous mathematician Alan Turing, where he says that a machine can pass the Turing test if it can convince a person that the responses it gives is as human-like as possible. So the person on the other side of the test, if he or she cannot differentiate between the result given by a human being and the result furnished by an artificial intelligence algorithms, that is when that model or whatever is the entity in discussion has cleared the Turing test. Way back from the 60s until now, it has been an amazing feat that we are trying to get to teach machines to do it. It is not a new concept. It is not something that was born yesterday and that it is exploding right now. It is a very old concept, just that we did not have ample amount of computing performance to go on to process it then. But now that we do, it's going to be an amazing thing of how personally we can sit and teach the machines of how they can think on their own, how they can build logic on their own. We are logical beings, but the computers also have logic, yes and no, 1 and 0, multiple states, continuous values, discrete values. It is just that your computer does not understand and process emotions, nor does it have this complex network that is wired by itself, right? Of course, we are a product of evolution, and we are developing the computer to make sure that it can evolve into something better as well. So that's an important thing that you guys should know about. Now, deep learning is a name which comes from the fact that we actually use several layers of processing. Now, when we say deep, it means you have to go through a process, you have to go through multiple things to get to the depth of things, right? So your algorithm is going to touch the depths of what it can do, hence the name. Multiple layers on layers. It's called as a neural network. We're going to be discussing in depth about it in the next module as well, but for now you need to have an understanding of the domain itself. So this kind of a way of learning where we use multiple layers of learning at the end of the day to give us a fantastic product which is very, very powerful and is amazing to use, right? That is deep learning on a whole, ladies and gentlemen. So as I've been mentioning right now, for a while, right? So it is an important thing you have to understand that we are trying to imitate human intelligence here. We humans are very, very, very intelligent compared to our computers right at this moment. Even though you might say, okay, there's the world's fastest supercomputer that can, compute things faster than a human being. I will agree to all of that. There was a time when, Shakuntala Devi, the person who was called as the fastest, the human computer, the human calculator, right? At the end of the day, we set new benchmarks which our machines themselves beat. Nowadays, of course, when you look at programming power and the processing of computers, it is definitely a lot more than what it was in the past, because even if you go back to the time when the humans landed on the moon, right? When NASA put humans on the moon, the processing power of the computer had somewhere around 0.001 MB of RAM. 0.001 MB. That's it. It's not even 1 megabyte. Today, the phone that I use, the laptop that I use, and of course, the machine that I use to work on are powered with a maximum of somewhere around 64 gigabytes worth of random access memory RAM. 64 gigabytes, right? Now, where is 0.001 MB and where is 64 gigabytes? Look at how much the world has progressed, right? Now is the right time to teach our machines and to make sure they understand everything there is to know about what makes us intelligent, right? Now, there are many things you have to consider when you are trying to get your machine to imitate human intelligence. First of all, it is our programming which goes on to teaching these machines, right? Now, usually a question comes into picture whenever we talk about deep learning and artificial intelligence is that can machines learn on their own, get more stronger than the humankind and, sort of attack us and all of that, like how it happens in these amazing movies that we have watched in the past, right? The thing is, as I told you, your deep learning model, your machine learning model, your artificial intelligence solution at this point of time is only as good as the programmer himself or herself. So at the end of the day, if you are amazing at your programming skills, it means that you are, your program at the end of the day or your model is working efficiently. So it cannot surpass your intelligence. Of course, there has been cases where cryptic texts have been passed through which we do not understand as humans, and we perceive it as something like, okay, so the machines are talking to themselves, something is going on. It can be a fact which can be debatable, but of course that's a different discussion. But for now, you have to understand that one particular thing, that your program is as good as you, right? One important place where we can imitate, get the machines to imitate human intelligence well is pattern recognition. Everything you look around you is a pattern, and that is what builds your conscious experience, right? Now, I am looking into my camera to, sort of teach you guys on this. You are looking to your phone or your laptop or your TV or wherever it is that you are learning on. That is an experience, right? So there are certain patterns you know where to look at when you're learning. It's not like you're randomly staring at the wall and, learning, right? You know what pattern you're supposed to know. You know what a square looks like. You know what a circle looks like, even to its most foundational level. That is the important thing here in discussion, ladies and gentlemen. And the fourth point, right? So in the case of deep learning itself, we take a little bit of machine learning, we complexify it. What is the word? We complicate it and we apply so many different transformations to the existing machine learning solutions in a way where it becomes way, way, way more powerful than it already is. And that gives rise to and brings us one step closer to artificial intelligence, right? So using very complex machine learning concepts are an important thing here in deep learning as well, guys. So I hope this section was clear for all of you all. Now, let us actually talk about why we even require deep learning, right? Now, Why we require deep learning is a question when asked to me, I can probably give you an answer hours and hours together to tell you why it is required. But we can have a detailed discussion on the application of deep learning sometime else. But for now, to give you the highlights of all of these very, very important points, the first thing is we are generating an immense amount of data. You already know this, right? The world puts out somewhere around 25-26 lakh terabytes of data every single day. To handle this data, which is just adding on every single day, and to make sure that the data is available for further use and processing, we require more intelligence. See, manually, if you have to sift through maybe 10 lakh files which are full of data, physical files with papers in it, it becomes tough, right? You can take days, you can take weeks or months. A deep learning algorithm can do it like this, and maybe at the end of 5 or 10 minutes or maybe 1 hour, it has ran through 10 lakh documents and it knows what the documents are all about, right? Where is 10 minutes? Where is 1 month of hard work? That is an important thing you have to note. The second thing is that we are living in a world where autonomous systems are guiding us, right? Everything, from the most simple thing, you might have an aqua guard or whatever is your water purification system, right? If you're wasting water, it usually shuts off the power supply, your camera, the CCTV system at your home, it can detect movement and it can take photos as and when people sort of move through in case you have authorized it to do so. And planes have their own autopilot systems. Defense systems use a lot of drones and unmanned aerial vehicles, or UAVs as they are called, right? Things have become intelligent in a way where you really don't need as much human care, as much piloting, not only in the case of aircrafting but of course in other domains as well, to make sure that the job is done. There was a time when, of course, we're still living in that time where you have to drive your own car. But now we have come to a point, I'm sure all of you all watching this video already know that the systems we have, there are certain companies like Tesla, Google, and now even apparently Apple is developing a car, which I'm not sure of, is a fact that you should know that only thing that is stopping us to have complete autonomous driving is the law. Apart from that, the systems are here, they are ready to go on to do the driving for you. There was a time when cars would just back out of parking lots automatically for you, but now they can automatically take you from one destination to the other destination, do everything that you want to do. You can talk to your car. It is very, very intelligent these days, right? In this case, in the case of defense, for in the case of having robots to do a lot of tasks where human life is on the line, it's a very important thing. The third thing we have to discuss is how you can make use of large amounts of data to drive a good amount of information, right? Just the example that I gave you with the physical example of the files is exactly my point here in the third point. The fourth thing we have to discuss, which is very important, is how we can use iterative learning. Now, see, iterative learning is something that even we as human beings use. It is not a new thing for us. When you were in school, when you were in college, or even every day when you're learning something, right? Maybe you're learning to play badminton, or you're learning to code, or even you're watching this data science video to become, knowledgeable about the domain, right? If you just watch it once, yes, there's a good chance you can pick up all of the different things, but you can get more clarity if you do it 2 times, 3 times, right? You will not become a professional or an Olympic gold medalist the first time you probably play a sport. You have to give your time and effort to learn, to train, do the same thing again and again and again, that you remove all your mistakes and become efficient at what you do, right? That is iterative learning. Your computers also do the same thing. In the case of machine learning, again, in the case of deep learning, a common data set, your machine just runs through the data set, keeps learning. With every time it learns, there is some new insight that it picks up. It understands something new, something more than what it previously learned. Of course, in not in all the cases that it just keeps happening that if you train for an indefinite amount of time that your machines will keep learning. No, there goes until a point where it can learn new things. That is the key point in discussion of why we require deep learning, guys. The next 3 points that we have to discuss talks about how immensely popular it is in all the domains, right? Self-driving cars, personal assistants, home security on your phones, social media, the TV shows that you watch, the music that you listen, the computers that you use, the search engines that take in the search entity element that you put on, Guys, again, as I told you, it is literally there everywhere. It is just that you have to find out. If you're ever confused about where deep learning is used in a certain domain that you think, quickly Google it out. If you're thinking about, hey, can deep learning work in finance departments? Can it work in the case of law? Can it work in the departments, or can it work in the domain of anything else which is not directly related to computer science, maybe arts, right? There is deep learning there. Trust me, there is. You just have to search and then you will find a ton of results, right? Now, the second point here, or the fifth point in discussion, a very important thing you have to understand is that we are a being where we want our lives to be more and more convenient, right? Now, we can also talk to our computers with zeros and ones, but we have to just type millions of zeros an hour or a day, which is not convenient for us to talk. So we want to use Windows, we want to use other operating systems like Mac OS, whatnot. It has to be as simple as possible. It has to be snappy. It has to make working fun for us, right? So we want convenience everywhere we go. Right now, I have a fan which is swirling some air in the room as well. So even that is convenience. We have a roof over our head, convenience. Nowadays, everything is talking about how you can make your phones convenient, right? There was a time in the past where if you held a brick and if you held a phone, it weighed the same thing. Nowadays, a phone is a pretty tiny thing which can fit at the palm of your hand. It can be a watch. Watches these days are millions, if not billions of times faster than the entire spacecraft that took humans to the moon, right? That's a fact. That is how amazing we have come through. So contributing to add more and more convenience to our lives is why people want to look towards these solutions, guys. It adds so much value for us, right? Now, deep learning is used in a lot of different places, which we are going to discuss in the applications section. But understand this, it is very, very popular for the usage of face recognition. As I told you, security assistance, parking assistance, and all of these are extensively used. Even though you might not be the person who is actively using all of these, but everywhere across the globe there's millions and millions of solutions which are powered by deep learning. That is what makes this domain fantastic to talk about. The next thing we're going to check out is the applications of deep learning. So guys, as we have discussed, there are numerous applications of deep learning, but let us check out some of the most popular ones. First one, which you might not know of, is real-time behavior analysis. Now, it is a fantastic thing to know about and understand if you're a person who is selling a product, right? Now, let's consider the case of fidget spinners, right? They became extremely popular. People who are young, people who are old, everyone wanted to play with a fidget spinner, and of course, I myself had one as well. To understand about, if you are a person who was selling something like that, people will definitely talk about your product on social media, right? They're going to give you their views saying how good is it, how bad is it, if they liked it, did not like it, all of that. So there is a sentiment which goes into what they type, and computers today, your models in the domain of sentiment analysis, which can read a message and understand if the person is angry, happy, sad, all of these emotions which we understand, right? We can train a machine to understand them as well, cross-reference it with data that exists to see what your what your customers are talking about the product. Now, 3 guys might be happy about it, 4 guys might be really unhappy, they're suggesting changes and all of that. So you can use that feedback to positively have a difference on the life of your product, right? Maybe they're giving you important feedback which you can use to further develop your product, right? So this can happen even in real time, as and when people maybe take on to social media platforms like Twitter or something and they're putting their views on it. You can have a deep learning model here to analyze, assess everything in real time and to give you a score saying, are people generally happy with my product or are they sad? That is an important thing in terms of real-time behavior analysis. The second thing that we are going to discuss are symptom-based disease prediction, right? I am not sure if you know this, but medicine has really come a long way since the past, and now with the world of computing and medicine, it has come together in a way where doctors sitting on the other side of the world can monitor your parameters, they can suggest changes for you, and maybe look at your whatever symptoms that you might have, and then give you a medicine right from where where they are across the world, right? Guess what? Of course, full credit goes to doctors because they are the experts in this domain, but computers are slowly catching up in a way where they can sort of look at symptoms, analyze what disease you might have, and eventually give you, a prediction saying, hey, this person might have this kind of a disease. It might be something very, very specific, very generic, like a common cold or a flu or whatever it is, right? So it has come a long way where I'm not saying that it will replace doctors, but it can assist doctors for sure to help provide a better solution. Right now, if there is something which helps the field of healthcare, I am very sure that the doctors are going to take a positive note about it. There will be time spent, millions of hours on research on it before it has been put to usage in a human life critical situation. But yes, it is possible. That is the important thing that you're supposed to know. The third thing is autonomous car functions, right? Now, I am a huge fan of this and I cannot wait for these autonomous cars to hit India, where, I definitely want to drive around in one of those in a way where, of course, even though it sounds very funny, like, how can you drive, how can you sit confidently if your car is driving for you? But the technology that goes into it, the immense amount of processing and the way these cars learn to drive on their own, the autonomous aspect of it is something I absolutely love, right? You can check out multiple videos online of how cars can drive people around. It's already there in multiple different countries. These cars are there, they're on the road, they're already being used. Think about Tesla, right? Tesla is very popular for putting out these cars which come with a feature called as the autopilot. The autopilot can take you from one destination to another automatically. It can brake, it can turn, it can change lanes, it can do a lot of different things, right? Coming to the fourth point. The fourth point talks about data center security. As we discussed in a previous module, that if you are storing your data online or if it's in a database or wherever it is, there is always a risk that someone might have access to it, someone might misuse it, right? In the case, if you're storing your data with a reliable data professional, maybe think about Google's data centers, Amazon, Microsoft, all of these, their data centers are guarded in a way where, there is impossible access for you to go on to even touch the servers that are there which hold your data, completely barring you from physical access. First of all, is the first way to defend against any sort of miscreants or misuse of your data, right? That is an important thing. These 15, 16, 17, 20 layers worth of security that you have to clear to even go close to the server is all in a human way. But nowadays it is becoming autonomous to a fact that, we can have a computer do this job of screening a person, seeing if he or she has authorized access to have, that kind of a security clearance, move ahead and all of that. It is very intelligent, it is fail safe, and it is being developed in a way where it is doing a fantastic job in this domain. That is data center security. The next thing we're going to talk about is the server optimization itself, right? See, manually we have come up with methodologies of how we can store your data on a hard drive and in a server architecture. But nowadays we use deep learning algorithms to make sure it is effectively stored based upon their usage. Maybe there is some data which you're going to store which you might not touch for the next 6 or 8 months, and your deep learning algorithm already knows this. It has learned the fact that you might not touch that data, so it will store it in a place which would not require immediate access to it. It understands that it is on the back burner and all of that, but there can be some data which you need on a daily basis which can actively store on a faster hard drive or a SSD or whatever it is, right? So moving these data around based on your usage, I'm not talking about 1 MB, 2 MB, 1 terabyte. This is thousands and thousands of terabytes every day, right? So this deep learning algorithm will run through the data, understand what it is, understand how you're using it, and then store it in a way where if required immediate access, of course you'll get it, but it knows how to store it effectively. That is the important talk about server optimization. Considering we are putting out millions and millions of terabytes out every single month, it becomes very vital, guys, right? The next application is self-driving cars. As I told you, self-driving cars are already in use today, but to go on to teach a car to drive on its own, it has to have, first of all, a ton of sensors which it can use to get a sense of the environment around them, right? So we have a lot of senses. We can see, we can hear, we can smell, we can touch, we feel pain. All of these things are sensory things which tell our brain that hey, there is an activity that is going on. But for a car to do all of this, for it to sense that someone is crossing the road, to know that it has to go in that, and it has to have some sort of image recognition to understand that it has to go on the road and not on the footpath, right? So there is a ton of sensors and processing which goes on in a very, very important way. As I told you, aircraft these days can be controlled from thousands and thousands of kilometers away. So there, a person sitting in his room can actually control an actual aircraft. This is usually very popular in the defense domain, but it is also trickling down to the commercial airspace domain as well. So in that particular case, again, another beautiful application, right? So in the entire automobile market, if you see that every day, it is not just Tesla, it is not just Google or Apple, it is just that everyone is looking towards coming one step closer to driving a better user experience, to giving you a sense that your car is more and more intelligent, right? Again, they're doing all of that by making use of deep learning itself. And if you look at cars these days, it will give you a personalized feel. As soon as you get into your car, you will realize that even though it is a commercially mass-produced car, that it feels very close to you. It understands you, it talks to you, it welcomes you, it sets your seat, your temperature, your steering height, everything, right? Maybe even your suspension preferences if you're a person who likes to drive really quick, of course safe at the same time, or if you're a person who likes a slow comfort drive, it can pick music automatically for you. It can turn the wipers on and headlights on depending on rain and outdoor lighting. Guys, the amount of personalization that can bring together a lifeless entity and give it this kind of a human emotion, that is an important thing you have to know here, guys. And the next thing, right, the last couple of applications we're going to discuss in deep learning talks about recommendation systems. Recommendation systems are absolutely amazing. I am a huge fan of this particular domain because we sort of use it almost every day, right? Think about Amazon. Let me give you an example. On Amazon, let's say there is a flash sale or whatever they keep doing where they're trying to sell products. You get a phone, you put it in your cart. Before you check out, there is usually a pop-up or something on the bottom side that says, hey, people who bought this phone also bought XYZ, maybe a tempered glass, maybe a case or something like that, which adds value to your original purchase, right? That recommendation, product recommendation, comes from the fact that the website or whatever it is that is displaying information on the Amazon's page is intelligent enough to understand that when people buy that item, a phone, they also buy a tempered glass or maybe a case, right? That is product recommendation. And you might think, okay, but I usually take one product, I buy it, I check out and I'm done. What is even the meaning or the validity of having a product purchase recommendation? You know that probably the co-founder of Amazon or Amazon itself as a business is grossing at number 1 or number 2 spot in the entire world, which is worth trillions of dollars, right? Now, Amazon themselves have said that 35% of their revenue that they sell on their website comes from product recommendation, guys. 35%, where a business is worth trillions. Of course, trillions, all the trillions are not on the Amazon sales thing, but think about it. It is still a huge number. 35% of a huge number is huge in itself, right? So it is adding a lot of value to, a lot of e-commerce sites. Amazon is just one name that I'm taking up here. Think about Walmart, think about Best Buy, think about all of these guys who are trying to catch up and use as much computing power as they can to solve problems. That is the discussion here. The second thing is Netflix. Oh my god, Netflix uses a highly complex recommendation systems, which is making sure that you stay on their platform, you watch nice content, right? Just a few minutes back, I just told you about how personalization makes you feel nicer, right? Netflix is a platform where their goal is to make sure you watch more and more content. To do that, they go to extreme measures which are beautiful, at least for a person who's looking at it as a developer. Now, you might have a favorite actor, right? Maybe your favorite actor is Tom Cruise. Now, if you are a person who loves Tom Cruise, if you watched 1 or 2 movies of Tom Cruise on Netflix, It understands that you have a favorite. It knows, it has learned that this user watches a lot of Tom Cruise content. So what it does is, even if Tom Cruise is on another movie where he might be a supporting actor, he might have done a cameo, or he's just on the screen for a few seconds, the Netflix recommendation system is so intelligent that it can change the thumbnail of the entire picture, put Tom Cruise on it to make sure you click on it and watch it. That is how amazing it is. Changing these thumbnails based upon your favorite actors, making you want to click on it and watch it. That is intelligence, in my opinion, right? Of course, it's a good thing. It is giving you personalization. It wants to show you what you like, right? That's an amazing thing. The next thing is, maybe after you're done watching a movie or done watching a TV show, for a second you might have a crisis saying, okay, so this TV show is done, what do I do? But right the next second after the credits or the thing ends, it will start recommending you new TV shows and movies to watch right then. You might have watched a documentary, you might have watched a comedy TV show, whatever it is, right? Or a thriller movie or horror movie in that same domain itself, or using the same actors and the actresses. It will give you a recommendation which would make you want to watch the next thing as well. It is a brilliant thing, Netflix making use of deep learning, in my opinion. The third thing is Spotify. Of course, Spotify is one of these music streaming services which, again, I use a lot personally. So based upon the songs that you listen, it can automatically create a playlist for you, arrange them in the order of your liking based on how many times you've played it. Not only that, it will create playlists on its own, looking at the genres of music that you have listened to, what type of music, are they sad songs, happy songs, what emotions are evoked in you. It cannot be 100% accurate, right? So even a happy song can make me sad if that is the case, if it brings back a different memory. But it tries to a certain level to make sure that whatever it is that you're going through, your emotion, that there is a song that can be catered to it to soothe your emotions. That is a beautiful thing that these guys are doing as well. So be it Amazon, Netflix, Spotify, or millions of others who are using it, everyone every day is getting one step closer to making our computers and machines that much closer to us and giving us an amazing experience, right? Amazing. Now, in the next section, we are going to take a look at the prerequisites that are required for you guys to learn deep learning itself. So there's many prerequisites you're going to require for deep learning, but I'm going to give you the highlights of it and the importance of it. The first thing you're going to require is mathematics. The concepts of statistics, concepts of probability, concepts of calculus and linear algebra are extremely important. Mathematics govern these algorithms. These algorithms are used to teach the model. Data plus algorithms gives your model a purpose to use, and that model is used to solve a problem. You see that change that I just built right now? That is why you require mathematics. If you remove mathematics from it, your algorithms are no more intelligent. Your model does not understand what data it is seeing. At the end of the day, your goal is not being met at all. So what is the purpose, right? So mathematics is foundational for this learning, guys. The second thing you're going to require is programming. Of course, you might have seen, we have discussed a lot of things practically at this point of time. So programming is something which you are going to require. You require proficiency in Python or languages such as C, C++, R programming language if you're looking towards deep learning and data analysis and all of those. But yes, the point here being that you require a programming language. First of all, ladies and gentlemen, this is how you teach your machines. Your machines are as good as you and your program, right? So you effectively typing out the best logic, the most powerful logic, using the maximum amount of computing resources allocated is human intelligence, right? That is a point to be discussed here. The third thing is, today's world is very intelligent in a way where we use a lot of cloud computing technologies, right? Be it Amazon's web services, be it Microsoft Azure, Google Cloud Platform. We use a lot of different things. We have used GCP to a point where we have shown you all the demos on Google Colab, right? It's a free and an open source Jupyter notebook. Where do you think the processing power for that is coming from? It is coming from the Google Cloud Platform itself, right? So you have to know that you can use a lot of deep learning, develop systems right there, cater to custom audiences, provide customized solutions. even in the domain, you even using a computer which is probably sitting 10,000 kilometers away from you in a very well protected data centers, or Microsoft has gone on to put data centers even in the ocean as well, is what I've read. So yes, so you are talking to a computer which is underwater. How cool is that, right? So it's an important thing that you're supposed to know, and these three things form to be the most important knowledge, guys. If you have mathematics, you can understand the data yourself, you can drive statistical insights out of it, and your algorithms can use it to learn. If you know programming, you can develop and put out these algorithms in a way where it uses data to train and learn and understand something. After programming, if you have an output which is working really well, you can take it to the cloud computing platform and give it out to the world to actually solve the problem, right? You might be catering to a client who's sitting very far away or right next to you. It is possible to use the computing power, the resources, and whatever it is that you require to drive that solution. You might require maybe 150, 300 computers, very powerful computers to do it. You might not be able to afford buying all of these at once. Well, you do not have to buy them anymore. With cloud computing, you can just pay as you go, use as many computers as you want to drive that solution to see if it is worth. Maybe at the end of the day, you might actually buy it. But to get to that point, it is highly convenient, right? So if you buy 300 computers, it is not just you paying money, bringing it to your office and sitting. You have to cool them down adequately. Heat kills electronics. You have to maintain them. You have to make sure that all these softwares are upgraded. Everything. It's a huge headache to do things offline. And now that is the reason why people just prefer cloud, guys. That is among I just gave you 5 or 10 reasons among probably hundreds of reasons of why people want to prefer cloud computing. So in the domain of data science as well, there is an amazing scope for that. So coming to a little bit of technicality of how the domain of deep learning itself works, right? How do you guys think deep learning works? Now, I've been giving you clues all until this point of time, but let me divulge it to you. The first thing is deep learning works based on iterative learning, guys. Iterative learning, as I've already mentioned, is how we humans learn as well. And the goal of deep learning is to make sure machines can learn like humans, right? So that is how we are teaching the machines as well. It sees a picture of a cat, it sees a picture of a dog, and if it's the first picture it sees and if it doesn't know what it's seeing, it'll be like, meh. The moment you start training it, showing it 100 if not 1,000 images of a cat and a dog and say, hey, all of these are cats, all of these are dogs, please learn it, and eventually you create a model that does it, at the end of it, it can say, oh, okay, so now I understand that this is not the only cat in the world that exists. Even if I see another image of a cat, I can understand it's a cat. If it sees another image of a dog, it knows it's a dog, right? Even in these motion sensor things that happen, maybe people, nowadays it's very common that due to the COVID-19 restrictions, you have to maintain a minimum distance between two people, right? 6 feet or whatever the distance is as per your country's guideline. There are machine learning models, and of course nowadays machine learning for image processing is slightly coming down because deep learning is way more powerful in that domain, where these deep learning models can assess if you have given that extra gap, if people are wearing the masks or not, right? The pandemic is not yet ended at the moment we are recording this particular video, so it becomes very vital to use technologies to make sure people are kept safe, right? So that is one thing. We make sure it trains and understands, and then it can provide beautiful solutions for us like this. The next thing is iterative learning is one part of it. The second part of it is hierarchical learning. It learns one thing, understands it completely. It uses that learning itself to build upon the next thing. It uses previous learning to go up and up and up. And at the end of the day, this kind of a hierarchical given with iterative learning methodologies makes it extremely intelligent and brings it pretty close to human level intelligence. That is our goal, and these are the things that are taking it there, right? That answers the question of how the domain works itself. One important thing is that in the case of deep learning, in 99% of the cases, the more the data the machine has access to, it keeps learning. It understands data better the more it does one thing again and again. So with every different level, it picks up new data. It knows something about the data than the previous iteration, guys. That is an important fact that you guys should know about. Let me give you an example to give you more clarity about how deep learning works, right? Think about this personal assistant, Alexa. Now, as soon as I say Alexa, of course, my phone wants to light up, and I have numerous products in my home which uses Alexa itself. So in that particular case, this is a personal assistant that can do everything. If I say, hey Alexa, turn the light on, it can turn the light on. If I say, hey Alexa, play this music, or turn on my home theater, whatever it is, it can keep everything ready. It can set the temperature on my air conditioner, open the door for me, and well, it can do a lot of different things. It can water my plants, right? There's so many things that I personally use this personal assistant Alexa for. So how does it learn? How does it understand? So we feed it with data. We say, hey, this is the requirement, this is what you're supposed to learn, and it knows a lot of different things. It knows the differentiation between when I'm speaking, it has to understand intonation, it has to understand that I am talking to that particular entity, it has to know inundations, right? For example, there might be certain commands that I give to Alexa which she'll follow only if I say it, not everyone else, right? She has to figure out that it is my voice that is coming, and once it figures out that it is my voice, the next thing it has to figure out is the content of my voice, right? All of that, if you just go on in depth and depth and depth, we can discuss so many things, but its basic nature of understanding our grammar, our vocabulary, of course it is not 100% there yet, and I'm sure the team at Alexa or any other personal assistant out there are developing to better their products, but the work is going on. It is intelligent enough in a way where it is fascinating to me at least, and I'm sure you guys can use some of these solutions yours itself. So having a common input, training on the current situation, and giving you a customized response based on this data and input is something that they are aiming for, and Alexa or Siri in fact is doing brilliantly as well, guys. So I absolutely love how deep learning works, and I hope with this now that you guys appreciate deep learning as much as me, right? So you go back to the second where I told you that we humans use billions of neurons to go on to learn things, and it's like a small tiny computer in itself. Well, in the case of deep learning itself, there's a domain called as neural networks where we use neurons as the foundational concept. A lot more detail about this is coming for you guys in the next module. But for now, you have to understand that just like how neurons work in your brain, where it stores certain information, it passes information to the other neuron, it processes it, multiple neurons work together to give a common output and all of that. We're getting our machines to do it for us in a very, very similar way as well. That's the beauty of deep learning, guys. So whenever you're assigned any sort of values into each of these neurons, that is when you have the capability to differentiate, hey, there's neuron number 1, neuron number 2, neuron number 3, and all of that. So they get their own numbers. It's called weights and all of that. We're going to discuss this in detail in the next module, but for now you need to know we have the capability to discern and differentiate between one neuron and the other, guys. So there's multiple ways of how these neurons connect to other neurons around them, how they map things, right? So for example, if you're a person who's learning to play a musical instrument, for example, I am trained on playing the guitar, so my brain's neurons are wired up in a way where it knows how to play a guitar. Basically, since it knows how to play a guitar, I can play the guitar. That is how I hope that made sense for you guys, right? So these neurons connect to each other in a way where they have trained, they have learned, and they have retained that learning of me playing a guitar, right? So based on a lot of things called as transfer functions, node connections, activation functions, and all of these, we get our deep learning model to learn something and hold whatever it has learned in its memory as well. That's a very important thing that is governing the basis of deep learning, guys. So as I mentioned, activation function, right? Now see, whenever you're using multiple neurons, it is mostly the case that you have to find out if a neuron has to fire or not, or has to work or not in its terms. So if it has to do that, and if the data given to the neuron, the number that is assigned to it is a very large number, things can get a little confusing. So we use an activation function. An entity, what it does is it squishes down your value, this value which might be negative 1000 all the way to positive 10 million or whatever it is. It just squishes squishes all of this down to bring it to a range of -1 to 1 or 0 to 1. So in that particular case, if it's 0, it knows that the neuron might not fire. If it's 1, there is a 100% chance the neuron is firing, connecting to another neuron and passing some information to it, right? To see if the neuron has to pass these values or not in its foundational level, we require activation function, guys. So once the activation is done, once the neurons are activated and is passing some values, there is a weight which gets assigned to each of these nodes. Again, we're going to see how activation function works, how these weight works, how they come together to provide a solution in the neural network module. But for now, you need to know that there is an entity called as activation function, and this is how it works, and this is why it works as well, guys. So after understanding activation functions, as I told you, one neuron connects to the other, so data moves in one direction or the other, right? In the case of deep learning as well, that is true. Data can move in the forward or the backward direction in this kind of an entity called as a neural network. When the data moves in the forward direction, it is called as forward propagation. When the data moves from the output towards the input direction in the network, it's called as backward propagation. Each of these has a very, very fantastic meaning. Forward propagation talks about how you can calculate all of these weights first, make sure that your neuron knows what it is supposed to do if it comes to its usage and all of that. The backward propagation talks about what the neuron has learned. It tries to verify it, compare what it has learned with what the output is, if it has learned something and all of that. So forward propagation is like the neural network learning, and backward propagation is like giving the neural network an examination and saying, hey, what have you learned? Right? That is a very simplification of this concept of how deep learning works as well, guys. So with that, I hope you guys are clear, with how deep learning works on a functional level. The next thing that we are going to check out are the differences that exist between deep learning and machine learning. Now, as I mentioned at the start of this module, it becomes vital that you know the differences, even though these two domains sound very similar, deep learning, machine learning, and both of them are the subset of artificial intelligence. There are key differences here that you're supposed to know, guys. So here are some of the differences. We're going to compare each point and see how we can work with that, right? So the first point, the first criteria for our comparison is the data set size. Now, in the case of machine learning, you can get away with training a machine with a smaller amount of data, and you do not require a large amount of data. Of course, a large amount of data will help it learn better, but it is not a compulsory requirement. In the case of deep learning, that is not the case. It really might not work well unless you provide it with a huge amount of data, right? So more the data works better in deep learning. It is a compulsory requirement there, but for machine learning, that is not so. Why is the case? Well, this is a very important thing you're supposed to know, because at the end of the day, how deep learning works itself, right? These interconnected networks means it is very complex, and your data is being processed in a very different way than machine learning. So to give it information, to make sure it understands what it is learning, you require a lot of data. So this complexity of deep learning asks for a bigger data set compared to machine learning, guys. That's an important thing that you should know about. Talking about the second important point here, it is feature engineering. See, what happens in the case of feature engineering is we try to see what column of data has how much amount of impact on the output, right? So in the diabetes example, again, that I've mentioned, maybe two columns of data have a huge impact, like age and blood sugar and all of that. Maybe there is another criteria which we haven't looked at until now, right? Hereditary can be one of those criteria, whatever it is, right? To know that this new feature can have an impact on it, you have to first of all know the feature exists and use it to get to the output. Right? So in machine learning, we have to manually do this. We have to manually say, hey, here's a new column of data. Try to see what impact it has on the output. In the case of deep learning, it is intelligent enough to sort of figure this on its own. So it has the capability on multiple levels of complexity that it can, go on to learn things, understand things, create feature labels, use it to learn, and then provide an output. And all of this is done automatically, ladies and gentlemen. That is the magic of deep learning. And of course, with this, what happens is that, whenever you go on to teach the machine how things work, right, it becomes very easy because it sort of is very quick at learning. It will understand shape, it understands texture, it knows a lot of different features. As soon as it sees a circle, it will not say, hey, this is a square. It knows it is a circle, it knows it is a sphere, right? That is the important thing. Making your machine already intelligent so that you do not have to teach it again and again sort of is the point here. Your machine will know the basics and you just have to train it on advanced things. If I have to break it down to the most simple level, that is why this automatic feature engineering feature that brings us out, that is shining in the case of deep learning, is very important, guys. So the next thing, the next important point that we have to discuss about is the hardware dependencies. In the case of deep learning, of course, in today's world, since we already have sophisticated high-end hardware, deep learning for its process, for its complexity. Now we are the most sophisticated beings out there. That is debatable, of course, but at least in my opinion, sort of, in our perceivable world right now, right? So we are very sophisticated, and nowadays computers are getting sophisticated, as we have discussed. So deep learning uses this kind of, there is a hard requirement of high-powered computers and graphical processing units, GPUs as it's called, along with CPUs for it to learn and understand things. In the case of machine learning, even a complex machine learning algorithm can get away with low-end machines as well. So you do not require state-of-the-art stuff. You do not require the most fancy, most expensive computers to get your application created and done. Right? That can be a make it or break it things for a company who might not be able to afford a huge computer. Right? You have to understand that it is not the fault of the technology, because that is how deep learning works. We are trying to imitate the most intelligent being in our senses right now. So all the mathematical operation which goes on, very, very heavy matrix multiplication operations, high amount of computation rates, that goes on in deep learning is what asks it, saying, hey, to do this, I require high-end hardware and high-end computing technologies, right? So that is an important difference that you guys should know about. And then talking about the next thing is execution time. I think you would have guessed execution time by now, right? First of all, deep learning, whenever you're using it, it requires a lot of time to not only train, but also to give you an output based upon whatever it is learning in, and to furnish a usable output. In the case of deep learning, it might take a day, it might take 10 minutes, all the way until a week, a month, for it to learn and give you a usable output at the end of the day. So what happens here is that I'm going to show you a demo at the end of the next module, the neural network module, where you will see that it takes a comprehensive amount of time to execute, right? We have already discussed machine learning in a previous module. Now you would have seen that as soon as I hit play, it takes 1 second, 2 seconds, boom, the output is ready. That is not the case when you're training a deep learning model, right? You're going to check that out practically in the next module. So it requires, of course, I'm not going to take weeks worth of time to make you guys wait and show you that. I'm going to take a demo which will probably take 10 minutes instead of 2 seconds to go on to do the same thing in the case of machine learning versus deep learning, right? That's the thing. So it is not just the large amount of data that adds to this kind of a large amount of time, but it's also the complexity, the way machines get trained. But I'm sure execution time is something that you guys would have already picked up on, right? Now, to give you an example, think about creating an application where, it takes pictures of people and sort of helps them find whatever clothing they like, right? So I just have a model in front of me. I take a picture of the model. So in the case of machine learning, you have to manually say, hey, this person is looking for a shirt. This person is looking for a hat. This person is looking for maybe shoes, a tie, a bow tie, whatever it is, right? So we have to create these features, and it has to be coded manually and say that is what we want. So learn based upon that. In the case of deep learning, you do not have to do all of that, so you can get it to understand features automatically, get things created automatically, and it will give you a feature at the end of the day saying, would you like a bow tie? Would you like a tie? Right? So it understands that is the requirement that is being asked of it. It learns based upon that and eventually gives you a result. This automatic way of feature extraction and feature generation is something which is, again, it is a constant amount of research that goes into doing it, but it is intelligent enough to give us the output. output at this moment in time, guys. Right, the next thing that we're going to discuss is the important use cases when it comes to deep learning. In the case of image classification, in the case of object identification and face recognition, wherever it is, right? Be it in a very simple usage of maybe Facebook's algorithm where you just put out a picture, it automatically tags your friend for you, all the way to knowing that, hey, this person might be who I thought that I saw maybe in some kind of an investigation, criminal proceedings, civil proceedings, whatever that is, right? So right from something which is very, very vital all the way to social media, which I don't think is an extremely vital part of everyone's life, is where these things are popular. Be it object identification, you show an apple to your computer, and if it sees it, things like Google Lens and all of these things understand what it is seeing. It knows it is seeing an apple. It can see if it's a ripe apple or if it's still a raw, unripe apple. Is it good to eat? If your apple looks maybe black or something, or if it's not edible, you can show your phone the apple and say, can I eat this? And it can be intelligent enough to tell you, hey, it is good for consumption, it is okay for consumption and all of that. So guys, computer vision is a brilliant use case where you're making your computer see things and understand them right hand in hand, right? Multiple airports across the world have used a concept right now with face recognition, where if you're trying to check into the airport to get your plane, to get to board the plane, there was a time when you had to show your passport. Of course, it is still there. You have to show your passport, you have to prove that you're there physically, and you have to go through a lot of procedures to get your plane. Nowadays, the check-in is in a way where you just go look into a camera, the machine on the other side matches your photo with the passport or something, or whatever details that it has. It understands that you have checked in into the airport and that you're waiting to board your plane and all of that, right? Of course, I just simplified that entire process to you, but that is how computer vision is very popular. Now, I've already talked about text and sequential data in the case of speech recognition, in the case of sentiment classification. It is very, very important. When I say Alexa, that when my voice is said, Alexa knows that it has to recognize what I'm saying, why I'm saying it, and all of that. Sentiment classification, I told you, if you're a product seller, you want to analyze the sentiment of your customers, right? In the case of DNA sequence analysis, if you do not know what sequence analysis is, I highly recommend you read it. It is fantastic. We have DNA in our body, right, and our being itself. So it's a very complex term to explain it to you guys, but it is very interesting that you guys check it out after this video as well. The fourth thing is video activity recognition, as I told you, to check if people are wearing masks or not, to make sure that there is minimum distance maintained, to see if someone is intruding at the middle of the night, right? So you cannot have a security system of human beings, maybe, have 10 human beings to guard one building. You can have 10 different cameras. And if this camera captures a motion where a human is walking or something, it can alert people saying, hey, during the time of night when people are not usually expected to whatever office or government building it is, that people are coming there, then it is intelligent enough to understand all of that, guys. Right, coming to the last section of this particular module, where we'll be discussing the top libraries for deep learning. We'll be taking a look at these libraries which are extremely popular for Python, guys. We have 6 amazing open source libraries which I absolutely love to work with. They are TensorFlow, we have Microsoft CNTK. CNTK stands for Cognitive Toolkit, so it's Microsoft's Cognitive Toolkit. We have Cafe, we have a lot of different things. We have Theano, we have Chainer, we have Keras, we have Deep Learning for J, and we have at least 20 amazing deep learning libraries out there, but these are the ones which get used a lot. So I thought it is worth to mention to you guys the top 6 open source libraries for deep learning, right? To talk about the first one, TensorFlow, right? Now, TensorFlow is amongst the world's most used framework for deep learning. It is the most popular in the case of natural language processing, speech recognition, image recognition, and all of these different things. It is a framework which comes with multiple libraries. It is very flexible to work with, and it also provides you tools that you require in the case of machine learning and deep learning to deploy your applications automatically, right? So to build and even handle deployment, TensorFlow offers multiple options to users. And TensorFlow is a framework in which the at the end of the day, the syntax that you use in Python is very easy, as we have been checking out. But even in the case of TensorFlow, that is the same thing as well. Here, using TensorFlow's syntax in Python is sort of very easy. Of course, you require some training to get started, but once you're trained, eventually you will know what your deep learning algorithm is trying to do, guys. That is the point here. So TensorFlow is extremely popular. It is a brainchild of the people at Google. The next thing that we're going to check out is Microsoft's CNTK, or the Cognitive Toolkit. This is Microsoft's offering, of course. It is amazing. It works really, really well whenever we're doing any sort of image recognition or pattern recognition kind of applications. It works with two types of neural networks called as convolutional neural networks and recurrent neural networks. We're going to check out what these are to a good amount of detail on the next module. But for now, you need to know that CNTK supports both of them. And in this concept of deep learning, where things can get really complex even for the programmer, CNTK offers a way in which you can break down complex concepts into simple stuffs, into building blocks, tiny Lego blocks, work with it, and then build upon a complex solution, right? The pyramids of Egypt were not just one rock which was just placed there and people shaped it, right? They brought tiny rocks and eventually put one on top of the other, and then it became a pyramid. That is the approach that people at CNTK sort of take too. Right, then we have Caffe. Caffe is one of these amazing frameworks which will help you to scale up rapidly if that is your requirement. It is built keeping in mind that today you might have a deep learning solution which might, you might be catering to 10 applications. At the end of the day, if you want to build 100, if not thousands of applications, or have one application used by 1,000 customers to give them some sort of personalization, Caffe is the framework that you're supposed to use. It is used with Python in a modular way. It's an amazing user interface. You can work with it in Python, C, C++, and all of these, and it is very, very, very popular to work with one type of neural networks. It's called as the convolutional neural networks, or CNN as short, guys. So Caffe is meant, it's a tool, it's a framework that is built if you are looking towards to scale. Right, guys. The next thing that we're going to discuss is Chainer. Now, Chainer is again another amazing, it's a fantastic framework which is again built if you have dynamism in your head, right? So, not all the things in deep learning cases are static. It keeps learning, it keeps changing things, and you don't have to do the entire thing again, teach it again and again every day to make sure that it knows a new thing or it understands a new thing, right? It perceives a new thing. So in that case, with Chainer, to do all of these things, to make sure that it is a very dynamic, snappy framework to use, it uses a lot of what we call as auto differentiation APIs, and it uses approach using computational graphs. It uses define by run approach. All of these amazing concepts which you guys should learn about if you're very serious about a data science career, right? So you can build amazing neural networks here using high level APIs which are not very difficult to code with, but at the end of the day, a small amount of effort from your side will get you an output which is fantastic, guys. That is what Chainer is all about. Then Keras. Keras is again a very, very popular offering. It is it is basically a framework which runs on top of using TensorFlow as well. It's a tool which has the capability to run on top of TensorFlow and increase its capability. It works both on convolutional neural networks and recurrent neural networks. In the case of how Keras is built, Keras is actually built, the framework itself is built using Python. It works fantastically in the case of Theano, in the case of CNTK, and works really, really well with TensorFlow as well, guys. So if you're a company who is into rapid prototyping and experimentation, right? So maybe you have a concept right now and you don't have a lot of time to take it to a product where you have a short amount of time which you can invest to make sure you can take this prototype, right? So a prototype is this first thing that you create which eventually gets converted into a product. So if you want to rapidly do it, if you want the methodologies, the tools, the techniques which goes into rapid prototyping and experimenting a lot of different things, Keras is something you definitely should be looking at because it provides a very simple API to help you develop new things rapidly. And of course, if there are bugs on the way, which of course as a programmer you're going to see a lot of bugs, it will make sure that you can find out these bugs easily and solve them easily as well, guys. That is the magic of Keras. So right, guys, the next one we're going to check out is deep learning for J. Now we have been talking a lot about Python and all of that, right? So here is a deep learning module which is built upon using Java, guys. So deep learning for J For J sounds, stands for Java. It is basically built using Java. It is meant to be used on the Java virtual machines. So it is again a very, very popular library. Again, all of these frameworks that we have discussed, all of them are open source as well. So even in the case of deep learning for J, it is an open source library. It supports the usage of multiple deep learning algorithms, which you can use for a variety of solutions to cater, for a variety of clients. And it works really, really well with all of these big data solutions like Hadoop, Scala, Spark, and all of these different things. It brings together this architecture of big data, binds it to deep learning, and makes sure that you can have a constant flow of data to work with, use distributed computing, and give out a solution which is very powerful, guys. So guys, with this you have come to the end of this particular module. I hope you guys took away a lot of information from this particular module. Deep learning is very, very important for you guys. In the next module we're going to be checking out neural networks. So neural networks again are a subtopic or a concept of deep learning itself, but that is again an ocean's worth of concepts on its own. You got introduction to neural networks here. We spoke about neurons, activation functions, and all of that, but yes, we have a separate module. We're going to be discussing it in detail and check it out practically as well, guys. So make sure you check out the next module as well. So guys, welcome to module number 10. In module number 10, we're going to be discussing the very important concept of neural networks, as I mentioned in module number 9, right? So deep learning and neural networks go hand in hand, because at the end of the day, most of the things that go on into the working of deep learning come from the foundational aspects and the functional core of neural networks itself, guys. So without further ado, we can actually begin to understand neural networks to a good amount of depth. Now guys, with module number 10, we are going to be covering these important points here. First of all, we need to take a look at the introduction to neural networks, understand it in a more intuitive way, understand why it is called the way it is, why it works the way it is, how it works and all of that, what is the mathematics that powers the concepts of neural networks and all of that. Once you're clear with this, once you understand the foundational aspects of things, we can take a look at the varieties of neural networks that exist. Once you get to know, hey, so these are the types of neural networks, you will have a complete understanding to hone in on, either 1, 2, or 3 or multiple types of neural networks that you would like to work on and eventually get started with it, right? So we're going to be using a popular application. I'm going to be demonstrating all of these practically as well whenever we're taking a look at the working of neural networks, or consider the practical implementation aspect as well, right? So as always, a good amount of theoretical knowledge backed by practical learning is something we've always standing by here at Great Learning, and I'm sure you guys saw that through this full course video. So guys, let us get started with module number 10. Now, whenever the talk is about the introduction to neural networks, right? So guys, everything that we have learned from module number 9, the deep learning aspects of things, why don't you head to the comment section and why don't you put down in the comment section what you think is a neural network, right? It can be a definition, it can be the way you understand neural network, it can be that you might have used it, heard it anywhere, right? So make sure you guys are doing that. Now, to actually talk about a neural network, right? A neural network for me personally is a very, very fascinating concept. At the end of the day, the goal, again, as I've mentioned in module number 9, is to get your machine to think like a human being. And with module number 9, we saw that that is not a simple task, right? So deep learning, first of all, it's machine learning, then comes deep learning. Deep learning consists of neural networks and many other concepts. And this takes us to be on a pathway of where we can go on to use these concepts to achieve artificial intelligence, right? Now, achieving artificial intelligence is one of the products that we look out for in this domain of data science, as I've told you. So it becomes very vital that you know how you can achieve it in the most intuitive, most fun way possible, right? So these concepts of neural networks are amazing to work with. The output they give you is very satisfactory, in my opinion. They give you a high amount of satisfaction at the end of the day. So the time you invest in trying to solve a problem with this, right, you will be very well rewarded at the end. That is what makes you want to learn more and more about these domains and get working with them, guys. Right. Anyway, coming back. Now that we're talking about artificial neural networks, one very important thing that you have to know is that this is a concept. Neural networks is a complete concept which is sort of a direct lift from how the human brain processes things, right? So we have millions of, if not billions and billions of neurons in our brain, and each of them act like a micro computer, mini computer on their own. So these computers are always in conjunction to create a network. That network is what we experience as reality, right? So reality is how we perceive things, and it's not like all of these computers work the same way. There are certain things which is common to our species which work the same way, but at the end of the day, when you look at the thought process of a human being, it can be very, very different from another person, right? And we have 7.5 billion people across the globe, so that is 7.5 billion people with billions of neurons each, right? So this is a web of the world's biggest computer network, is something that I can tell you now. Bringing actual computers into this is going to be something fun and interactive, right? So guys, whenever we take a look at this concept of how neurons talk to each other, right? So one neuron consists of certain data, and as soon as there is a requirement to pass this kind of a data to another one, it gets activated based on it. There is something called as activation that happens, where it sends a small voltage kind of a thing. That's how the whenever there's a brain scan or anything that happens, they realize that that part of the brain is active. So it sends its electrical signal, very mild electrical signal, and one neuron talks to the other, and that is how one part of your brain works whenever you're doing, for example, maybe a motor related activity. You're running, you're walking, you're thinking, you're happy, you're sad, whatever this is, right? So they know what part of the brain does what part of the thing. So even in our case of neural networks, what we do is we make sure that, of course, we will not have billions and billions of neurons here, depending on the application, of course, but we do have multiple neurons in a connected network, where we are going to make sure these neurons are connected to each other in a way. If information is supposed to be passed from one neuron to another, we have a way to say, hey, so this is the neuron that is sending the next neuron some data. Here's the data, who sent it, which neuron sent it, why it is sent can also be tracked if you're looking to backtrack into the neural network architecture. But the most important thing is that we have a verifiable mathematical and computer science way of how we can track this and replicate the human behavior there, guys. So this is a quick introduction to what a neural network is. But when you think about the generic working of what it would look like, what is the mathematical aspect of things, why does a neuron want to pass that information, and all of these things, right? Well, a neuron, in our case, in a neural network, is an entity which consists of weights and inputs. So each neuron is assigned an input, and it is given a weight, and of course it has a bias value with it as well. Now these inputs and random weights get multiplied, and there's a bias value which is basically attached to this. So a multiplied version of your input along with random weights get added with a bias, and this is later pushed into the value. So this is the exact values that we try to push. Of course, in multiple places, most of these values will get edited, which again we're going to cover down the line as well. So whenever you say, hey, a neuron is to pass a value to the next neuron, there is something called as an activation function that it has to go through. So once it goes through an activation function, the model will realize if this neuron is going to add any sort of value to the next one or not in terms of learning, right? So for example, if you are running and your only goal is to run, sometimes you might want to sing, sometimes you might not want to, right? So if you want to sing, there is a neuron in your brain or multiple network of neurons which says, hey, let us sing and run, right? So here as well, so if there is one particular thing in the input or the data that you think is going to have an impact on the output, and the neural network is capable enough to, of course, learn that on its own, it is capable of feature mapping automatically. So in that case, it will turn that neuron on, connect it to the next one, and move on. The way we track, the way we assess and help the neural network train is based on these values of inputs, weights, biases, activation function, and all of these terms, guys. So again, we're going to be revisiting all of these concepts as we move ahead. But now to give you a clarity, so that whenever I'm mentioning these concepts ahead, that you have some clarity, right? Weights. So what are weights? Weights are these concepts where things get multiplied with the input for the neuron, and they get basically sent to the next stages of a neural network. Right now, in that case, you might be wondering, okay, so what is the point of having a weight? Why do we need weight? Right, well, weights are these numbers, numerical measures, which we use later down the line to see if if the model actually learnt anything or not. During the training period, these values get set randomly, and along with the input data, they get pushed forward. Once during this forward motion, the entire neural network learns, we trace back, we run the neural network in the reverse direction. This is a concept called as back propagation, where we try to compare our final value, what was supposed to be obtained, with the data of what the machine used during the training, right? So there again comes the concept of loss function. Loss function is again something we're going to discuss. But our goal is to make sure that the neural network's loss is very less. So when I say loss, what I'm trying to mean is the difference in the accuracy rate of the actual output we were supposed to receive versus what the neural network actually learned. Right. So of course, when we're going through the concept of backpropagation, we revisit each of these weights. We change it based on what it learned on training, what was the predicted outcome, how far away it is based on the predictive outcome as well. Now this is a concept that will eventually add a lot of value, because with this we have a way to optimize, train the network better, and tune it out in a way where it gives us the most accurate value, right? That is why we require the important concept of weights. Now, once you understand what is weights, why we multiply it, what is the use later down the line, and now you should know that weights form to be a very, very, very important concept of it, right? Because without weights, it would become highly difficult to optimize your network, to train it in a way where, things work, and it is backed by data and, mathematics as well. So keeping that in mind, since we are taking a look at mathematics to a good amount of extent, it becomes rightly so that you guys are well versed with the mathematical calculations that happen in a neural network. Now again, be aware that there are hundreds if not thousands of calculations that happen. I have picked up some simple examples here to make sure that you guys are well versed with the concepts, right? So, first of all, let us actually take a simple example to begin working with, to begin understanding about how things work here. So guys, take a look at the example on your screen. We have two input variables, x1 and x2, where x1 has a value of 0.6, x2 has a value of 1.0 or 1. Now, as I told you, inputs get multiplied with weights, right? So we have weights. Let us take a weight 1 to be 0.5, weight 2 to be 0.8, and we have another value called as threshold. Threshold is 1.0. Now, what are all of these values? What are we doing with x1, x2 forms to be the input variables, w1, w2 forms to be the weights, correct? Now, the mathematical aspect of things in a neural network happen in a way where the step one, where you have to transfer data into another neuron, you have to push data ahead, happens with the usage of a transfer function. Now, in the transfer function, as I mentioned, our input value gets multiplied with the weights, right? So x1 into w1, the answer of that gets added with x2 into w2. Now here we have 0.6 into 0.5 added with 1 into 0.8. So this gives us a product 0.3 plus 0.8, which eventually our transfer function's value right now stands at 1.1. Guys, all of the values that you see, x1, x2, w1, w2, threshold, I have put it on the right hand side to make sure that you guys are calculating this alongside as well. Take a note of the formulas that you see. Transfer function is a very important thing. That is how data gets passed on to the network, right? So that is a very important thing. Next guys, after you take a look at the transfer function, step number 2 is how we calculate and compare this output that we just got with the threshold value, guys. So the output that we have, if you remember from our transfer function calculation, is 1.1, correct? what is our threshold value? It is 1. So if we take a difference between 1.1 and 1, it gives us a value of 0.1, right? So this is how we are comparing our output with the threshold itself. But still, what is threshold, right? See, threshold comes into the picture when we talk about the activation function. If your output value, the value that you got, if it is greater than the threshold, right? In our case, output value is definitely by a huge margin greater than our threshold. So in that case, what happens is that the neuron itself gets activated. Right now, if we go back, as you can see, the output is 1.1. What is our threshold? Our threshold is 1. So we have a positive difference, right? Anything, when we compare this, if the output minus threshold is a positive number, it always means that your output is higher than the threshold number, right? So if the output is higher than the threshold function, the neuron gets activated then and there, guys. So this is the fancy concept of, the mathematical calculation in a neural network. I have tried to simplify it as much as possible so that all of you guys, especially beginners who are watching this video, can understand it in its full sense. Right. Now, what happens if your output is less than the threshold, right? If your output is less than the threshold, our comparison value in step number 2 will either be 0 or it's going to be a negative value for sure, right? If it is a negative value, we are trying to say, hey, no, your output is less than threshold. If your output is less than the upper threshold, right? So if this is the output, if it comes very close to threshold, this hand is the threshold, this hand is the output. If it comes very close to it, then you say, okay, let us still activate it, because at the end of the day, this hand is the threshold and this hand is the output, right? So if your output is less than the threshold, your neuron will not get activated. But once your output beats the threshold and it is higher than the threshold, then we say, hey, activate it, push the value next, because whatever you are contributing is going to affect the neural network. That is the simple way of how we can take a look at the mathematical calculations in a neural network, guys. Right. Now with that, you have to know the various types of neural networks that exist. Now there are multiple different types of neural networks, which again, trickles down to what is your requirement, how you want to use it. But at the end of the day, even though there is a long list of types of neural networks, there are certain very, very popular things. They have their own set of advantages and disadvantages, their own set of usage, their own set of working methodologies, which is very popular for certain specific applications as well. So keeping all of this in mind, let us discuss some of the most popular or the important types of neural networks that exist, right? As I told you, there are many, but here are some that we are going to discuss. You have, among the multiple types of neural networks, we have a perceptron. We're going to be discussing feed-forward networks, a multi-layer perceptron, convolutional neural networks, or it's also called as CNNs. Then we're going to talk about the radial basis function neural network. It's also called as the RBF neural network. And of course, then we have the recurrent neural network, which is very popularly called RNN. Now, if you might have done a little bit of research on your own, you might have heard the term thrown around everywhere: CNN, RNN, RBF kernel and all of that, right? So again, these all concepts are something that you're going to get a quick introduction to in this section of module number 10. Right. Without further ado, we can actually jump on to the first one to understand a perceptron. Now, perceptron is the most foundational concept of how a neuron works, because practically in all of its sense, it is the most simple neural models that one can go on to calculate, guys. Because at the working stage of it, at its initial basis of propagating values and becoming a network on its own, a perceptron itself is a simple unit in a neural network, right? So this simple unit, even though it sounds very simple, as you can see, we have two inputs and these two inputs converge into one output cell on the image that you see on your screen right now, right? Even though you just have two inputs and you have one output, do not be taken by the simplicity of things here, because even a perceptron is very well capable enough to detect features and give you computations for that as well. So it accepts inputs, it accepts inputs and weights, and it uses an activation function. All of these concepts we already discussed, right? So it uses these values to push it to the next layer, and eventually, since there's only one layer with the perceptron, the weighted inputs and of course the activation function, depending on it, whatever value gets activated between 1, 2 or multiple neurons, it is just directly pushed to the output and say, hey, this is the output, here's how we have arrived, right? So guys, make sure you're taking a note of the image as well. If you have a pen and paper handy, it is always vital, because these are the functional concepts which will help you down the line in data science a lot. So guys, this is a perceptron. Now to talk about a certain advantage and disadvantage of using a perceptron, right? Now, whenever you're talking about the concepts of electronics in a way where, again, even with computers as well, right, the hardware functionality of it works on multiple logic gates, AND gate, OR gate, NOT gate, and all of these. So we're trying to use these logic gates to say, hey, if these inputs are passed, I want such and such output, right? So in the case of an AND gate, only if both the values are true or same, the output is given to you as a true. If one of these is false, then it's false. But in the case of an OR gate, that is not the case. One out of two values, if it is the opposite, if it is the same, it doesn't matter. If one, this or that is whatever that you require, yes, you will get the output. NOT gate is again a very fancy gate where no matter what you throw at it, it is going to give an inverse of the output. So if you give the NOT gate a logical input of 1, it's going to give you an output of 0. So it is used to invert the signal or invert the concept of whatever you sent into the input, right? So the advantage here with the perceptron is that you can implement all of these in a very, very simple fashion. But it also comes with a small disadvantage, is that whenever you're working with nonlinear functions and whenever you have nonlinear gates, such as the XOR gates, where you have to build applications based upon this, a perceptron will not work, because again, XOR gate comes with its own working, its own truth table, its own challenges to implement. So the concept of perceptron doesn't directly feed into the working of that, is the small disadvantage with the case of a perceptron, guys. Right. Next up, taking a look at the feed-forward neural networks. Feed-forward, what does it mean, and why does it, look a little bit more complicated than the perceptron, right? Of course, perceptron is a very simple entity. Here, it is no longer a simple entity. We have a network where, you can have multiple inputs, layers in the network, and of course it is passed through the output, right? But one very important thing that you have to know about whenever you're learning about feed-forward networks is this is a type of neural network that is extremely popular for face recognition applications, guys. So whenever you want to add filters onto your face, whenever you're using social media, whenever auto tagging is implemented by multiple social media out there, or you're trying to use any sort of computer vision and all of these concepts, right, it becomes very vital that you know what sort of a network is powered the concept in the backend. So a feed-forward network is something like this. Coming to the working of it, as the name itself suggests, a feed-forward network will only feed data in the forward direction. Remember how I told you previously that we even work the network in its backward direction in a concept called as backward propagation, where we try to minimize the loss. In this case, that is not possible because the data moves in only one direction, which is the forward direction, right? Of course, here, even though it is not a perceptron, it means you can have multiple layers out of it. So a multi-layer network is definitely something that is possible. But the working of a feed-forward network itself changes, very much from a conventional neural network, where here we do not require a back propagation itself because the weights are static in nature. Now, with back propagation, you keep changing weights in a way where you have to recompute, change the weights, bring the loss down, all of that. Here, if your weights itself are static, it means down the line the model sees these inputs and these static weights multiplied. So it literally doesn't have to use the concept of back propagation itself, because weights are not random, and even if they are at the first stage of it, they are static. It is one set of numbers that are used which moves ahead, right? So coming to talk about certain advantages of the feed-forward network, one thing is that whenever you're working on it, it is brilliant enough to give you a very good output, which doesn't require a lot of effort from your side. So it is very easy to implement. It is amazing to maintain and keep reusing for multiple solutions out there. To talk about the disadvantage of it, see, the concept of deep learning itself talks about how well versed can you get your machine to learn. If it learns it differently or wrong, it has to have the capability to relearn it, right? In the case of feed-forward network, relearning is the backward propagation aspect which we are not taking a look at. So in all of its sense, if your complete application is a requirement of an output based upon the concepts of deep learning, well, it certainly does not hold true because ability to relearn is sort of lost here, right? So this is feed-forward network. Next up, we're going to take a look at multi-layer perceptron. Now guys, perceptron is something that we checked out. What is a multi-layer perceptron? A multi-layer perceptron is basically a fully connected neural network where you have a certain set of layers called as the input layer, where all of these neurons are there which gets its values. On the most right hand side, as you can see, we have an output value. But between these input and output values, you have certain layers called as the hidden layers, right? So this hidden layer again consists of multiple neurons where each neuron has an effect on what the output is going to be like. So guys, since we already know the basic working of a perceptron, here it is the same thing, but again here the data moves in the backward direction for the neural network to relearn itself, right? An advantage of a multi-layer perceptron is that the weights are automatically adjusted. It can self-adjust in a way depending on the result that is obtained at hand. So that makes it a huge advantage in the working of a multi-layer perceptron with these hidden layers, right? Now, based on the complexity of the solution that you're trying to obtain, you will have multiple hidden layers. It can be 1, 2, 3, it can be hundreds of hidden layers if your model can get that complex as well. So multi-layer perceptron is an extremely trending concept in the world of speech recognition, right? So whenever you're talking to a chatbot, for example, when you say, hey Siri, hey Alexa, when you're talking to these chatbots have to recognize everything in your speech. It has to know that it is you who's talking. It has to understand grammar. It has to understand phonetics. It has to understand so many different things, and it has to give you an output in real time, right? So a multi-layer perceptron is very fancy for these kinds of applications, guys. To talk about advantages and disadvantages, again, each of these neural networks come with their own set of advantages and disadvantages, as you've seen, right? In the case of a multi-layer perceptron, a huge advantage here is that no matter how complex your deep learning problem can get, even though implementation might be slightly tough, you can use it and work with a multi-layer perceptron to eventually get to your goal. That is the advantage. The disadvantage whenever you're talking about a multi-layer perceptron is that execution times are a little bit slow, because what happens is that things here are very complex to implement, right? With the hidden layers, your neurons are interconnected. It is fully connected in a way where one neuron's interaction can completely trickle down until the output layer. So execution becomes a little slow due to the complex nature of the working itself, guys. So this is a multi-layer perceptron. Now, once you've understood about a multi-layer perceptron, we come to a very nice type of neural network, which again, probably a lot of the people in the world use today. It's called as a convolutional neural network. Now, convolutional neural network is extremely popular whenever anything talks about image processing. This was a type of neural network which was built to handle image processing, guys. So imagine it is purpose built for that. So of course it is going to be really good at doing things the way it does, right? So here what happens is that whenever you pass an image into a neural network, it gets converted into an array of pixels. These array of pixels are clubbed together. They get converted into another form. Eventually they get flattened, and these give you a complete output of how things work. You take the inputs, you have multiple hidden layers, and then you have an output layer. So taking your image right from its input, right, you are basically giving your computer an image saying, hey, here is what it is, process it. You're going to take it right from its image form until an output where you're trying to predict maybe what the image is, right? We are going to check out convolutional neural networks practically. So in those steps, I'm going to highlight the mathematical aspect of things. I am going to take a look at and teach you of how things work in each of these layers as well, guys. And of course, when we're implementing all of these practically, you will have a complete knowledge of what we are talking about, right? But for now, you're supposed to know images get broken broken down into pixel, and that is how mathematically data is processed and furnished across the input, hidden layer and the output stages of the neural network. So again, here we make use of a concept called as filters, which we are going to check out in the next section. But for now, you have to know the advantage and the disadvantage that CNNs, are very good at, and of course the things that are bad at as well, right? Now, an important advantage that you have to know about CNNs is that whenever you're training a model to understand images, right, it is actually a very complex thing, as you can see from the demo we're going to be discussing. But to train it, you will not require a lot of parameters. A convolutional neural network is intelligent enough to understand what it is seeing in an image. So your job as a person who's trying to code a neural network is definitely reduced, but the output is still complex. It is an amazing output, but less effort on your side. That is the advantage here, guys. And then whenever you're talking about the disadvantage, right? See, one important disadvantage that you have to know is, even though you're doing a small amount of things and your network itself is using a small amount of parameters to give you an output, at the end of the day, the end design that's going to take you from your problem statement till the solution, right? That is still a little bit of a complex procedure. And whenever you're trying to talk about code maintainability, well, it still poses a slight challenge, guys. Right. Now, the next neural network that we're going to talk about is the radial basis function neural network. It's also called as the RBFNN or RBF neural network. So it means the same thing. So whenever we're talking about the RBF neural network, the radial basis function neural network, right? So it is an amazing neural network, which again, I am a very huge fan of, because here we try to use a priority based problem at hand and use this network to solve it, right? You have multiple inputs where each input gets tracked into an output, and eventually you have a hidden layer, and this layer talks to an output, as you can see from the image on your screen right now. So we take a classification problem at hand, and we try to classify our input at hand with the solution we are supposed to obtain based on how similar the input is to what our model sort of learnt in its training stage, right? So when it's training, of course, it's going to use the training data set. How similar is the input to the training data set? And then that is how we use a concept, again, a mathematical concept called as Euclidean distance. Euclidean distance is this concept we're going to use to say, hey, okay, so if I have an apple or an orange, if I have a priority to say that I have to arrange the oranges first, do I have to arrange the oranges first? And if so, it will do it, right? But to get to that question, do I have to get to the answer of it, right? The concept of Euclidean distance is used. That's a very simple analogy to make sure you guys understand the RBF neural network, right? So, in fact, to give you a clarity of how things work itself, let me give you a very nice example. Now, let's say, there is your local power distribution hub, which provides electricity to your house, right? So there is a transformer or whatever it is, and there's multiple houses that one area's or one locality's power distribution hub gets connected to, right? It's not like each house has a single hub. No. So in this case, let's say there is a power outage in 3 places that you can see. One, as you can see in P1, if you remove the connection at P1, if there is an outage there, everyone at P2, P3 sort of lose their power, right? Even though they might be the same channel, even though they might be the different channel, if you have to prioritize saying, okay, if I remove P1, maybe the person at P2 will lose electricity. But if I if I do not fix P3, right? If I do not fix the electricity going from power plant P3 to houses B, C, D, well, 3 houses are losing electricity. But in the case of P2, there's only 1 house that's losing electricity, right? Again, let us take away all of these critical things, which is fire station, health services, hospitals, and all of that. Let's just consider these to be plain simple houses. So if you look at the problem in a logical way, you will realize that, hey, of course, we need to fix the P3 link first because it has a more impact on more number of houses. 3 houses are waiting for electricity there. So firstly, we're going to fix P3. Then after P3, you're going to say, okay, so now let us go on to fix P2 because there's only 1 house that's affected there. And then you're going to fix the backup line, which is P1, that says, hey, okay, so P3 is ready. The power is gone to the houses B, C, and D. Now P2 is ready. The power has gone to house number A, and then you say, okay, let us have the backups lines ready. In this case, it is P1, right? So this is how you have to prioritize things, right? You don't go on to do it in a random way. You see the impact, you see what is important and solve it based upon that, right? That is exactly what goes on in the working of the RBF neural network as well, guys. Right. So the next type of neural network that we're going to take a look at is the recurrent neural network. Now, recurrent neural network is also called as the RNN or RNNs, as I've told you. And this is an amazing neural network because with this, you can go on to do text classification, text processing, and there are so many different applications of RNNs that it is an amazing thing, guys. Of course, you can take a look at the image on your screen. It says recurrent. It means that something goes on again and again and again, right? So one advantage, one very important thing, even before we talk about the advantages about RNN, is that it has memory. It has the capability to save and hold the output of a layer. So using memory functions, using the concepts of forward propagation, you have the ability to teach the neuron what it is doing and save the output, right? Now, as we've been checking previously, the output of a neuron becomes the input of the next neuron, right? In that case, it has to hold some memory to say, hey, okay, this is the reason in this particular step of learning that this was the value that I have, right? So for that, especially that in the case of usage of text processing is very important, and recurrent neural networks are amazing with this because they are designed keeping text classification and processing in mind, guys. Now, to talk about the advantage and the disadvantage of recurrent neural networks, right? One advantage is that whenever you're trying to model and work with sequential data, right? Whatever it is, text data and all of these things, it does it amazingly well. It is purpose built for this. So if you have a requirement where you have sequential data and you want to process it, think not anymore. Just try to implement a solution with RNN, right? That is, my advice if you're trying to solve a practical problem. The disadvantage though is that training an RNN becomes a little bit of a tedious task because at the end of the day, the working makes it complex enough that first of all, it'll give you a beautiful looking output if things run fine. If it, is struggling to learn things, and if there's a little bit of a confusion about why, things are working the way it is or anything of that sort, to go back and to retrain it to understand what parameter, what memory function is missing things, why, upon more training, sometimes it so happens that more and more you train, your recurrent neural network's accuracy keeps coming down and down. So it is a very important thing that you will not understand about what parameter is having this kind of an effect, guys. So all of those things have to be kept in mind when you take a look at and of course implement a recurrent neural network. Right, guys. With this, I believe that you have to have an understanding of one of these neural networks to a good amount of depth. So we are going to take a look at understanding convolutional neural networks. Let us check out its working. Let us check out each of its layers. And of course, we're going to take a look at all of these things practically as well. Right. Now, as I've already told you, convolutional neural networks, or CNNs as I'm going to be calling it from this point of time, is very, very important for image processing. It is built for image processing, guys. So when you understand the concept of image processing, when you take a look at an image itself, right, as I've already told you, your computer, even though it is the most intelligent thing, it can understand zeros and ones, right? Even an image is a 0 and a 1 to its most functional level, but then usually images get a value which is again a little bit more than 0, a little bit more than 1, 255, 256, 1000, all of those things. We're going to discuss them. But the point is that if you're trying to bring it down to its most functional level and understand what your computer looks at when it understands an image is just numbers, right? So each of these numbers will have a value. It will talk about a shape. It will talk about the brightness. It will talk about the color. Again, I'm talking about the pixel side of things, right? So in the case of a CNN, the simple thing you're supposed to know is whenever you pass an input as an image, right, a JPEG image, a picture that you have clicked, as soon as you go on to give it as an input to your convolutional neural network, the output is going to be either another image or it's going to give you the characteristics of the image that you have put. It can guess the features of an image. It can say, hey, I see all of these things in this image. This image is of a building. This image is of a person. All of these things. Even if you're looking at the most simple steps of classification, classification, right? It is something that is definitely possible to do so in the case of using a convolutional neural network. So as I just mentioned, right, let us say you want to implement the concept of a binary classifier. Binary classifier. So binary talks about two things. Classifier talks about how you can classify these two things, right? You have a picture of a cat and a dog on your screen right now. So, you give the input image as that dog on the left, and your convolutional neural network can run through it, and it can train in a way where it can give you an output saying, hey, I have a 94% probability that the picture that you have shown me is that of a dog. On the right side, it's the same case. You can give it multiple pictures of cats and dogs, and the output it's going to say is, hey, I have a 91% probability that this picture is that of a cat. Now, if your neural network learns it wrong, or if your input is not that of a high quality or even a good amount of quantity that we discussed, right? Think about the section where we discussed machine learning versus deep learning. I told you that the data set has to be huge, right? So if your data set is all right, if your image is accurate, if your data is accurate, it will give you an output like this. It is going to find you and give you the probability, the percentage of detection that it thinks the image is whatever it is seeing, right? On the left, it says 95% I think it's a dog. On the right, it says, hey, I'm sort of 90% sure that this is a cat. But it also says, hey, I might be also thinking that this is a dog, right? It says this is 37% chance that this is also a dog. But of course, we consider the biggest number there where it accurately got it, saying, hey, it's 91% a cat, right? And of course, a lot of people will get curious, saying, okay, so what does it do if you give a picture of a cat and a tiger and all of that? Will it understand what a tiger looks like? Will it understand what a cat dressed up as a tiger looks like? Again, all of these are fun implementations, and I'm going to leave it to you guys after you understand, once we check out all the steps that go on in the learning of convolutional neural networks, right? So this is a basic binary classifier, right? So to again revisit the concept of how we are trying to bring the human aspect of things, human learning aspect of things here, think about the actual neuron and think about the artificial neuron that we are trying to create in our neural network. On the left, you have what goes on in the brain, right? So you have a cell nucleus, which sits in the aspect of a neuron, and that in our case is a node. It is one single node that we saw all those circles, right? It is a single node like that. Then you have a concept called as dendrites. Dendrites are used as points of entry, data entry points. In our case, inputs were x1 and x2, right? It is similar to that. Next, you have a concept called as the synapse. Synapse is how one neuron is connected to multiple different neurons. There is multiple new connections happening in your brain right now that you're learning a new concept in data science. These become the weights, because you don't just look at this and it just gets stored, right? It's not like you only see this slide to know what a convolutional neural network is. Next, when you go on to talk to a friend, you can also talk about multiple other things about convolutional neural networks. So there has to be a layer which gets mapped with a new neuron, right? That's a synapse. Then you have the concept of an axon, where axon talks about the actual process of creating functions, the aspects of mapping, activation functions, learning, and all of that. In your brain, it's the duty of the axon to go on to do all of these things. In our case, we manually implement all of these because our computer is apparently not intelligent enough, right? And the last thing is you have something called as the terminal axon. Terminal axon again corresponds to your output. Each of these axons along with the nucleus dendrites, so it's one entity that we have to separate out in the case of an artificial neuron, right? I hope that concept is clear to you guys. Now, when we're talking about implementing a binary classifier, that is how you guys have learned it in school. In fact, of course, including me as well. We've learned it in school, right? So probably when we are very, very small, when we are infants, our parents used to show us, hey, look, there's a dog. Hey, look, that's a cat. So our brain continuously trained. Neural networks were formed in our head that says, hey, if I look at a cat, it is not only that I have to look at only that cat to know it's a cat, right? I can look at thousands of other cats and say, okay, that's a cat, that's not a cat, that's a dog, that's a parrot, or I don't know what that is, something like that, right? So that is how you would have trained, and that is the approach that we are taking here to again add that human aspect of thinking to our artificial neural network as well, guys. Now, To come to the depths of how a convolutional neural network works, first of all, you give it an image, right? Your input is an image. Now, as you can see, I have pictures of two very cute dogs here. It's one picture, right? Now, when I input this into a convolutional neural network, what happens is that this image gets broken down into pixels. Now, an image is consisting of pixels, right? When you take a look at the resolution of your monitor, it can say 1920 into 1080. It means horizontally it consists of 1080 pixels, horizontally it consists of 1920, that is 1920 pixels, and vertically it consists of 1080 or 1080 pixels, right? This changes. Your phone has a different amount of pixels, your TV, a 4K TV has different things, and 8K resolution TV has a lot more pixels compared to a 1080p TV and all of that, right? So at the end of the day, an image is basically a pixel which consists of certain data. Now, this value that gets broken down to, as you can see, 4, 2, 21, 22, 54, 36, all these numbers that you see, each number has a value on its own. And once an entire image gets mapped into these numbers, there are three different things that we pick up. As you can see, it is an array of 32 cross 32 cross 3. 32 cross 32 is basically how many pixels, right? It has 32 into 32 pixels is how the image gets, the image is basically in the form of its array structure into 3. This 3 is actually called as channel. Now, with the channel, when we say the channel is 1, either the image is black and white or it's in grayscale, where it's either colored or, so in this case, it's either nothing or it is black and white. But in the case of a channel being 3, we have 3 colored channel that goes on, guys. RGB, red, green, blue. So the values of mixings between red, green and blue eventually give you all the colors that you see, right? Of course, in this particular case, that is how we use it to train a convolutional neural network. So what happens is that once you give the input, right, so let's say in our case, we're trying to do a cat and a dog classifier, we give it to the input layer, we give an image. Now, it sees the image and it goes into the convolutional layer first. In the convolutional layer, again, mathematically filters get applied and all of that. We're going to check it out. I'm going to show it to you with an example so you understand it better. After convolutional layer, there is the pooling layer that is next, and after which you have the dense rank layer, where again at the end of the day it gets squished, it gets pulled down into one filtered row, and then you have an output layer. Your input layer is you giving an image. The output layer is it is saying, is that a cat or not, is the question you're asking, and it's going to say, hey, this is the probability that it is a cat or it is not a cat, right? It is a very simple thing that you should know. But my point with this slide, again, we're going to check out all of these layers, is that know the order of the layer. First, we have the input layer, next we have a convolutional layer, next we have a pooling layer on the third thing, on the fourth thing we have a dense layer, and then comes the output layer, right? That is the working of a convolutional neural network in its order, guys. So we just checked out the various layers, right? So here are the actual layers. In the convolution layer, what happens is that the image gets converted into an array. This array, I already showed it to you. And next comes the ReLU layer, or it's also called as a rectified linear unit. Here we try to do one of these concepts called as regularization, where we try to convert all these negative numbers to 0 and to bring it to a certain limit. I'm going to show it to you why we do this, but now you should know that this is what goes on. On the third layer, we have the pooling layer, where again, if you keep doing things to an image, it will drastically transform and become something else. It can get huge, right? So to make sure that your image is not huge and out of bounds, we reduce the input size with a concept called as filters, and we bring your output size very similar to be that of the input size as well. That is what we do in the layer of pooling. And then you have the fully connected layer, where we bring together multiple features and we have an output, or we have a process, we have a model that says, hey, this is a cat, here's the probability of it being a cat or not, right? So let's visualize what each of these layers mean. So the first layer in the CNN is called as the convolution layer, right? So convolution layer is a layer where an image gets converted into an array. It is the first layer of a convolutional network. It takes the image, gives out it understands the pixel values, and it gives out the array output. Right now, each of those numbers you see had a meaning there. If the number was 0, it means that part of the image was very dark. If the number was a huge number, it means there's a lot of light, there's a lot of color, or there's a lot of activity that's happening for that pixel, right? So that is a simple way to take a look at pixels in numbers, and that is what happens in this case as well. So with the convolution layer, our goal is to make sure that we are trying to extract features, we are trying to understand the mathematics, we are trying to understand why pixels are lit up there, what it is trying to convey, what shape is it trying to give us, what is the outline of the image, what is the edge, what is the curves, what is the bounds of the image. So all of this we can understand later if we break the image down into pixels and reduce its dimension, right? That is what we're doing in the convolution layer. So let me show you how it works. So first of all, we send it an image. As you can see, it's a little dark on the left, so there are smaller values here, and of course on the right it gets brighter, so bigger values are here. Then what happens is an image goes on to become a pixelated value. It gets created into an array that looks like this, and then we have something called as a feature detector or a filter that we apply onto it. Now a filter is basically a set of another smaller tiny set of an array that we multiply it with the original array to make sure that we know what it is seeing, right? A filter transforms your input in a way where it teaches the neural network about what it is seeing. Like, is there an edge? Is that a border? Is it dark there? Is it light there? Now I can take a look at it and tell you, hey, this is light and this is dark. But for the network to figure out, we have to multiply it with a feature detector, or what's also called as a filter, and then it gets to it. So once we multiply all of these things, this matrix with this particular filter, here is the output matrix that we get from the convolution layer. So here we're trying to say, hey, I understood certain features from this particular image, and of course you can see that our input is very much bigger in size compared to our output, right? So we are trying to reduce its dimension. So to get to here, what did we do? We took the input was broken down into arrays were multiplied with filters, and once you multiply the entire array with a filter, it's going to give you a smaller set where it understands the features now, right? So that is the convolution layer, right? Next, we have the rectified linear unit layer, where what so happens is that now you might have seen values there which were negative in nature as well, right? So to bring all of these negative numbers to 0, we use the concept of what's called as a half rectifier. Look at the graph on your screen right now. Now, whatever is the negative input that you give, right? It can be -1, -0.1, -1 million, -1 billion. It doesn't matter, it becomes 0 eventually. Whatever is the positive values, of course it's going to remain positive itself. Whatever is negative just gets squished down and becomes 0, right? So f of y, your output becomes 0 no matter what if your input is less than 0, and your f of y remains y. Your positive numbers remain the same whenever y is greater than or equal to 0. Even if it is 0, it is going to remain as 0 itself, guys. So the range of the rectified linear unit function that we use is basically 0 to infinity. No negative numbers in talk whenever we consider the use of rectified linear unit, right? So we're trying to regularize, we're trying to remove these occurrence of negative numbers. Again, you will understand why we have to remove negative numbers, as they have a tumbling or a rolling effect down the line, because a negative number in a real scenario does not make sense, right? Your array value that you saw, the pixel value, if it is 0, it means it is completely dark. If it is -5, there is no meaning to it, right? It is not like a light is being removed from that pixel. It can either be dark black or it can have some value there, right? That is why we require the layer of ReLU. So here again, we added all the, from the previous layer, we got the filters, we multiplied the filter with the input, we have a value. Once you go on to apply the ReLU layer, as you can see that we have one negative value here, which is -2. So what happens when we have any sort of negative values? It gets replaced with 0. What happens to all the positive values? They remain the same, right? So this is the ReLU layer. Next, we take a look at the pooling layer, where we are trying to reduce the size of the image input with multiple filters. Now, we commonly multiplied in the convolution layer with one filter across all the dimensions to give us more detail about the image. But here we are trying to reduce the size of the image itself and to bring down the number of parameters we're trying to use to assess and understand what the image looks like. Now you might have a question saying, okay, so why do we even require the pooling layer, right? See, pooling layer is very, very important to make sure that your model, whenever it's learning something, it does not go into overfitting. Overfitting is a concept where your model looks so deep into your data that it will rather get confused looking at noise rather than useful information. We want to avoid all of these things. That is why we reduce it in a size. We bring down the number of parameters and say, hey, this is what is required, right? So you might have a question saying, okay, so you used a 2x2 filter. Can I use any size? Of course, you can use 3x3, 4x4, 5x5, anything that you require. But the most common way of, or the first prototype aspect of looking at things is to usually use a 2x2 filter there, right? Now to talk about this layer, I have a simple animation here. First of all, our convolution layer is done. Our ReLU layer is done in a way where all the negative numbers are now vanished. We multiplied -2 and we had a 0 here. So our data is ready for it. So now what we're going to do is we're going to multiply this with 2x2 filter, and we have a parameter called as stride. Stride, of course, can be a new terminology to you. So with stride, what we're trying to do is when you have the image and when you have a filter that is being moved across an image, think about it like a torch, moving on each pixel, right? You're going to understand what I mean right now. For example, if stride is 1, I want the image to overlap 1 pixel to the right every time it moves. See, now I apply a filter here, and this filter talks about, it's 2x2 filter, where I have applied filter only on the first, this row and column that you can see on your screen. So upon applying a filter, multiplying it, all of that, I just get one single output here. Now, what happens is when I move it to the right? If stride is 1, it is saying, hey, if I take this box, think of it like a torch. If I move the torch just one array value to the right side, the overlapping comes at 2225, right? So this is stride equal to 1. If stride equal to 2, you can actually go on to move it another point to the right, where instead of it being 22, 0, 25, 87, it's going to be 0, 10, 87, 139, right? So it happens like this. We have stride equal to 1, so one layer on the right gets overlapped. You get one value as a result of the multiplication output. And again, now you have to overlap the next layer, which is 087. As soon as you do it, you have one output. But for the next one, you have nothing. You have only 10 and 139 there, right? So you assume default values to the right. This is where overfitting becomes a problem. It takes in nonsense values here, and it eventually gives you a very, very different or a random output, which is of no use, right? So as you can see from the output of this particular layer, this is the entire output. What you see on the white here on the bottom right? 25, 87, 139, and 139 again. So this becomes the actual output of this particular layer, which is again used in a very simple concept called as flattening the layer. So flattening the layer, all we're trying to do is after pooling, we try to take the feature map and convert it into an array. So we have numbers 25, 87, 139, 139 in the form of an entity, right? A data storage entity. We're going to take that, convert it, and flatten it out into, as you can see, we're just basically flipping it and flattening it out to get us again the same numbers arranged in a different order, right? After all of these things, the convolutional layer, the ReLU layer, then came the pooling layer, we have the fully connected layer. In the case of a fully connected layer, what happens is that we are bringing together all of the features to give us a particular model output. Whatever happened until now, from us giving it an input to it giving us an output, everything is brought together here and created a network, guys. This is the fully connected network. One important thing that you're supposed to know is this is the final step in the process of a convolutional neural network, right? So once you have flattened all of this has arrived. Each of these goes as an input, then you have the hidden layers which get trained, and then you can see the output layer which has a prediction saying, hey, it's a dog or it's a cat. Now for all the input that we saw, you remember the image of two dogs that we saw? Well, based on all the data, our model will learn. It gets passed to the input layers, then it connects to a multiple hidden layer network where it trains, it learns, it understands, data moves in both direction, forward propagation, backward propagation, and all of that. And at the end, the last layer, it says, hey, I predict that the image you have shown me is that of a dog, right? So this is how we get a CNN to work, guys. Now that you understand the theoretical aspect of all of these things, I want to show you guys the practical of it. it. I want to make sure that you guys understand this and I show you practically how fun it is to work with neural networks, right? So let me quickly open up. So right guys, now we are here at Google Colab as we've been using all these past modules. It's an online Jupyter notebook hosted on the Google Cloud platform. The first thing I have to do is connect to a runtime, right? Once you're connected to a runtime, Google Cloud platform allocates a certain amount of resources to you so you can go on to work with it, right? So once it says connected, we have to do one step which we have not done until now, is to make use of the power of graphical processing units. Google Colab allocates a certain amount of GPUs for free. So using that, we have to change the runtime from the actual CPU. So click on runtime, click on change runtime type and click it as GPU and hit save. So we're going to be using the power of graphical processing units, because at the end of the day, your GPU can handle image processing a lot of times faster. It can learn, understand it better using the power that goes into making a GPU, right? Now think about all you gamers who are there. You know what a CPU is good for. A CPU does everything nice, but if you have to play the latest games in 4K, not native support in the CPU. CPU is meant for other things, not image processing, graphical processing. So you have another entity called as a GPU or a graphics card that you put in your computer or your laptop, right? That is what handles all of the things. Eventually all the output that gets given by the CPU to be shown on your screen is what it manages that, right? So again, here we're going to be using the same concept too. GPU with working with the GPU, your CNN is faster, more efficient and trains well as well, guys. So let us go on to perform image classification with convolutional neural networks. The first step I'm going to do is we're going to be taking a look at the cat and the dog classifier here. So with this command wget, all I'm trying to do is I have the training data set and the testing data set stored in a Dropbox format. So it's stored in an online cloud storage. I'm trying to implement it and bring it to my to the working environment here. Now if I click on the left side here, files, it should have downloaded all of these, right? So I asked it to download 2 zip files. Again, one data set, it is already split into testing and training. As you can see, 2 data set elements are here, testing set and the training set. Now these are images of cats and dogs and all of that, and again all of these are labeled data sets. Again, a dog is a dog. For our reference we can understand it. As you can see, one file was 173 MB, which was the training set. Then the testing set would also be something similar in size, 217 MB in size, right? So this downloaded 2 zip files for us. Now what I'm going to do is I'm going to unzip the contents of those zip files to make sure I can actually see what the image are like. Look at it, you can see it says dogs / so we have thousands of images of cats and thousands of images of dogs. So all we're trying to do is we're going to take a zip format, unzip it and give it to our Google Colab, saying, hey, here are the individual images which you have to give to the model to learn, right? So since there are a lot of images, this is definitely going to take a little bit of time. It's asking me if I have to replace all the testing training sets with the storage. I am going to say let me just click on this. I have to say A, saying that, hey, replace everything with, create a new entity there and give me the output. So now it is basically going to create folders. In a folder, it's going to add cat. Another folder, it's going to create dogs. It's going to separate it based on testing data, training data, and all of that. Perfect. I hope that step was clear. Let me zoom in a little more on the next set of code. So the next set of code is I want to print a simple set of an image to show you what a cat looks like, right? So I have picked up one random cat image here, and all we're trying to do is we're trying to use the imread, the image read function, and we're trying to use matplotlib to plot an image for us. And as soon as I hit play, it is going to print the cat, which is from the file cat.4001, right? So this is a cute picture of a cat. You are trained, I am trained, both of us know that this is a cat. Our computer at this moment of time is not intelligent enough to know this is a cat. I have printed this for your reference. Similarly, let us print a sample image of a dog. This is such a cute dog, right? We know this as soon as we look at it, right? Now, we cannot say this is a cat, right? Now, we are well trained enough, I hope so, to look at it and say this is a dog. Now that we've taken a look at 1 or 2 sample images, next we're going to import all the libraries that goes into understanding the convolutional neural network, right? So we use TensorFlow, which is very popular, as I've discussed at the end of the last module. We have Keras, we use Matplotlib wherever we want to plot images and all of that, right? So our model is going to be a sequential model, since the data itself is sequential data. We're going to be using dense rack, we're going to be using two-dimensional convolutionals, we're going to be flattening it, we're going to be using max pooling for the pooling layer, we're going to have activation function. So we're trying to just bring in all of those and import all of it, so at the end of the day, later down the line, we can use it instead of having to manually import everything at that stage, right? So one code block, 5-6 line to import everything we need, and we are done. Now, just for the sake of showing you guys that we're going to be using the latest version of TensorFlow, it's 2.4.1. So this code works very well with the latest version of TensorFlow. So I've just printed out the TensorFlow version for your reference, guys. The next thing we actually come to is the aspect of where we are, designing the actual model. To design the actual model, you have to initialize all the things that you have given, right? So you have multiple images here. You have to sometimes resize it. You have to tell your model, hey, this is what is at hand, right? Now I'm telling my model saying, hey, look, the image width and the image height, the height and width of every image is 150 cross 150 pixels. Here is where you can find the training data set. Here is where you can find the testing data set. I have 100 samples that you can use for training. I have 100 samples you can use for testing. And whenever you're learning anything, right, since this is an iterative form of learning where the network feed forwards, compares with the output, comes back with backpropagation, learns again, minimizes the loss, right? So I'm telling it, hey, 20 times I want you to do this experiment, this iterative experiment. That is what an epoch means. And an epoch basically means the time count, how many times a thing should be done. In this case, I wanted to learn 20 times. So I'm just initializing a variable to say down the line, I'm just gonna, instead of manually putting down 20 there, I'm gonna say, hey, use the value of epoch. Epoch consists of 20, so it knows it has to do it 20 times, right? Next, I have the batch size equal to 20. With batch size equal to 20, what we're trying to do is we're trying to say you have 100 images, but split it down into sub batches and use 20 images at a time to learn and verify. As soon as I run this, all our variables are set. So when we discuss the theory aspect of things, I already told you what an image consists of, right? Pixel data in terms of three things. It's a 3 cross 3 cross 3, or let's say 32 cross 32 cross 3, where 32 cross 32 becomes the size of the image, and the last thing is the channel, which represents the color RGB, one number for each channel, right? So sometimes it so happens that whenever you're trying to represent an image, in the case of this array representation, you can have first to be all the row data, then you have the column data and the channel data. This is called as row first representation. If you have channel first representation, your channel itself becomes the first. So in our case, it can be 3 into 150 into 150 if it is channel first. If it's row first, it becomes 150 into 150, and then comes the channel at the last into 3. Right? Perfect. So all we're trying to do is we're checking the shape of what inputs we have, and we're trying to say that, hey, even if it's 150 into 150 into 3 or 3 into 150 into 150, you please know what to pick up. So we're giving it both the situations to understand. If it is that, take this to be the input shape. Else, if it is another one, then here's a different input shape that you have to understand. Right. The next thing is where we actually go on to train the model to generate an image for us. Now see, you might ask a question saying, why should we generate an image since we already are passing it images, right? Now, if I just give it that image as it is, it can take a look at it and say it's a dog or a cat. It can train on that. A machine learning model is good enough to do it. But what if you want to change the image in a way where you have to, let's say you have an image, you want to reshape it, you want to zoom into the image, you want to flip the image in a different direction, you want to rescale it, resize it. If you do all of these transformations to an existing image, can it still understand later, right? Can it still say that it's a dog or it's a cat? So to make sure our model accuracy is high, we go on to reshape, change, shear, we just tear the image left and right, and we, in a very different way, we try to think about like a crazy mirror when you go into these houses, right? It just distorts your body shape and it shows you yourself in a different way. That is what we're trying to do to our images here. So even with that case, it needs the capability to say it's a dog or a cat. So this is a simple 4-line code of how you can do that, right? So we're trying to flip it horizontally, we're trying to zoom it, we're trying to shear it, and we're trying to rescale it. Now all of these values, why we require rescale from 1 to 255 is that sometimes the values that we obtain will be very high numbers. We have to bring it down into a range. We have to bring it down into a range between 1 and 255. That is why we go on to do that. And in the case of the color aspect of things, right? So even RGB values will have a value between 0 to 255 after the first line executes. But here we have to bring it to a range of 0 to 1. So later down the line in processing, it becomes simple, right? So So we train the image data generator. It creates all of these new image for us and gives it for us. So let me quickly go on to run this, and it says, hey, I found 8005 images belonging to two classes. Our two classes is cats and dogs. It eventually rescales all of it and gives us the output, right? So if we go on to see what the representation of the image data generator looks like, what are we doing with the image data generator? We are trying to generate an image, we're trying to reshape it, we're trying to resize it, we're trying to horizontally scale it, vertically scale it, all of that, right? So as you can see, this can be a part of a very big image where there is a table in the background or whatever it is. We are trying to rescale it. Then you try to shear an image, right? So this dog that we are trying to see here is a little stretched in its up and down aspect, right? Now even this cat. So even this image, and of course even this one, right? It is squished on the left and the right side. So this is a simple representation of we trying to generate images in a different form for it to understand, guys. Right. The next thing we're going to do is actually take a look at the layers in the convolution neural network. Again, you already know the layers. It's a convolution layer, ReLU layer, a rectified linear unit. You have the pooling layer and the fully connected dense layer, right? So here is where I say, hey, I want this to be my input layer. I want 64 neurons in total, which use a 3x3 filter. And then in the pooling, right, this is the convolution layer. Next, we have the pooling layer where I say, hey, I want to use rectified linear unit and bring the data down into that. So again, 2x2 filter is applied there, and our final layer, which is going to be the dense layer, which consists of our output layers. We're going to try to say, hey, take all of these things, create a fully connected layer for me, but create it in a one-dimensional array, right? So 64 neurons are what we're going to be using for that layer as well. Again, this talks about all the hidden layers too. So the convolutional layer, we have the activation function based on the rectified linear unit layer. Then you have the fully connected layer, and at the end of it, we have the output layer, right? So we're going to be using an activation function here called as the sigmoid activation function, which again gives us the output. So as soon as I go on to run this, it is almost like I've told it, hey, this is the model structure. This is what my model should look like. So it actually goes on to gives us the input shape of each of these layers, the output shape, how many number of parameters were there, right? See, look, the amount of trainable parameters it found were 22 lakh trainable parameters, and of course it goes the same to talk about how the total number of parameters is there, because we are only using the training data set to learn here, right? After you have created the basic structure of all of these layers, we have to go on to compile the model. We have to create a loss function. We need to have an optimizer. Optimizer is basically making sure that whenever back propagation happens, your values are being compared, right? At the end, our goal variable should keep going up and our loss should keep coming down. To calculate that loss, how do we do it? You find out what the actual output is supposed to be, compare it with what the input is, minus that, find a difference, right? That is how you know what is the loss function. Bring the loss down and use the metrics of accuracy to give us what it would look like, right? That is what, simple guys, compiling an entire model to say, hey, this is the optimizer I want to use, this is the loss function I want to use, here is the structure. Again, look at it, it's what, all in all 10-12 lines of code for a very, very complex convolutional neural network. Simple, right? Then comes the actual place. Look, train generator, steps per epoch, all of these things is all the variables that we used at the first step of model initialization. As soon as I go on to run this, simple, it's going to start training. I told it to train 20 times, right? I told it to do 20 epochs. So now it is going to take a certain amount of time to make sure that our accuracy rate keeps going up with every epoch and the loss keeps coming down. Look at your screen right now as I speak, right? The loss is coming down. It started at somewhere around 18 or something, and now it's at 11. With this particular epoch, loss was at 11, accuracy of detection was 0.52, right? So the next one, the next epoch where it is going to train, again, it's going to use 20 sub batches of data, and look, the loss function is again exponentially down for this particular epoch, right? Accuracy is slightly going up from 0.52 to 0.59, guys. Now similarly, this has to go on for 20 times. With every thing now that you see on your screen right now, just look at how time keeps going on to be less and less. Sometimes it becomes more as well, but at the end of the day, look at how the loss just keeps coming down and down and down, and the accuracy just keeps going up and up for all these 20 cases, guys. Let me zoom out a little so you guys can see better. So guys, as you can see, we are done halfway through. 10 epochs are done, and you look at the loss values, right? It is just keeping, it is coming down and down, but in one step, certain times, if it is, the loss can also go up based on how the weights were changed and the back propagation step happened, right? See, it was 0.59, but in the ninth epoch, it went to 0.61 again, and now it relearned something, so it's bringing down the loss again. That's the beauty of neural networks, guys. Now let us wait for the next 10 epochs to finish so we can analyze what is our final value and our accuracy rate. So guys, this took about a solid 5 or 10 minutes to get done, and as you can see, with every single epoch from 1 to 20, epoch 1 out of 20, 2 of 20, 3 of 20, the loss at the first step was very high because it is, of course, the first step you cannot calculate a loss unless you know what the output is, right? So you can ignore loss at the first step. As you can see, the loss keeps coming down from 0.7 until 0.5. That was the best of what we could train the model for 20 epochs. If I do it for 100, 200, 300, it might train better. Of course, there's no guarantee of that. I have to try it out. And then if you look at the accuracy, the score went up and up. From 0.52, we are all the way up to a 70% accuracy of detection, right? So you get a lot of metrics that you can check out as well. You get the value of accuracy, the value of loss, and all of these things. This is the actual process, guys. When I say, hey, train 20 times to create a model and understand, that is what I was doing. The next step we're going to take a look at is to find out how accurate the model itself was when it went on to learn, right? So here is a simple graph that talks about model accuracy and model loss as well. Let me zoom in a little. Yes, so model accuracy talks about what the testing data set is supposed to be like and what the actual training happened, right? So the blue line talks about accuracy with how many number of epochs, right? Every one epoch it trained. So this is how it could analyze and train, and this is how it compares to the testing data set as well. As you can see, it is almost in line, perpendicular, parallel to the data set, which is showing that it is learning in a way with every epoch that it is bringing it closer and closer and closer to bridge the gap that exists between the testing and the training data set. That is what we want to see as well. Of course, in some epochs, the loss function, as I told you, it can go up again and come down. Of course, again, that is a common thing. And look at this. This is exactly what my point was. Your model loss, when we're talking about it, right? Your loss keeps coming down and down, but sometimes with many epochs as you keep going. In some epochs, again, the loss can be very high for the testing data set and eventually it just levels out. So we want the loss to be as minimal as possible, right? That is exactly what we're trying to show. And of course, the last step is where we are actually doing the magic. We're trying to say, hey, here is an image, tell me what it is. Either it's a cat or a dog, right? Now, as soon as I go on to run this, we're trying to predict if the result is 1, it means it's a dog. If the result is something else, it means it's a cat, right? Now, this is the image that I passed into it. And this is the image it's printing for me. Look at the prediction. If I give it this image as an input, right, for the first layer in the convolutional neural network, if this is the input I give, this is the output. It says, hey, it's a cat. How amazing is this, right? You can just change around any image here and ask your model to find out, guys. Now take a look at this. If I open the training data set and if I open the folder inside it, for the cat pictures, again, I have a lot of cat pictures here. Yeah, as you can see, look at the amount of cat pictures I have here, right? So I'll keep going on and on and on. It used all these to train what a cat looks like, and similarly for a dog as well. Look, I'm going on. It's still it's amazing how many amounts of pictures we have here of cats and dogs. And all of those were just cats. Next, we have all of these for dogs as well. So you can take any one of these, ask it saying, okay, so what image is this? Your neural network model is going to give you an output saying it's either a cat or a dog, guys. That is the most fascinating concept of convolutional neural network.
How exactly sampling takes place here? Yeah. So if there is an image, I hope everybody is very clear. If I say image is 16 megapixel, or if I say image is 2 megapixel, or if I say image is 64 bits image, for example, or 644 bits or 64 bits or whatever. What does it mean is here there are more pixels. It means the array that is holding this is pretty big. It is of size 16 mega. And here the size is very less. So there is a problem now. In your current project, what is the size of the image? The size of the image is 32 cross 32, or what do you have taken? 120?
Yeah, 32.
ठीक है. 32 cross 32 is the size. So 32 into 32 is what? 1024. Yeah. So it is okay for me to build a neural network which can take 1024 neurons as an input, and which can, do up and down of these things, and finally give me a classifier as an output. It's okay, not a problem. Correct? But what if now this was 16 mega? So when I multiplied these two, it became 16 mega. Now, is it possible for you guys to handle this? Yes or no? Can I have a 16 mega input neural network?
Memory problem will be there.
It'll be a memory problem. It'll be a computation problem, cost factor. A lot of things comes into picture. Agreed? So in this case, what do? Is we don't go ahead with simple MLP or FCNN. Guys, what is MLP?
Multilinear perceptron.
Correct. Multi-layered perceptron. Okay, which is nothing but another name of FCNN itself. Okay, so please don't get confused. I have seen many people, they say MLP and FNN and all, they mean the same thing. Perceptron is nothing but a neuron. Whenever a neuron goes into hidden layer, that becomes a perceptron. God knows why, but this is what it is. Okay. Now this becomes very difficult to compute. So now what are we doing is, what if we just saw, we had a Python code, beautiful Python code we are writing. It is working good. What we did, we went on to a new software, or especially me, went on to a new software, and we got a diminished version of it, which does the exact job as what it does. I will say not as effective as this, but yes, at least I can say if I'm able to achieve 70% of what it does. I'm very helpful. Why should I code? I should directly do this. Why should I waste my time on coding? Agreed, everybody? So same thing you can imagine about images. What if I don't want to scan the whole image? So let us say this is an image, and there is one person standing in the image. Okay, let's ignore my drawing. Okay, yeah, let us say this is a person, and there is a flower over here. There is a flower pot over here, and say there is one picture. In that picture again, there is an image. Okay, something like that. Let us say we have this. So if I ask you guys, what is the information that you guys can derive out of this? You will definitely tell me that there are three spots of information. First is, there is an object, which is a frame. There is an object, which is a flower. There is an object, let us say, which is a pot. There is an object, which is a face. That's it, you can derive out of it. Let us say you've got four. So if you tag this up, if you remember what do I mean, what do I mean by tagging? Your current project has got taggings. Agreed? Here also we have taggings. I will say object. I will say person. I will say object. Okay. Now there is chances if you have designed it very nice, it will detect a person out of this also. Yeah. So if I want to do this, I do not have to scan these other empty parts. I hope you people are getting it. I don't need to scan this. What if I design small filters? Okay, what are these filters? These filters are some random filters, like your random weights that you have chosen or you have seen usually. Let us say these are some weights, some filters, which when you multiply with the whole image, we are able to get a diminished version of this whole thing. So there is a possibility that what if I multiply this filter to this, okay, and I will get lot of diminished feature maps like this. I can call this as a feature map. I can call this as a feature map. Now, what if I use this as one image? Now, this could be around, say, 4x4 image, for example. What if I could use this into my fully connected neural network to do a classification? What if I could use this separately, this separately, this separately, this separately? So I need to run my fully connected neural network 1, 2, 3, 4, 5 times to identify these 5 objects. Agreed? So rather than running neural networks megapixel times, I'll try to find out some features so that I will be able to classify them.
Yes, Krishna, clear.
Perfect. So this is what is your neural network. Convolution neural network. And this is what we are going to do down the line. So in convolution neural network, so whenever I say filter, you people should completely understand that we are talking about convolution. Post this, there are a lot of things I will show you down the line. And always a convolution neural network is backed up by a fully connected neural net. So this is not leaving us anyway. So whatever you guys have done in the first session or first module will remain with you guys through this complete convolution module. Okay, perfect. So now moving on, what are the other things I was talking about? So I will just show you directly that particular page. Okay, let me be fair now. Let me not be rushed because we have got good amount of time today. So these are my filters, which I am giving it to my image. Yeah, so my white portion I have named it as -1, and the colored portion where 1 is written, I have put it 1. When I multiply, I'm going to get a diminished version of this. So if you want to see what do I mean by diminished version, this 3 cross 3, which is 9 numbers, I have diminished to one number called 0.33. If you still want to understand how it does it, I'll show you one small GIF which does it. Guys, just observe the GIF on the right hand side. A 5 cross 5 matrix is now diminished to 3 cross 3 matrix with one convolution. Everybody's okay with this? How we got this one number, I will show you. It's a formula, very simple formula. Manual multiplication is needed here. Okay, so yeah. So this is what we have done. Good. Now when we did this, we got 3 matrices like this. Okay, post that, this matrix, whatever we got, we will transfer it to an activation function, say ReLU. Now, as soon as you pass through ReLU, you people know that zeros and anything below 0 will be omitted. Remaining, whatever is left will be processed over here. So now I have got this as an output, and whatever I have hidden, that means it will be moved out of this matrix, negative numbers. Moving on, there is a technique called pooling, max pooling or average pooling that I do. I'm still not happy with this. I want to still diminish this image. So this is now, I will say 7 cross 7 image. Now I will say the size of my filter was 2 cross 2. So in this case, I will do a max pooling on this. I will say, find out the maximum features out of this 4. Maximum number out of this 4. Obviously, it will be 1. Do it. This is called max pooling. So the whole 2 cross 2 matrix now is represented by 1 cross 1. That means I'm dividing the whole matrix by 4. Agreed? Guys, simple. Instead of max pooling, you can even do average pooling. Average pooling means take an average of all 4 of them. Put it over here. All right. So do it. Pass this filter to each and every portion of this matrix and do it. Good. So this is what it is.
So is it always 2 by 2 that we have to take?
No. It can be more than that also. We have to define that.
Okay.
We have to define our max pooling thing. But usually we take 2 by 2 because it is easy to decide, you know. And let us say if we take 3 by 3, it will be this divided by 9. So there is a possibility that we might lose a lot of pixels out of it. Do you agree we have lost some pixels here? Information?
Yes.
Yeah. Now, why is this? So why am I happy with this? One question to all of you. So if you people got this pooling part of it, quick question. What is the use of doing? Like, we are already happy. We have already diminished the matrix. We are happy with it. Our neural network can take it. Still, why are we doing this?
Optimization.
Sorry?
Optimized version of.
Yeah, correct. But why? Still, why I want more optimized?
To prevent overfitting, kind of.
No, not exactly here. See, I'll give you one very simple example. Say I have currently I have 5 batches under me. Okay, all are my AI/ML batches only. Now, from this 5 batch, if I want to, let us say there are 4 candidates who are the top performers. For example, let us say candidate number A, candidate number B, candidate number C, candidate number D. From all 5 of them, let us say something like that. Now, if I want to represent how a batch looks like on an average, or what is my strength of my batch, Can I say I will pull out the best out of these 4, max pooling, or I will take an average out of these 4 and pull it out? Correct? Yeah. So what does it mean is this particular 4 things, when they come together, they kind of represent a single region. So it could be, let us say, an eyebrow of a person, like this. Okay, where if my scanner has gone onto it, or if my, say this is my, I will choose one light color. Okay, say this is my convolution. Okay, say for example, we are talking about, say this is a face. Okay, imagine this is a face, and say these are my eyebrows onto that. Okay, now what am I doing is, let us say my scanner is currently hovering over one of the eyebrows, something like this. Yeah. Now what if I'm doing max pooling onto this? What does max pooling do? We just saw it will take the best feature out of this. Do I need all the features here, or do I need the best feature out of this? Can I say here the best feature is nothing but the black portion here? Let us take and pull it out, saying that when I scan through this, I find out this particular location, the color of this image is black. Very simple. Note it down. So in future, when you are giving a new image, when this is going through a newer image at this particular location, if max pooling pulls out black, that means this image and this image is perfectly same. Let us say this person, I know it looks scary. Let us say this person has got one, what you call, mole on his face. And when in future you compare it at this particular location, definitely this mole is going to be there. So it's going to understand that yes, it is a same image. A very high level view, guys. We have not dived deep into it. Huh? Just trying to understand you guys that sometimes what happens is when you try to think that, okay, we are removing the pixels, not actually we are taking the best features out of these pixels. Take it that way. All right. Any questions onto this?
But Krishna, we might lose the information, right? And in images, mostly it's like black color is more dominant in any ways, right? So if there is anything that is having less information but also significant information, we might lose it, right?
Yes, kind of, yes. So that's the reason what we do is we strike this, we make sure that our filter that we have designed here, it goes through, okay, 1 minute, let me change the slide. Yeah, I will make sure that the filter that I've designed, first of all, I'll make sure that I have done a good sampling. I have not done a waste sampling, first of all. And also I'll make sure that my filter goes through almost everything. I don't lose any of this. My filter gets multiplied with everything of it. Okay, so you are kind of right. Yes, when we try to diminish something, it happens. But also on the other side, when we oversample it or when we do a good sampling, we will not be losing any pixel in this case. All right. See, what do I mean by sampling? I will give you a very good example. Let me open up an image. If we have an image here, yeah. So there are chances that when I do some type of sampling, 1 pixel could look like this. And also there are chances that when I do very good sampling, 1 pixel might look like this. Also, if I try to do more sampling, 1 pixel could look like as small as this dot. So if I have good samples like this, more samples, it will be easy for me to remove certain part of it. It's okay. Because if you observe here, the same color propagates almost through the complete top part of the frame. Agreed? Yeah? So if I remove 5 to 10 of them, doesn't matter. Pixels. Yes?
Yeah.
So guys, be very frank onto this. Are you people able to visualize or not? Because if we say, like, if we don't question right now, no, then down the line in second and third week, we are not going to go back onto this. So please be very clear onto that. Whatever I'm saying, are you guys able to understand? Amit, Akash.
So I just have one question, Krishna. How about the samples? Is it like, because we might have like 1 lakh of samples provided to us in the data. However, it might be an individual image which might not give the correct representation of that data. Could be like nose is coming on the left or it should be on the right in order for
Augment.
augmentation and flipping and all those things. So how do we ensure that the samples are right in place as required for our analysis? Because we cannot check all the 1 lakh images if we are provided with that, right?
Correct. Correct. So for that, we will see something called metric learning in one of the weeks. I think it's almost last week of this module, where we will try to find out the distance between the two images, how far they are. Similar images, but how far they are from each other. Okay, a very good question, but let's hold on till the last week of it. Yes, we'll cover this also.
Sure, but I am clear on this, Krishna.
Perfect. Because this is one topic where majority of my batches, they don't get it, that how by filtering or multiplying a filter we are able to get an image. Okay, good. Second application I will show, why CNN. So if somebody will ask you why exactly CNN, so you can give a very simple example is, whenever I show you, let us say if you look at a car, and let us say the car has, the front part of the car is like this. We are, 1 minute guys, really sorry. Yeah. Say the front part of the car has got 2 openings like this. Yeah. And definitely we know what car it is. Let us say this is a BMW, for example. Just imagine this BMW. Okay. Yeah. So do you go and check the car? Let me check the wiper. Let me check the steering. Let me check the hood. Let me check the seats. No. Visually, if you want to identify something, immediately from the bonnet, down the bonnet, when you look at these filters, you will get to know, okay, this is nothing but a, BMW. Also, if you look at the Audi part of it, right, and the filter, you might find the 4 bangers. So definitely this is enough for me to identify image. Same concept, you bring it onto computer vision. You don't need to scan the whole image if in case you want a generic scanning happening. Let us say, I'll give you a very good example. I am currently working on this project where this is for my gated community there where I currently live. So we have got an app called MyGate. And what does this MyGate do is it helps us to track the vehicle. So somebody is coming in our community, it has to report, and there is a notification sent to the owner that somebody has come to meet you. Do you allow or not? We say yes. So everything is manual. The security guard has to get the name of the vehicle, get the type of the vehicle, name of the person, a lot of things. Now what we have done is sometimes also it gets unnoticed because the person who's coming from outside doesn't know. He directly walks into it and security assumes that, okay, he's a part of the community. So sometimes they go unnoticed. So what currently I'm working now on is, let's install 2 cameras over here, okay, which will try to snap a picture out of these incoming cars. And as soon as they take a snap a picture, they should be able to locate where the number plate is. And if you remember your current project that you are doing, we can easily identify the numbers out of it. And from my central database, we'll get to know whether this car belongs to the community or is not in the community. If it is not in the community, the gate, let us say over here, there could be an automated gate which will open or close because of these triggers, for example. Okay, so far I am able to identify. So if I take a webcam and run around through the cars, I'm able to get the number plates. So I will show you guys shortly once you guys understand what I'm talking about. So probably second or third week of this session, I will show you this, where we'll take a webcam and we'll try to identify objects out of them. Okay, good. So this is what it is. So what I wanted to show you guys here is, sometimes in computer vision, you don't have to identify the whole image. You just have to focus on certain part of the image. That's all. If you get it, do it. And how do we do it? CNN will help us to do it. In CNN, we don't scan the whole thing. We don't need the whole thing as an input. We scan certain parts of it and we take it as an input. And sometimes some of the parts are perfect image that we want. Good. So this is one example of CNN. I will give you one more example where this is used. Nowadays, if you go to these metro cities, there are malls. In malls, there are parking lots. And now right in front of the gate itself, the display. How many slots are empty on which floor, which level, and what size. Good. So earlier what they used to do is they used to put sensors over here. So if there is a weight on the thing, it is car, there is a car. If not, there is no car. Actually, the sensors are very costly, and during maintenance and all, they get destroyed. They have to embed it such a way, very sophistication has to be followed over here. So now what they do is very simple. They put a camera. If they find some other color over here, that means there is a car present. The slot is not empty. The counter will be 0. What is this? This is called semantic segmentation. This is your week 3 content that we are going to do. We don't care what it is. We just see that there is one background color and there is some different color on the top of that. Done. Over. This is occupied. I don't need to know what car it is, what color it is, what shape, size it is. That's not our application. Good. So this is where convolution neural networks will come to our help. Good. Now coming on to the weekly content. So this was a little extra. So all we do is we take the image, we go through convolution, we go through ReLU, we go through pooling. Again, we go through convolution, ReLU, pooling. If you still want more, you can go through normalization, your wish. Okay. After this, what did we get? There are 2 layers of convolution I did. What did we get? A bigger was converted into a smaller. Now, next, what to do? Next, flatten them up and push them on the fully connected neural network. That's all is your CNN. This is your flattened data, and just ignore this. 0.66 means 0.55. Actually, it's an Excel screenshot, so it did not do decimal adjust over here. Okay, so 1, 0.55, 0.41. They are flattened completely, and that flattened thing goes here, and you know what happens here and how we classify over here. That's it. That's all is your convolution neural network. And when you bundle all of these together, this is how it looks like. Image, convolution, pooling, convolution, flattening, and your fully connected neural network, or MLP, whatever you call it.
So, Krishna, I have a question. How many convolutions and pooling should we do?
Correct.
Is there any recommendation, or how do we determine when to start doing the flattening?
Yes. So there is a formula we are going to see down the line, which will help us to do this. But frankly speaking, I will tell you, what you have to do is you have to determine what should be your input here, first of all. And from there, we will go down the line. Okay. So if you want, say, 64 inputs, that means your flattened should be 64. And if, let us say, you are having, say, 10 features over here. Let us say 10 windows over here. Now, each window should be what? If you divide 64 by 10, you will get 6.4, which is not a good value. So what, in that case, what you do is you make it 8, for example. So 8 8s are 64. So it could be 2 cross 4 each one. Or you can say 2 cross 2 many number of times. I think 2 cross 2, 4, 4 to the 8. I think 8 number of times. Good. I'll show you down the line how to do that. Don't worry.
Hey Krishna, can you repeat it? I don't think I got that.
See, what was the question here was how many times I should do this, plus what should be the size of each filter and all this stuff. So it completely depends on my input, first of all. So what you are planning here. So let us say you are planning an input of 64.
Right.
If your flattened data is 64, how many filters I should have? This is what the question is. Yeah. So how do we devise this now? So take the reverse engineering concept. Let us say if my each filter is 2 cross 2 in nature. So 2 cross 2 means how many numbers I have? 4. How many more I need? 16 fours are 64, right? No.
Yeah.
Yes or no?
Yeah. 16 fours are 64.
Correct. So in that case, I need 16 of these. 2 cross 2.
Okay.
Yeah. So now go reverse. If I need 16 of this, how much should be my previous value? How much should be my previous value? We'll keep expanding. I'll show you down the line. But this is what majorly we do it. Also, one hint for all of you is very less models we are going to use this. We are going to use ready-made models. VGG, AlexNet, GoogleNet, MobileNet, ResNet, RNN. Sorry, not RNN, RCNN. We have ready-made models, huge, big models, which can handle values up to 6 million parameters. Very few places we are going to do this. Okay, because now no, we don't want to take burden of this. Something like our KNINE crime tool today. We already have ready-made models by some of our famous companies. Why not to import it and use it? Okay, good. Perfect. So overall, the whole module, what you will do, you will be given an image. You should be able to identify first of all the image. You should be able to detect the image first of all, and post detection you should be able to identify it what it is. It can be a car, dog, human being, cat, object, anything which I give you. You should be able to do it. So just what do you say? Overview to all of you. This session or this module will be around 7 to 8 weeks, to be very frank. It has got 2 projects into it back to back. The first project will come after your 4th week, where you have to detect an object. You have to create a boundary around the object. And the second project is you have to check whatever you have created boundary around, what it is, what type of object it is. Good. So by the end of 8 weeks, I will say, or else 2 months, you should be able to be good at computer vision. You should be able to at least implement basic level of computer vision from your side, from scratch. Plus something extra from my side, I will show you simple versions of this. I don't want you guys to go and code huge. It's good, nothing wrong. You do it. But also what we do on industry side, I will show you smaller codes. We use ready-made models to do it. Plus, I will show you something extra which is not covered here, which is called video, image identification, continuous image identification, CIA. Yeah. So that could be a very good application, especially if you are from manufacturing industry, building industry, or I will say majorly onto construction industry. Some last time I gave you some examples from my side onto testing industry. So still we are exploring how to use this opportunity onto. Okay, good. Especially if you are from retail and manufacturing, this will help you a lot. I'll tell you frankly, I currently interviewed for one of the startups who were into, I will say, manufacturing, and they were from a QA team, so they've got a very big project from one of these large automobile manufacturers where they want to pinpoint from their manufacturing line which product is defective just by looking at the image from the camera. So let us say there could be a lot of high definition cameras attached. Earlier, what these guys used to do, they used to pass this stuff from UVs, or they will pass a laser light to check the deformities and all. But now, looking at the image itself, they want to predict it. Okay, a very sophisticated portion of this. Good. So day by day, this stuff is going on and it's evolving. So by, let us say, I'll tell you one more thing. The timeline for computer vision is at least it will take for you guys 6 months to get normal to this and start applying onto real time. So by then you can say this will be a learning curve. So please be very patient with it. It is not a simple concept. Okay, what is it we discussed? Why we discussed? Because of image size, cost, and all. We are doing this. More or less, this is what we saw in my handwritten image diagram where you have an image. You take a feature out of this, convolute it, flatten it up, put it onto a fully connected neural network and get the prediction of it. So if you observe here, we have a prediction called car, truck, and van. Yeah. Good. All right. How I just explained you how we do it. So please remember one thing. This is your static layer, forward propagation layer. This is your forward and backward propagation layer for learning. All right. So this is your classification layer. This is your feature learning layer. Exactly where image processing is used. As I said, a lot of possibilities. One, as I said, could be onto something like object detection in any industry is good. Something like comparison. So nowadays, our government is using this to compare images, find out a lot of things. So this is usually used by Interpol, FBI, and all. We would have seen in movies also, where they compare two images and try to find out what is the best match and try to find out where they are and all of things. Third application could be into retail industry, where then let us say there is a product which is displayed on the website and there are a lot of attributes attached to it. Let us say there is a phone. So 2 GB RAM, this, that, and also. There are certain attributes which need to come from the technical person. But there are certain attributes which you don't need to manually type, like color, shape, size, what it is, which company it belongs to, a lot of things. So those things which can be easily scanned and put, they are automated. So some of my friends working with Amazon, Flipkart, Reliance Trends, and all this, that's what they do. They are hardcore into computer vision onto this cloth, objects. So whatever they see, they put it. So for example, there is a t-shirt which is displayed, let us say something like that. They can find out it's a V-neck t-shirt, is this color, this could be a probable size. Yeah, so some application. And then the final one I will say is onto reinforcement learning. Google car, Google glasses, a lot of examples you can take it up from this. Yeah, so it's a combination of computer vision plus reinforcement learning. What is reinforcement learning? It takes an image and learns it. It does not have to do all this. You know? If it is not in the corpus, it should not reject it. It should try to understand what it is. Good. Okay. So these are the applications. Any questions onto this? Anybody wants to know anything more onto applications specific to your industry where you can use it? Do let me know.
So, Krishna, have you come across any such usage in terms of HR services or payroll services industry?
Payroll. Yes. I will not say purely payroll, but yeah, one of my seniors has worked on to one domain. I'm not sure how relevant it is with your. So let us say there are a lot of invoices processed, no? Yeah. So from these invoices, they try to pull out the numbers they wanted. So might be you can do something onto your. Okay. Is it anything related? I'm not sure. Huh?
Yeah, so we have some kind of requirement right now in our company, but I don't think it's assessed fully of the capability.
Mm-hmm.
But it goes like this: so we get new clients, right? When it comes to implementation.
Mm-hmm.
So rather than going to clients asking them questions about how the current system is designed and what components, payroll components do they have,
Mm-hmm.
we actually scan the employee sample payslips, and from that we could determine that these are the components that are there and how they get calculated, the formula and everything gets derived out of that values that come.
Okay.
But it was a failure earlier. But if there is something that you have seen from your market industry or someone of your friends have worked in similar kind of thing.
Yeah, let me show you right away. I've got a very good example for you. Could help you. Okay, I'm not sure exactly what you're looking at. I have worked onto one of these where we try to pull out certain tags or requirements out of a document. So it was something similar to your thing, you can say. Just give me a minute. I'll not show you the whole case study because it's a part of your next module anyway. But give me 1 minute. Module number 10, NLP. I just finished this code, so a good time to see it. If you observe here, I'm able to tag certain words out of this. Yeah. So you can, in your application, I will say you can use partly to identify the text, partly as a text processing. And wherever you find a formula or a process or something which has got functions and all, you can use NLP to find out which is the closest it belongs to. So for that, you need to have a very good corpus. Huh? Corpus is a backend data. You need to have all possible formulas. I hope that's what I'm talking in sync with you. Yeah.
What I was trying to understand is there any way where we can have a mixed kind of database having images as well as the raw data that we get, which we were looking into machine learning databases?
No. So you need to have two separate corpuses. One is for text, one is for images, separately.
Okay, and we should be able to correlate these two, right?
Yeah, definitely. If you want to work on this, no, do me a favor, give me some sample data. I'll not expect the whole data from your organization. Give me some draft, fake data, which you think is in sync with that.
Mm-hmm.
We can work together onto this. Not a problem at all.
Okay.
I have done something onto text purely, but yes, we can include the images and we can combine both of them and tag it.
Okay. I'll try to get you some sample data.
Perfect. So what I do currently is I have done one of these implementations where we scan RFPs. Yeah. And we try to pull out requirements from RFP using image processing. So we can, using text processing. We can say which requirement is a functional requirement, which requirement is a non-functional requirement, which is a business requirement. Under functional requirement, what possible they are talking about. Are they talking about automation? Are they talking about functional? Are they talking about unit? Whatever it is. It's very easy to pull this stuff out. The only thing is, luckily I've got a good corpus for this. Yeah. So we can do that. All right. Okay, it's a shutdown for me. 1 minute, guys. I'll just restart this. Anyone else? Everything is good then? Yeah? All right. So let's see what we can, what is planned for this particular session is we'll take an image and data structures and types. We'll see to it. What are they? Convolution filters, kernels on an image, convolution neural network versus fully connected neural network, convolution layers, average, max pooling. We'll see this. And forward and back prop in CNN. Yeah, good. So I think we've covered almost everything. Now let's see what type of images or what pixels can consist basically. So we can have gray or we can have an RGB or grayscale. Now if I give you an example, what do you mean by grayscale is, in here, the lowest possible value for pixel, let us say 0, and the highest possible could be 255, for example. 0 could correspond to white, 0 could correspond to black, 255 could correspond to pure white. And whatever numbers you see in middle will be the different shades that you are seeing here. Okay. Good, everybody gets this? Yeah. Okay, so now moving on, what about this one? Here also same stuff. Here we'll have 3 different channels. One is called red, one is called green, one is called blue. Okay, let me go a little neat. Again, I started scribbling red, green, and blue. What are the numbers over here? Same thing. 0 could be darkest green, 255 could be lightest green. Yeah, different shades of green you can observe over here. 0 could be lowest blue, 255 could be highest blue. 0, 255. Now you may ask me, okay, fine, then how do I mix match? How do I get one color? So if it is purely green, we'll pick it up from here. But what if it is a combination of all 3 of them? In that case, there is a special function which will give us a calculation between all 3 and give us one number, which will correspond to one of the color matrices which is stored in our computer under computer vision. Yeah, so if you guys remember, there is a special type of plotting function called IMShow. Yeah, in that you put any matrix of your choice. Say create a 64 cross 64 matrix of your choice, no problem. You put it and try to plot it using IMShow. It will definitely give you some or other color out of it. So what does it mean is there are some predefined values stored in the computer which takes up these values. Okay, so this is what is 2 things which we'll deal with. Next, moving on, what type of images we can see? So we've got 2D and 3D matrices. What is a 2D matrix? A 2D matrix is your M cross N. And what is a 3D matrix? So I will say grayscale image could be a 2D matrix and RGB will be a 3D matrix. So in that case, I will say 32 cross 32 cross 3. That means it is a 3-channel 32 cross 32 image. And if you want to make it 4D, I will say, if you remember in your model, we have 42,000 images, 32 cross 32. In that is a 4D, but don't take it up as a 4D. You know, it's we can ignore the first and the last part. 32 cross 32 is what we are interested in. Yeah. And please remember, pixel is the lowest form in which an image could be represented. It depends all on us how we are sampling it. If you want more samples, that means if your image is 16 megapixels, it has more information, it is more sharp. If the same image has 1 megapixel, you can understand how blur and vague it will be. If you want to see how it looks like, a very lowly sampled image, look at this. This is how it looks like. Each square over here represents 1 pixel. I could have done it in a very simple way also. Each dot over here could represent 1 pixel. In that case, what would have happened? We could have easily been able to see his eyes, nose, mouth, and beard. Look at the blurriness. Okay, so if you look at this, this is how an image looks like on the back end. So this is your front end. This is how we give numbers to this image, where black is 0, anything which towards white is 255. And you can check it out. Look at this value and look at the darkest value. Where is it? Look at this value. They're perfectly sync. And then you remove whatever it is, and this is how it looks like on our Python side, backend part of it. Okay, what if I want to normalize this? I'm not happy with 0 to 255. What happens, guys, in that case? What we do is we divide it with the highest value. What will be range? What will be my range now? Can somebody spell it out? If I divide or if I normalize this, what should be my range?
Between 0 and 1.
0 and 2.
Perfect. Between 0 and 1. Very simple. This is how a digital image is processed in the backend part of it. Now, if you want to understand how a filter works, very simple. Just look at one particular corner of this image is being scanned or multiplied by the filter. This is my filter. And once the filtering finishes, this is what we get out of it. So a 3 cross 3 is becoming one number. So I can say I have divided the whole this thing by 9 basically. Totally 9 numbers are represented by one number here. This is what is my convolution. And how does it happen? If you observe here, very simple. -1 into 3 plus 0 into 0 plus 1 into 1. Like that you do it for all the rows and columns. At the end, we'll end up with -3, some number called -3. If you ask me what does this number represent, I will say it's just a pattern. So when I pick up one feature out of an image, the answer for that pattern or that image is nothing but -3. So tomorrow when you get a similar, you get almost all the numbers similar down the line to another image, you can say that this image and this image is perfectly same. Future. Okay, perfect. So moving on. Now there is a thin line of difference between convolution and correlation. So just now we were thinking about, okay, what does this filter? How do we decide this filter or not? Again, I will say filter is, let us say, some randomly chosen 3 cross 3 matrix here, for example. So what is the difference between correlation and convolution is? In convolution, what I do is, it is in correlation also we multiply, in convolution also we multiply. The only difference here is every time you want to use a filter, no, you flip them. You flip them. You don't use the same filter every time. You keep flipping. Now, what do I mean by this? Let me show you an example onto this. So let me take you to that place. Yeah. So let us say this is one image given to us. Okay. These are the filters that I'm going to multiply this image with. So have a close look at this particular filter. This is how it looks like. Now, just see what I do. So when I change, sorry, I'll show you guys how do I play around with these numbers and all. What I'm doing is both my extreme vertical ends, I'm making it -1, -1, -1, and whatever middle values are there, I'm keeping it 1, 1, 1. Look at the original image. Now let me run this. At least I need to run this. That's it. Yeah. Now let's try to plot this up. Okay. This is my original image. I have changed my filters. Earlier, if you saw, there was a different filter. It was vertical stuff. Now it is going to become. Did you observe this, guys? Yeah. Just by changing certain values in and out, I changed my complete image, how it is interpreted. Look at this. Yeah. So just by changing these filters, I'm converting this image into this image. One more thing I'll show you. Let us say I divide this by, say, 14. For example, some random number. It will be blurred. Okay, 1 minute. -1, -1, -1, -1, 1, 1, -1, -1, -1. Okay, let's try to generate this. See? Yeah, and what if I remove this, for example? Yeah, the complete image is changed. So please remember, when a filter changes, definitely the value of your pixels inside the matrix also changes, and because of that, you will get different images. So this is how we play around with images, and this is how what we mean by filters. Okay, good. So now let's see this one. Did you people see the implementation in the weekly video onto this, or yet to do it? Do you want me to do this image processing basics, or we know this?
No, we don't know this.
You know this? Okay, let's do it. See, very simple thing. We have seen this Snapchat, and what else we have? We have got Instagram and Facebook, and a lot of them now, if you just look at it, there will be glasses put on your face, or there will be some cap put on your face, or beard, and a lot of things are happening. And also sometimes it will try to change the color of the image. How do they do this? Very simple. Only they have to do is they have to design one filter like this. That's it. Okay, so this is an example of a simple filter. You can imagine they have to design a little bit bigger filter, such a way that they change certain background in and out, and they try to understand that this is your face, remaining things is not needed. Okay, so if I multiply this image with this thing, we are going to get this. Now, what is the pattern here? If I multiply this, if I want to sharpen an image, this is how I'm going to get. What is sharpening? You are highlighting the hidden features out of the image. This is what I call it, sharpening. If you want to do edge detection, this is how you are going to do it. So you will see only edges over here. Okay. Where do you think we need this, guys? Just try to think about it. Except this Snapchat and all I say, not those examples. Apart from that, anywhere else you are able to visualize we need this?
Augmentation.
Okay, perfect. Whenever you want to augment an image in your corpus, you can use this. Good one. Anything else? Anything else, guys? Okay. Let us say we are talking about something about into medical industry, for example. In medical industry, let us say you have a snapshot or a microscopic image of a person's cells, and they want to detect whether these are cancerous cells or normal cells. In that case, what we do is we pass it through one of these filters, such a way that we get edges like this. And from these edges, we might come to know how big is the size of a cell and all those things. Could be one possibility, and I've seen extensively healthcare using this nowadays. Nowadays, even the sophisticated hospitals that we go to, they can no need to show the X-ray to the doctor. The X-ray machine itself tags. Let us say if this is an X-ray. Okay, this is an X-ray of some part of the body. It tags itself where is the problem. It auto detects the problem. How? By this kind of machine learning or by this kind of computer vision learning. Okay. Also, I will say not only computer vision, you can use even our KNN and SVM also over here to identify these things. Very simple. Moving on, if you take the image of Lena, this is a very famous model. So when I was studying my engineering, all of my textbook had this image. Okay, same image used years on years. What is this? Take an image, put a filter onto that. What is this filter? Sharpening filter. Now, is this filter in sync with our earlier filter? Look at this filter, guys. 0, -1, 0. Okay, and look at our earlier sharpening filter. 0, -1, 0, -1, 5, 1. Okay, so wherever you go, this filter is going to be same. Now, what if I want to sharpen my image more? What is the possibility? What you can change here? Anybody is able to get the pattern?
5 needs to be changed to
Let's say 10. Good, perfect. So just understand the pattern, you will get the processing. Take this example, edge detection. Now, this edge detection, look at this and look at our edge detection here. Is it in sync? Not at all. What does it mean is it's not necessary always to follow the same thing. Yeah. In this edge detection, what we have done is we have highlighted the extreme edges with zeros and ones. And in middle, we are changing it to -4. Okay. Same thing if you want to more sharpen it, what we are doing, we are converting the complete third row to this zeros to ones and this to 2. Here also zeros are converted to -1, -1, and this one is 2. And this the middle one are all zeros. In that case, you will get a sharpened image like this. This is also sharp, this is more sharp. If I want to go one more level above, I could have done -2, 4, -2, 0, 0, 0, 2, 4, 2. It would give us a better one version above the sharpness. Okay, perfect. So this is what majorly in and out we do onto image processing, filtering. Now you may ask me, okay, fine, why did we do this? We did this because tomorrow you need to augment your image, or tomorrow you want to, basically compare two images. And let us say one of the image is in some form, other one is in some form. What you do is you apply a single filter on both of them so that you bring them to a single level, and then you physically compare them one to one. Or you use distance formula to understand how far are the points. Okay, good. Perfect. So this was your image processing. Now let me give you one example on this. Let us say this is one image of me. Okay. Let us say this is one more image which I have taken. So this was usually, if you look at our ID cards, I don't know how many of you feel that. I have a 6-year-old ID card from Capgemini. Okay. If you look at my image before 6 years, and if you look at my image now, this is something like before and after. Something has happened to me because of which this image is in no sync with what I currently look like. Okay. So let us say this is my old image and this is my current image. So let us say this is something on my ID. This is something which live my organization is taken. Now I want to say this is old and this is current. And there could be one more image from a person who looks almost similar to me. So I will say this is a positive image, this is a negative image. Positive in the sense it is kind of me. Negative means I know it is not me. What if I take this 3 separately through a convolution neural network? Say, what if I take this person through convolution neural network? Okay, I will get a set of matrix. Agreed? I take this image, I'll get a set of matrix. I take this image, I will get a set of matrix. Yeah. Now, what should I do to find out that these two are same where these two are not same? I need some patterns, right? I need something, some function. What according to you could be used here?
Facial features.
Sorry?
Facial features.
Yeah, but if you observe here, these are nothing but numbers.
Mm-hmm.
These are just numbers, some matrices. So what algorithm or what I should use here? Guys, you remember KNN? What was KNN? Yeah, I know you know KNN. Silly of me asking that. But yeah, what does KNN do? Distance? Yeah?
Yeah.
So what if I find out the distance between these two matrices? Give me 1 minute. I just have to plug in. Yeah. What if I try to find out the distance between these two? Okay. Let us say the distance between these two is alpha. And what if I try to find out the distance between these two? Let us say beta. Now tell me the relationship between alpha and beta. Guys,
Shortest distance
see,
between which?
see, when I subtract two similar things, what will be alpha? Can I say tending to 0?
Yes.
Yeah. And when I subtract two dissimilar things, this will be tending to infinity. Beta. So can I say alpha is always less than beta? Yeah. Or else can I say like this, alpha minus beta will be always less than equal to? Does it come to your, okay, fine. Let me not confuse you guys. What I was trying to say is, please remember at the end of the day, these are nothing but numbers. You can use any of your machine learning classification techniques to do this. Here, what I did was, here I used loss function as distance. We can definitely find out the complete distance and we can say which two are nearer, which two are farther. So if I say, if if we say two images are similar, I will say, let us say the similarity should be around 0.5. So when I subtracted them, no, let us say I got a value of 0.29. That means the difference between them is 0.29, which is very less as compared to 0.5. I can definitely say that the distance is very less between them. But let us say when I compared this with this, I got a distance of 0.75. It is above my threshold value. So I can say that yes, both of the images are different. You can use even CNN into that level, very simplistic way. You don't need to go and do all hi-fi stuff always. This could be as simple as this. This is called metric learning into CNN. Okay, so this is where you will need all this image processing skills sometimes to alter the data. I hope everybody is in sync with me. Yeah. Amit, Shakti, Akash, Dhruv, Harish, Kaushik, Kranti, Raghu, Vishnu. Are we good? Yeah. Perfect. All right. Great. So now let's see this case study where I will say it's not majorly a case study, but yeah, some of the basic concepts which will help you to work on this. So what do I have? I have got NumPy. I've got skimage, okay, which has a data. There are some images pre-stored, and also it will help us to do some kind of IO functions. Okay. Next, there are some predefined data sets which are stored inside Python. So inside basically a skimage. One of them is coins data. So I just have to call the data, coins data, and then push it onto image and find a type of it. So usually it is a NumPy array, because if you remember, I just said images are nothing but a matrix of numbers. Okay, and if you want to see how do they look like, first of all, if you want to see the shape and size of it, 303 cross 384 is that image, one image. This is how it looks like. So if you want to play around with it, if you want to see what is image 0 cross 0 has 47 numbers in total. Yeah, so this is nothing but your 47. Also, if you want to print the top, say print stuff from 100 to 150 on X side, and from Y side you print some from 25th to the 75th reading. If you do that, when you print it out, you get an image like this, which is one of these coins. Okay, now CMap defines what type of image it is. If you want a grayscale image, you can put a grayscale here. If you want a red, green, blue, you have to define reds, greens, and blues. So I have shown down the line, or else let's do it 1 minute. Okay, so this is my grayscale. Okay, this is my image. So let us say if we say 0, 1, 123, say 0, 7, 1, for example, is 130. Okay, so what do we do now is, let us say I want to show you a grayscale image. So I will say gray. Okay, in that case I'll get a gray one. If you want a green one, greens, we'll get a green one. Yeah, so these are some manipulations on CMap. Later on, there is one more set of image called data.coffee. So this is how it looks like. Now look at the dimension of it, 400 cross 600 cross 3. That means it is RGB kind of channel. Okay, next is if you want to focus more onto the the red part of it. So what I do is I keep the third channel as it is normal, and I say reds. So for example, if I say greens here, okay, it is going to give me a normal image when it is green, how it looks like. That's it. I'm just changing the filter. Why? Because I have not imported the image here. Okay. If I want to make it more greener, if I want to focus more on the green part of it, so what do? Say I change this. Okay. So if I want to sharpen it basically from the green side. So when I print it, look at this. If I want to make it more green, so instead of blue, I say greens. Yeah, it's going to become more sharper and sharper. So this is how we can play around with some of these numbers. Say I want everything, or else say I'm not sure. I've never tried this. Let me try from 1 to 3. Say 1, 2, 3. I never altered the middle one. Yeah, good. Let's not play around with this. Yeah, so this could be some operations you could use it. Next is understanding the filters that we have shown. So this is one new image, and this particular image, if you observe, if you want horizontal bars, so this is the same image as this. The only thing is we have got a filter here. If you want to sample it, or if you want to edge detect it horizontally, the first and the last one, horizontal one should be -1s, other one could be 0 or 1, not a problem. If you want to do the same operation vertically, common sense, the first and the last column should be -1s, other one should be 1s. Okay, what are we doing? Basically, we are multiplying this with our image. That's it. Next is if you want to sharpen if you want to edge detect it properly. So if you go to our PPT, the same filter is used for that camel. -1, -1, -1, -1 instead of 8. So let us say if I do 16 here, for example. Yeah, we have got back the original image almost. What if I reduce it to 2? Yeah, so at 8, perfectly it detects all the images and it does not show me black and white. You can easily see there's an 3D kind of cubes over here. Yeah. Second thing is if you want to blur an image. So if this is my original image and if you want to blur it like this, what you have to do is you have to multiply, or else you can say you have to divide something by 16 and multiply with an identity matrix. Or I will say not even 16. You can take any number here, say 1 by 5. Definitely you are going to get a blurred image as compared to this. As you keep going higher and higher, your blurriness is going to kind of vary. Yeah, good. So this is what it is majorly onto your image processing part of it. Play around with these images, import your own image and try to play around with these filters and all. You will get to know. Now, one quick question is, sometimes we are using 4x4 filter, sometimes we are using 3x3 filter. Okay, do not hesitate to use even 8x8, nothing wrong into it. The only thing is you have to know if you want what kind of feature you want out of it. That's it. Yeah. There could be many websites where these standard filters are defined. So you can download some of these filters and try to create your own values out of these images. Play around with that. If you're not able to find them on web, do let me know. I'll try to search for it. Okay. Good. So you can do some work on image, understand what it is. Now moving on to something complex now. So let's see how to do all this now, how to go ahead and do convolution out of this. So these all are the basics. Yeah, so just observe the animation that is happening on the right hand side. So on the left, we have got 3 bigger images where we are convoluting them layer by layer. So the first one was layer 1. Now we are doing layer 2 convolution. And finally, you will observe the green colored cells. These are the final outputs of your images over there. Okay, guys. And also you observe the right hand side how RGB is working onto it. Okay, so any image is nothing but a combination of RG and B, 3 layered. And finally, we are convoluting it and converting them into one particular value. So here 4x4 is getting converted into one particular value. So we are convoluting the image. Okay, good. Now, moving on, another simplistic version where you don't need to focus on all of them. So if you observe in our previous animation, we were going cell by cell. So if you see, we did not move anything extra. We are going to almost all the cells. Did you people see that? Yeah. Here, what are we doing? We are not going to all the cells. We are going to some focused areas, for example. Yeah. Now, how do we do that? There is some factor called stride. If you guys have seen your weekly videos, the professor talks about something called stride factor. What is stride? Very simple. If I have this, say 4x4 image, okay, just assume this is a 4x4 image. And if I have, I'll take a red one and I'll take a dark color. If I say I have a 2x2 filter, this will be my first filter. If I say my stride is equal to 0, that means I have to immediately go to the next. But if I say my stride is equal to 2, so what I will do is, let us say this was, initially it was intended like this. Now, if I say my stride is 2, I will skip 1 and 2. I will go to the next one. So in this case, it's not possible because it's not there. But what we'll do it, just imagine there was one more column. I will skip 2 cells and move on to the next one. So these are the examples where you can increase the stride and focus only on to certain patches of your image. You don't have to worry about the whole thing. Okay, good. So this was your convolution. Guys, anyway, still this is basics only. I'm just making you comfortable with it. Now comes the real part. How to decide number of filters and this size and that size and all that. So please remember, you see two formulas here. One is called output width, one is called output height. And as I said, we'll go in reverse direction. Okay, so first thing is what output you need from your convolution layer. First question. So let us say from this whole image, if I just focus on this tires and let us say this door, it will be enough for me to identify that this is a bus. Okay, now that's not a problem here. The problem here is how to decide what filter size I should take about. So the first thing is, I want to understand what will be output. So what you guys do is either you fixate on this or you fixate on this, whichever way you like it. We cannot have both the options. Say I fixate on my filter. Say for example, I use 2x2 filters 4 number of times, 4 filters out of that. My stride is equal to 2. That means I will skip 2 cells and move on. I don't want to do a very good sampling. Yeah. For that, what I will do is I'll take the width of my image, which is 32. Okay, minus width of my filter, which I have decided as 2. So 32 minus 2. So let me do it properly. 32 minus 2. 1 minute. So I will reduce this thickness, otherwise I will not be able to write. Width is 32. What is this width? Width of my image. Okay, a minus width of my filter, that is 2, plus 2 into padding. Padding in the sense, sometimes the image is not enough to scan because of our filter. We just saw just now when I was trying to do stride 2, it went out. So for that reason, what we have to do is we have to pad it up. Pad means add an extra layer of zeros around it. In our case, we don't need padding. So this will be 0, I will say. 2 into 0 is 0. Divided by stride. What is my stride? Stride is equal to 2. If you compute this, 32 minus 2 is 30. 30 by 2 is 15. 15 plus 1 is 16. This is how I got my convolution layer. Now, what I did was I froze this and I got this. What if you freeze this and you can get this? How? It's very simple. You say 16 over here and don't put anything here. So the equation will be 16 is equal to 32 minus filter width plus 2 into 0 divided by stride I have set as 2, okay, plus 1. Take everything on the other side, you will get your filter width. So it will be 16 into 2 is 32. 32 is equal to 32 minus filter width plus 1. So I will set 33. Sorry, divide by. Sorry?
First, I think you have to take plus 1.
Yeah, I did not take the LCM. Okay, now it's okay. Yeah. So 32 plus 2 is 34. So when 34 goes this side, it will become minus 34. That will be minus 2 is equal to minus of f of w. Minus minus cancel. So I will say my filter width is nothing but 2, which is nothing but your answer. So whichever way you do it, I'm okay with it. Yeah. You can check it up with this. Guys, quickly check it up. Is it matching here? I will not do it. You people compute it. Both the ways. Just check it out. Is it matching? Are you able to do it? Padding is 0 in this case, okay? So don't take padding factor.
Yeah, matching.
Matching, right? Good. So what if I would have taken 3 cross 3 then? Can somebody tell me the output layer width?
What 3 cross 3?
The
Filter.
filter here, instead of 2 cross 2, let us say I have taken 3 cross 3 as a filter. Now what will be my output width?
Will you need padding first?
Yeah. So that's all. Check it out. How will we do it?
It's an odd number, so can't compute.
Okay. 32 cross 32 is 2 big. Let me not confuse you guys. Let us say this is a. Let me put some brackets over here. Say 1. Say 2. 3, 4, and 5. Okay, similar to that. 1, 2, 3, 4, and 5. Good. Now, what should be my filter size? Such a way that, or else I will give you the filter size. Let us say 3 cross 3 is my filter size. Can you people tell me the output form? What output I'll get? What cross what? Use that formula. I'll give you 5 minutes. Just check it out. It'll be good, guys. You'll be able to, visualize the same thing in your convolution also, because you have to put hyperparameters there, right? What should be the width? What should be the size?
5 minus 3 plus 1.
Okay. 5 minus 3. Okay. Plus 1. Padding should be 1. What?
No, 0.
0, right? So 5 minus 3 divided by 2. So that is 2 by 2. That is 1.
Okay.
So what will be the answer?
2.
I want M cross N. You guys can type it out, not a problem. Type me on the chat one by one. I'll put the formula for you guys. Output width, okay, is equal to the width of your image. There is a lot of noise. Guys, please mute up. Still a lot of noise. 1 minute. Who is it? Yeah. Okay. So width of the image minus filter width plus 2 times padding divided by stride factor plus 1. This is the formula for output width and output height, both the same formula. Now tell me, guys, what will you do? You have to decide on padding. You have to decide on stride. How will you do it? Stride should be 1. Stride should be 2. What it should be?
Yeah, if padding is 0 and stride is 2,
Okay.
then output is 2 cross 2.
Okay. So one answer I got is 2 cross 2. Okay, perfect. So did you see 5 cross 5 image? Now we've got the best features out as 2 cross 2. Okay. Next, anybody else? Change the padding and stride. Check it out. See, guys, what here Dhruv said was he doesn't want to do any change in the padding and also doesn't want any stride. So sorry, stride is what, Dhruv? 2, right?
That is 2. Yeah.
Okay. In that case, you can say this is 3 cross 3. And if stride is 2, 1 and 2, it will come here as 3 cross 3. Then in the next layer, 1 and 2 will come like this. Agreed? And it will come like this. So do you people agree it's a 2 cross 2? Perfect. 1, 2, 3, 4. Because he has taken stride as 2. What if the stride was not 2? Then in that case, what will be the answer? Let us say stride is 1.
3 cross 3.
3 cross 3, exactly. So you will get more features, 3 cross 3. What if you take a padding, Dhruv? What if there was a padding there? Let us say I take a padding of...
If it is padding and 2 stride, it gives 3 by 3.
Okay, perfect. Perfect. So now I hope you are able to get it. It is not always necessary that to pad or to have more strides and all. It all depends on your filter. So you baseline one of them. Either you baseline this or baseline this, and then choose the other one out of it. I will always say baseline this. Easy way. Okay. Is everybody in sync with me? Everybody got this, guys? From next week, we'll not be able to discuss all this. Okay. So when I say something I've taken in the code, you people should be able to identify what is stride, what is padding, how I've taken this decision. Okay.
Padding and stride are higher.
So Amit, yeah, kind of, yes. Anything else, guys? Anybody wants me to repeat? No? All right.
If padding is 1, then what will be the effect on actual image?
See, if padding is 1 through, padding is like putting zeros. So you will get one extra white colored patch onto that. That's it. I will say padding personally is not good, but sometimes our images are of some odd size, no? To match up the filter, we have to do padding. Correct?
Okay.
Yeah. It is like a fake white colored layer unwantedly pasted onto that.
So Krishna, padding would be used if the image is not like in square in shape or something.
Correct. Agreed. So here we have taken 5 cross 5. Now what if it was 5 cross 6? So let's try that out. And guys, remember, it's very difficult to visualize all this. So don't strain yourself if you say, okay, I'm not able to get it. Definitely one shot will not be able to get it. Say this is 1, 2, 3, say 4 and 5. Okay. Now if this was 5 cross say 3, for example, 1, 2 and 3. Okay. Now my intention here is to use a 3 cross 3 filter. Is it possible? First of all, just check it out, guys. A 3 cross 3 filter, how it will look like. So let me increase the thickness. So it will be 3 cross 3. Yeah. And if I say stride is equal to 1, now what's going to happen? To have one more 3 cross 3, do I have space? No. So in that case, what I have to do, I have to add one extra padding layer on the whole image. Okay. So usually you will see in all the codes is usually by default they take a padding of 1 or 2. It's okay. Because we are not sure, sometimes we'll not be able to visualize this. So it's okay to take an extra padding, doesn't matter. Sometimes we don't do it. If we don't do it, if it is an issue, it will throw an error. Anyway, it will notify us. So once it notifies us, either we change the size of filter or we change the size of image immediately. Good. Vishnu, is okay now?
Yes.
Got it? Okay, perfect. Okay, so moving on now. So this is very important. Please remember, so when I share this, keep it with you. And this is very handy also. It's not a big deal. Okay, so this is what is padding. What it will do is it will unwantedly add an extra number. Usually it is zeros, so it will not impact us much if we do pooling. Because if you remember what is pooling does is pooling will pull out the best features. So if I pull, let us say out of this, anyway the 0 is going to be ignored somehow. Okay, so it will not affect much, but at least it will not hinder us from doing. Yeah. Next is pooling layer. So we have 2 types of pooling available. I will not say that's it. You can have your own version of pooling also, but these are the most popular ones. Max pooling, average pooling. So average in the sense you take average of all 4 of them and you pull as one number. Max is take the max of it. So in this case it will be 112. Okay. Good. Yeah. Guys, one more thing. Sorry. This is the max pooled image. From here it is got. So if you see 20, 30, 37 and 112. This is how we got. If you still want to max pool this further, then answer is 112. Okay, I did not see that. I'm sorry. This is coming from here. Okay. This one also, if you observe average pooling. So take an average of the first one. Let's check whether it's in sync. 20, so 32, 40, 52. 52 by 4. Correct? It's 30. All right. So what else we can do? Anybody? Any idea? We can use any other computation.
You could do min pooling too. I mean, since we're doing max.
I mean, see, here we want to extract the best features. For mean pooling, you're saying we'll extract the worst feature. Okay. If in case we want to blur an image, let us we can do that. Okay. Let's see. Let's see that. I've never tried it out. Okay. Let's see that. But yes, if you want to spoil an image, if you want to spoil certain part of an image as a blur part or something, yeah, you can take that mean value also. Good one. Anything else out of these four numbers?
Can we take
Sorry?
min max?
Min max. How do we do that?
Or we can take a kind of maximum value minus the mean.
Okay, perfect. Perfect. Let us say in this case it will be 20 minus 37. Okay, nothing wrong. Yeah, but you have to design your own. At least it will not be present in the standard function. So you design your own function. The standard values are these two: max pooling or average pooling. Good. So that's it. Yeah. So now how it looks like. So a fully connected layer. So what do we have? We have got your
Hey,
input.
Krishna, one
Yeah.
quick question.
Yeah.
So where do you use max pooling versus average pooling? I mean, how do you make that decision?
Okay. See, use max pooling onto, let us say you have a low sampled image. So let us say the sampling here is 2 megapixel, for example, and the sampling rate here is 16 megapixel. In that case, what's going to happen is the images which are nearby, they'll be almost similar itself. So in that case, you can take an average, not a problem. But if you feel the sampling of your original image is not that great, you do max pooling. Extract the best out of this feature.
Okay.
Okay. See, I'll tell you why. Let's go back.
Are you saying that if the image is higher resolution, then go for
average,
and if it is lower resolution, then go for max? Okay.
Correct. See, if you look at this one, okay, this is only 0 or 1, or I'll say black and white. So now, if I have a filter which is focused onto this, which one you think is of our importance? Guys, max pooling or average? Max. Correct. We need to know where there is a black pixel. Definitely, we are going to get this. So this 2 cross 2 image now is represented by 1, which is called black, which is nothing but black in number. Now let us take one more example. Say, for example, you are having your stuff into this. Now, what is maximum number over here? All of them are 1s. So if you do max pooling onto that, what you will get? 1. Or if you do, let us say, average onto that, what you will get? Average is
3 by 4.
3 by 4.
0.7.
Correct. So you can do this or you can do this. So anyway, the answer is we got to know that majority of the features over here are 1 itself.
Yeah.
We know that. So this is some example of average. This is an example of maximum.
So I think the other difference is if you do average pooling, then especially where, for example, you have four black. I think that difference between the different values would be more of a range.
Okay. Let's take an example. Say, where do we get 4? Here we don't have it. So let us say we take something like this. Yeah, we take something like this, 3 cross 3.
Yeah.
Okay. So if we take an average of this, yes, I agree with you. Yeah. Kind of. Yeah. Works out. So we have got 1, 2, 3, 4, 5. 5 divided by 9. That will be our average. Yeah, correct. Okay, good. So it's, guys, you understood what he's trying to say? He's trying to say that you will exactly get the number. How many blacks are there? How many whites are there? That's it. 5 by 9. So the denominator is nothing but your total number of whites available out of 9.
Yeah. So the reason I asked that is, so in essence, you are getting more information, right, into the next layer, right, or into the next.
Correct. Correct. So we are basically taking the best information out of this and moving ahead. Here in our case, guys, best information means black. Worst information means white. That's it. You don't want white out of this. Now, are you guys comfortable a little bit with the filter part? Now you get the point why we need filters, what filters can do and what actually will do. We just need the best features. We don't need extra background stuff from this image. Let's not do it. Good. So this is one way to represent an image. If you want a little bit more simpler version, you can do this. What I feel this image is a better representation of where you can take out certain features out of an image and directly classify that it's a car, truck, or van. This could be we will see this little later in our course. You don't need to go and scan everything. Certain features will take it out completely. Okay. Good. So this is an example I will say of RCNN, Regional Convolution Neural Networks. We will see down the line. This comes in around third or fourth week. Good. So we have done almost everything which was needed. So next session, what I will do is we will start with implementation of the CNN, and then we'll move on to a very simple topic called transferred learning. So just to give you guys a very clear, a quick 5 minutes idea onto next week's videos, don't worry. Those VGG, LXNet, FlexNet, then ImageNet, ResNet, all those nets that are produced, no, they are produced by some people who have done a lot of permutation combinations to find out the best combinations of convolutions here. You know what it does? It basically, whatever image you give, no, it tries to classify you properly. Now, what has happened, since these neural networks have one certain computations, they are standardized now. What does it mean? Their weights are stored in an HDF format. Now on, what you can do is you can build up your code. You can download their weights. You can ready the architecture for them. You can automatically download their weights, and you can build your own FCNN at the end. So whatever you download, no, that will be only convolution neurals. The last layer, the last 3 to 4 layers that we are supposed to do, our own layers, that is your fully connected neural network layer, is what you have to design. That's it. Your network is ready. You don't have to take a pain of building your own CNN. This is called transferred learning. That's all is the topic for next week, whole week.
So which means the weights are already initialized?
Yeah, already, not already initialized, I'll say. The weights are already ready. The filters are already ready. All you need to do is pull it down and then rerun it. See, it's like you cannot train them. You can train this. So when you do your fully connected neural network, when you train your model, these are non-trainable static stuff. This will be your trainable stuff. That's it. Do you think our problem will be solved? Yes, right? You don't have to take a pain of designing a very complicated neural network. Neural network is good. We get it. But you don't have to take a pain of designing all this. You are getting this ready-made, this part. This one, what you are supposed to design. And you people are very good at this now. Got it? This is called transferred learning. It's like one of you design a code, generic code, and give it to all of us. We just change the input data and run it as our classification model. That's it. So don't get confused if the professor is showing LXNet. LXNet is very big. You just have to understand that this is a ready stuff. We are importing it and running it on our model, so that I don't have to go through a pain of training my own model. And usually the parameters are something like 6 million, 10 million, 16 million parameters. That's the reason we don't need to train them. We have to directly get them. Ready-made tools.
Krishna,
Right?
can you explain with an example? I mean, so would you say that maybe you have a corpus of vehicles, right?
Yeah.
So you would get kind of a model which already can identify vehicles. Correct. Because it has learned, it has gone through a corpus, and then you just add maybe a few more layers on that just to look at maybe if your problem is to identify a Ford vehicle, then you work on that. Is that way?
Correct. See, Vishnu, have you heard about framework anytime? in
Yes.
our industry? Yeah. What's a framework?
Framework is basically like a guideline of how to do work.
Yeah. Okay. So, for example, let us say you are doing lean.
Maybe skeleton, something like that. Yeah.
Okay. Or let us say, have you heard about A3?
A3, no.
A3 implementations under lean. It's a framework.
Okay.
Let us say you have a service and you want to improvise your service. So what do we have? We have current scenario. Let us say what is the service's current scenario? What is the problem you are facing there? How you intend to solve it? And what is your timeline to solve it? Let us say there is one framework available to us. What do you need to do when I give this framework to you? All you have to do is you have to put in your data. That's it.
Yeah.
Correct? Something like this, you can imagine that there is a neural network which has its own corpus, which was trained long back, which was approved by a lot of data scientists long back, which kind of is similar to what you are doing. Let us say the corpus over here was a lot of image or object identification. Any kind of object could be identified. Now we already have this neural network ready. So what these people have done is they have actually frozen their weights for us and converted them into an HDF format.
Okay.
Now what do? I take these weights as our framework. And now I just put in my data onto that. That's it.
Okay.
And use them. That's it. So I'll give you some of the popular ones which I am comfortable using is VGGNet, MobileNet. So what is MobileNet? You use it every day on your phone. If you people observe, your phone tags your face. It is not possible to put very heavy stuff on your phone because of computation. So we have simplified VGG into a very lightweight model called MobileNet, and we are using this ready-made. You can use ImageNet. You can use RESTNet, RESNet. We will see down the line what are these things. But in the next videos, you are going to see this. Okay, good. So the video next week should be very simple. So once you have got the concept of filters and convolutions, next week should not be a tough one. All right. Week 1 I feel is the toughest, and week 5, 6 I feel is the toughest. So middle of these weeks are pretty easy. We should not be a problem. Okay. All right, guys. So I think I'm done. If you have any questions, do let me know. Else, let's close down.
I want to ask one question on the project because I think when I was looking at the data, there were some missing values. So for neural networks, do we need to do any imputation?
No. Missing values in what? Images.
I think there was some data also that was provided in one of the case studies, I guess.
Okay.
And it has many n values. I'm not sure if it was that project only or if it's
No.
a different project.
In this project, there is no missing value, and there is no imputation to be done. Okay. Yeah. Okay. Before moving on, I just wanted to ask you one simple thing. Let us say I have an image, which is say 64 cross 64. Okay. And over here, I have a neural network. Say the neural network is having 512 inputs, for example. Okay. And I will say again, they have their own hidden layers. And finally, we are converging this neural network to say one classifier over here or two classifiers. We don't care. So the pointer over here is we are supposed to input 512 inputs. My current input is 64 cross 64 cross, say it's a grayscale image, so 1. Can you guys help me to put how many convolutions I need and what will be the size of my filters, max pooling and all that? Can we do this quickly so that I get to know that you people are in sync and we can go further onto this. So let's start putting the blocks over here one by one. Yeah. Okay. So let's put the first block. So what I'll do is we will write the filter size over here, filter size and max pooling, and finally we'll put here what is the total number of we have got over here. Yeah. So let's start. How to do this? How to design this filter?
3 cross 3 filters.
Okay. So we'll start with 3 cross 3. Okay. And how many I need, for example?
64.
So how do you decide on that?
I think
So yeah, so
just
one
a
hint from my side is this particular term we have no clue onto how many we need and all. So for now, you keep it empty. It's okay. But at least let us say you have decided 3 cross 3. So if I have 3 cross 3 here, what will be my output here? So what will be the output of my, what do you say, filters over here?
So it is 64 plus 3 minus 1.
Sure.
Yeah.
Okay. What is the formula? Width of the image minus width of the filter plus twice of padding divided by stride plus 1. This is the formula. Okay.
Okay.
Yeah. So now start putting it. So first of all, I will say, okay, stride is 1 only. I'm not changing my stride. And padding I have not done. 0 padding. So what will be the size here?
So 64 minus 3 plus 1.
Correct.
62.
64 minus 3 is
61.
61. 61 by 1, so 62. So I can say the output that I'm going to get will be 62 cross 62. Now, if you look at this and if you look at this, it does not make much sense to me. Why? Because we have not reduced much. So to reach to 512, so 512 means when I multiply these two, I should get 512 somehow. So if you multiply 64 and 64, you are going to get 4096. Yeah. So this particular thing is not going to help us. So in that case, what do I say is this transformation is not that great. Now to reduce it, what I will do is either I'll increase the size of my filter. It's not fair. Or else I will increase my stride. So let us say I increase my stride to 4. Okay. Now can somebody tell me?
So it's an odd number.
So
Odd divided by 4 is point values.
64 minus 3, or else let's be fair. Okay, 64 minus 2, 2 cross 2 will do, no problem. So 64 minus 2, that is 62. 62 by 4, that will be 31 by 2, that is 15.5. So say 15 will take. So 15 plus 1, 16 cross 16 we can get. So that is a good transformation. So now what is the problem here, guys, is this is not an easy task to do. So on purpose, I took these numbers so that it is not an easy task that, okay, I have these things in my mind, I have some input, let's try to convert the input to something. And also it is not easy to decide how much is the size of the filter, what will be my padding, what is this. So it is good to know the formulas and do convolution onto simple images. But when you go on to larger images, say 1 megapixel image, for example, and if I ask you guys that, okay, my image is 1 megapixel, can you design a CNN for me, which should intake 512 over here? So it'll be, you can do it, not a problem. You will be able to put one by one all the filters, or else even you'll back propagate and try to change and all. Good thing, nothing wrong. But it'll take a lot of time. So to avoid these confusions, what we do is we use a concept of machine learning. Concept of transferred learning. I'm sorry. Now what we do in transferred learning is, let's try to see that. Can any of you name one library from machine learning which is the best, like which has almost all the algorithms or all the functions that we dropped? Like I'll give you an example of SVC or KNN or decision tree or random forest. Which library we used for?
Scikit-learn.
Scikit-learn, right? Let us say we use that library to do that. Now, what is exactly scikit-learn? Can't we program a SVC using for and if loops? We can easily do that, right? But why don't we do it? Why? Because we already have a function, somebody has returned it, somebody has coded it in a generic way such that it will help us to input our unique data, and according to that, we'll get a customized output. It is solving my purpose. So what we do, we call this. Now, when we call this particular thing, what are we doing? We are getting the stuff ready-made from them. We are getting the hardware ready from them. The only thing is, we are getting the infrastructure ready from them. Only thing what we are doing is we are putting our data. That's it. Now keep this in mind. Let us say there are certain readily available convolution networks. I'll show you down the line which all are there. But say there is one convolution network which is readily available. And say you have stored the weights of these functions in an H5 file or HDF file or whatever file we can. We have pickled all of these weights. I'm not saying the entire network, I'm just saying the weights of the network. Weights in the sense what is the size of the filter and what is whatever we saw in the above example, which we kind of did not, if we are not able to clarify, weights are there. Now what do? I ask or I request this particular model to import the weights to my model. So let us say this is your model. You have created an exact replica of this model. Now what you do is directly pick up the weights and drop it in your infrastructure. Okay. Once you drop it in the infrastructure, what is remaining now? So you have just got convolution weights. What you have to do now? You just have to build your FCNN here. That's it. Fully connected neural network. We can easily do it, not a big deal. So this is what we do on the industry side. We do not write much of the CNNs. And even if we are successfully able to put a CNN of our own, training it and correcting it will take a lot of time, to be very frank. So I will say majority of your implementations on the industry point of view, you will be using transferred learning. But in this certification, at least for 1 or 2 or I think 3 weeks, we will be handwriting some of the CNNs. And after that, we'll start picking up CNNs of our choice as this. Okay. And that example that we saw, we will see it in the code. Let's see how we can solve it up. Okay. Any questions on transferred learning? The concept part of it, I will show you how we do it. But this is what overall goes around. We directly take the weights and use it. Okay. Any questions? No?
No, sir.
Perfect.
No.
All right. Good. So now let's try to use a PPT. So today I will use one PPT where they have mentioned a lot of networks. Now for first point, it will be very confusing immediately. So don't expect I don't expect you guys to master this networks in one module itself. What we are going to do is I will pick up each network every week. So let us say in today's session, I will pick up VGG, which is the most important one. Probably next session, I could show you something on LX, something on LENet, or I can give you something to do on LE. And post that, we can go to the complex networks like ResNets, Google ImageNet, and all those things. Okay. And this is not it. There are so many available. Okay. So let's start. Yeah. So for today's agenda, we will start with CNN architectures. So we just took an introduction of what is CNN. CPU versus GPU, we know this. I'll not go in much detail. And the most important, transferred learning. Now coming to the architecture of CNN, try to push our formula here, whatever we saw, right? So Harish, I think this will solve our problem, except I will say it will not solve the problem of what is the math behind selecting the number of filters. I'm still working on this, guys, and give me a week's time. I'll try to find out some paper or some logic behind this.
Okay, Krishna.
Yeah?
Yeah, okay, Krishna.
Okay,
Even I will search for that.
Yes. And also I will request our Great Learning, I think the professor who is teaching this, if he can share some papers with us. So Frank, so far I'm not able to find any particular good reference where I can say that this is the math behind selecting these filters.
Maybe what I feel is, as you said, they have also decided first what is the final fully connected layer, and then they decided on this number 6.
Reverse engineered it, right? Yeah.
Maybe I also think that, but I'm not sure. Yeah.
But still, there should be some logic, because randomly I cannot put anything here.
Yeah.
I feel it is a little weird. Okay. Also,
Yes.
I tried. See, if you see here, what does it mean is we have 28 cross 28 6 filters. So what if I multiply 28 into 28? Okay. So let us say I have 32 into 32. Now, when you multiply 28 into 28 and then add it 5 or 6 number of times, I'm not sure we are going to get the same number back, to be very frank. So what is happening is, as per our analysis or as per our knowledge in CNN, what is happening is we are converting, say, if the stride is 1, then definitely you are going to have the network which look like this. So one particular image is getting converted into many features. That's what the 6 thing shows. So I used to take it as feature maps. I used to say there are 6 feature maps available. That means I can pick any one of them, put it to one of my convolution network, fully connected networks, and try to find some information out of this if possible. Okay, this is what I used to take, but now I feel that is not enough. I need also to know how to do this. So apart from this, in today's session, let's ignore this. But apart from that, you can directly see 35 minus 5, that is 27. We are saying stride as 1, so divided by 1. Padding is done 0 plus 1. So if you look at it, 28 is the 1. If we still do it, 28 minus 2 divided by 2 plus 1, you are going to get 14 out of it.
Yes,
The
yes.
formula holds pretty good onto this part of it. So at least 50% of the stuff is solved. Except now if you ask me, okay, how they came up with this network now. So I will say it is a lot of mix and match trials happening. So it's not a one-shot job that, okay, they decided this and they got the best accuracy. Because if you look at it, they are currently working on 60,000 parameters. Okay. Now what are these networks and how we can use it? So if you look at the highlighted area that I am just drawing, this is what I am interested in. So if I have a ready-made network, open source network for all of us, which can identify handwritten digits. So your neural network project, if you remember, 7, 6, 5 and all. I know they were not handwritten, but anyway, we can correlate this. If I can do this, what I can do is rather than writing KNN, rather than writing the neural network, what I will do, I will ask this LENet weights to be dropped onto my network and then design my own fully connected neural network depending on how many number of outputs I have and take it forward. Okay, so these are the features. Now, if you expect to use the readings onto a face recognition system, then it will not work, to be very sure. Why? Because please remember, this is what is important. So why am I specifying is tomorrow when you're picking up this, you should know what it will solve. Okay. All right. So this is it.
This only works for the handwritten digits. Nothing else we can apply.
Yeah. If you are importing the weights. Okay. If you are replicating this network and giving face as an input and trying to get an output and just check how it is. If you get a good output, then you can say that yes, it works for face recognition also. Correct? But for importing weights, it works only for handwritten because they are trained only on that data.
Okay. So it means like if we are using it ready-made, then we can apply it only for the handwritten digits. But if you are trying to replicate the same thing, same architecture, then we can provide the face as whatever inputs we can.
Perfect.
Correct?
Perfect.
Okay. Yeah.
Perfect. So when I deliver today's code to you guys, no, so in today's code, we are going to use VGG. We are going to import VGG and do it. So what you guys can do is you have the network in front of you. You pick up your older data, that MNIST or SVHN data from your previous project. You pick it up, try to replicate this network and see what you are getting as an output. Simple. Okay. So how do you replicate? You use the same values, and at the end, when you're connecting this fully connected neural network, you multiply these 3. That's it. That will be your input. As simple as that. Or else, if you don't want to multiply all 3 of them, 5 into 5, 25, and you give 25 as your batch size. Okay. So at one shot, 25 will be picked up, put it in, and moved out. Or else, if you want all of them, all the filters to be put in at one shot, you can do that way. Or else, you can pick up one by one and do it. Yeah. So try this out. Good. It's good if you play around with this particular network because it's a very basic one. So if you're good at this, then you will be good at the next one also. So if you look at the features, it is for handwritten. It was published in 1998. So I will say it is an outdated algorithm, but I have used this into multiple tasks where I have to identify simple digits. It works perfectly good. No problem at all. Yeah. 60,000 parameters. If you are looking at your current Colab, then I will say it is not a very big network. If you're looking at Jupyter, yes, I will say it is a little heavy on Jupyter. The dimensions of the image decreases as the number of channels increases. So if you observe, the dimension is decreasing, but number of channels is increasing. Or else I will say rather than channels, what happens is when we say channel, we get confused with grayscale and RGB. Another case, I will say, call it as feature maps. So each square that you see, 5 cross 5 square, carries some kind of feature. That's what it means. The activation function used in the paper was sigmoid and tanh. But now what we do is you don't have to use always sigmoid and tanh. You can use ReLU now. You can replace both of them by ReLU. No problem. It will work good. All right. So this was your, how do you say, this network. Okay. Moving on. Okay. So some pointers here is it's a 10-way neural network classifier. It works properly on 0 to 9 data, handwritten digits, tolerant to various transformations like rotations and scale. So if you do augmentation also, it's going to work good. So our SVHN data will work pretty good onto this, no problem. Was used by banks to recognize handwritten numbers and digitized checks. So still on a very basic level, yes, they do it. So what they do is if there is a check, let us say return, if there are certain numbers written on the check about what is the payment, then let us say there is a signature over there or something. In those cases, if you want to identify the digits or if you want to identify the check number or the date, you can easily put the check below the scanner, you can pick up the data and process it. Very simple. You don't need a very heavy hardware for this also. And it's a 4 weights layer. So if you observe here, 1, 2, 3, 4. 4 weights. Okay. Now, if you guys have understood this, one quick question for all of you. Can somebody tell me if I put an Adam as my optimizer, let us say ADAM, Adam. Adam is going to work on this or on this. Take some time, think about it. How my back prop is going to work. Is it going to work on only fully connected or it's going to work on everything?
I think for everything.
Perfect. And what if, Dhruv, I do, okay, so in the first case, if you are using the whole network as it is, yes, back prop is going to work for both of them. I'll show you how back prop works for this. You people know how back prop works here. Okay. Now, leading to this, another question. What if I import the weights to my network and I use my own fully connected neural net and go further? So in that case, back prop is going to work on both of them?
No.
No. You got my question? Let me repeat myself. What if you have imported? So this is my import of weights from the LENet website to my network. And after that, I'm building my own fully connected neural network here, something like this. And now if I put Adam, Adam is going to work on this, or Adam is also going to work on this also.
I think it will work only for that part which we have customized, not for the imported part. I feel so. I'm not sure.
No, perfect answer. Why? Because if I backpropagate and if I change my weights, there is no fun of importing the weights. Why we imported the weights? Because they were standard weights. These were already learned weights. So if I backpropagate here, it's not going to work out. So we have to make sure that if we do it, we freeze these panes. Whatever we have before this, we have to freeze them. They are not editable, and this side will be editable. So I think in 3rd or 4th week, I will show you how to do that. Yeah, but this is a very generic question. So when you go for an interview or when you look at some of the most important deep learning, convolution, or CV questions, this is what they ask. Okay, so this is one concept. Now, keeping this in mind, let's try to complex, or let's try to make one more model out of this, which will be your LXNet. So LXNet is an extension of LENet, we can say. And why do we need this is, let us say the earlier one was able to identify 0 to 9. What if I want to identify some of the objects or some of the faces or any other thing which is not even number, which is more than a number? If I want to do that, I need a bigger architecture. So what they have done is they have simply increased the layers of convolution and pooling. That's it. Okay, there is no other difference. And if you observe, even there, FCNN will differ because of number of changes. So the goal for the model was the ImageNet challenge, which classifies images into 1000 classes, for example, has 60 million parameters compared to 60,000 parameters. So when this increased, okay, so when this increased from 60K to this one, even the capacity to classify images increased for us. Now it could be anything. If it comes under those 1,000 classes, you can use the weights ready-made from this network to your network. It uses ReLU activation function default. And this paper was convinced the computer vision researchers that deep learning is so important. Fine, this is blah, blah, blah. And this is how they have done this. So if you want to see the tabular structure, they have taken 1, 2, 3, 4, 4 heavy layers. But if you look here, one minute, something is wrong in my diagram. If you look here, there are more convolutions. Give me 1 minute. So we have one convolution, we have another. Yeah, we have a convolution here, we have a convolution here. This is no convolution, no convolution. There is a convolution here, and there is a convolution here. So I have 1, 2, 3, 4, 5, 6 convolutions and 2 similar layers. Okay, there is no change over here. All right. So this is it. Okay, so this is what is your LXNet. It's an extension. Please remember this particular number. It is very heavy. Okay, let's go to the extension of, okay, what made LXNet successful? So I will say architecture, I don't believe that, because anything you mix and match, definitely you're going to get something out of it. We can say overlapping max pooling. So if you observe here, what is overlapping max pooling is, if you observe, we are not doing in middle. We are doing for one, we're doing for another one, we're doing for another one. Okay, this is what it means. You don't have to do always max pooling after convolution. ReLU function was universally used. It was very simple. Dropouts, cropping, data augmentation, and inference augmentation. So inference augmentation, I will say, is okay. Let us today take the case study and revisit this particular part of it. But more or less, if you look at the important part, this is what it solves. This is okay. It's not a big deal. Not a big deal. Yeah, this is what you need to remember about max pooling. You don't have to do always. And I think architecture, fine. So these are some important success factors of LXNet. Okay. Next, coming on to VGG. Now, increase still more number of pooling and convolution layers, you will end up with this particular network. And let's confirm what was the image size here, 227, 227, 3, and this was 9261. And here we have 224, 224, 3, and fully connected is 4096. Okay. So if you observe, again, what you do is you increase the number of convolution layers, modify LXNet to make something called VGG. 16 is not the latest version now. Now we are having 19, but both of them work equally. So for me, if I've done some implementation, if I'm using VGG 16, it gives me a good accuracy. I don't go to 19. It's okay. 19 is a little heavier than 16. Yeah. Other all remains the same thing as our LXNet. No change after this. So what are these what are these networks? Is there were some challenges in which some of these people came together and built this up. That's all. If you ask me how, it's about mix and match, to be very frank. Yeah. Okay, this is of no use. Some of the important things is from 60 million, now we are jumping to 138 million parameters. Yes. It holds a total memory of 96 MB per image for only forward propagation. Most of the memory are in earlier layers. So if you just observe that you have two things, one is your network and one is your FCNN. So we can say that most of the memory kind of goes away here. This is the heavy part, this is the lighter part. Okay. Number of filters increased from 64 to 128 to 56, 256 to 512, and 512 has been made twice. So they are just replicating some numbers from the network. So you don't have to remember all this. Whenever you want to use it, just come back to this particular thing and try to replicate the network. You have the numbers ready. You just have to put it in the Keras add dense keras. That's it. Whatever that particular command you have to use. And if anybody is interested in paper, this is the paper attached. I will say it's a little heavy, so first get comfortable with all this and then go on the paper and have a look at it. Okay. And as mentioned over here, there are two versions, 16 and 19, but more or less it does the same job. So whichever you want to use it up. Okay, good. Now comes a little problematic part. So now these were the three simple networks which we can visualize. Now comes a little different network. We call it RESNet, RESTnet. Now, my question to all of you is, what if I want to use this particular hardware, whatever we have done? Okay, it's a very good network, agreed. But now I want to use on a handheld device, and within fraction of a second, if I give an image, no, within fraction of a second, it should give me some output, or it should put a square around my face and say that, yes, we have identified it as you. Will your device be able to hold this up? Guys?
You mean computer?
Yeah, so if you have a mobile, for example, so will your mobile be able to hold this up, this heavy processing?
Maybe as you said, there is another architecture called MobileNet.
MobileNet. Oh, that's why you, okay, yeah. MobileNet is an alternate version of it, yes, but let's not go there. Let's try to think what we can do here, or, okay, my example is not corrected. Let me try to create another example. So guys, let's take one more example. Let's not think about computation side. Let's say I am currently having one image which needs to be given as an input, and immediately within some time limit t, I'm supposed to get the classification output along with some tagging or some classified output. Now, as you saw, the number of layers are more over here. So we had one layer, another layer, third layer, fourth layer, like that. Let us say so many layers are there. And it is going in a sequential manner so far. We have not broken any of the sequential, flow as of such, correct? Now, what if I want to increase the speed of this network? What should I do as per you? Let us say I'll take 5 inputs from you guys. The current time is t, okay? I want to make a time period saying that t new. Now, t new should be far less than t. That means it should be faster. What should I do?
Are you talking about embedding software like Coral, NVIDIA Jetson Nano?
No. Let's not go there, Dhruv. Let's say if I make some changes in my current network, I should get some good speed. I got it that this network is very good. Perfect. We got that. I don't want to lose it. What if I am not happy with the time part of it?
So maybe to increase the hidden layers, I mean, it might reduce the time.
If you increase the hidden layers, then the time will increase, right?
Yeah, right.
But simplify the input and output also.
Exactly. So how do we do that? You are perfectly right. How to simplify this now? Distribute, okay. So Kaushik, you're talking about parallel processing, something like that? Yes? Okay, yeah. Fine. That could be a possibility. So let me write down. What if I have a parallel processing? Or I am having a Hadoop environment where I'm doing parallel processing. Okay, fine. This could be one possibility. But we are not changing the architecture, right? What we are doing is we are distributing the data. I will split my data into many and then I will distribute parallelly onto multiple networks. Okay? What can I do in my network? Okay, let me give an example. I think then you guys will be able to pull out something. So guys, let us say when this is my computer screen that you are able to see. Okay, and for example, in front of my screen, I show you half of the image like this. Okay, now as soon as you see, so just imagine that you are not able to see this particular part of it. So as soon as you see this thing in my screen, what do you assume it to be? What shape you assume it to be? Everybody will say, yeah, it's a circle. Okay, or else if I just, So in the time frame, if I am just scrolling one image onto my screen and you are able to see only half part of it, but yet you are able to describe it, right? What it is. You will have some assumption in your mind that yes, he is trying to show a kind of square. And as soon as it comes in the picture in my frame, everybody knows, yeah, it's a square. Keeping this analogy in your concept, what if I can give some early inputs? Say that I can take up the output of this and throw it to this. So definitely it's going to go here. So let us say the output from here to it goes here. It takes some time frame t. Meanwhile, parallelly, I throw the output here also. So what's going to happen? This particular network is going to make some outputs and start throwing it in future. So till our image is getting processed here, our output would have reached here immediately. So there are certain cases where if you look at certain parts of your image, let us say in this particular part, this, I'm sorry, one of the feature map looks like this. And as soon as I give this feature map, let us say the feature map was here, as soon as I give it to the next network, and if it gives next to this network, we could be able to identify that this looks like a cat, possibly it's a cat. So till I get all of my feature maps, all of the shrinking and all, I would have easily identified this. Are you able to get it? Kaushik, this is something similar to what you said, but here we are not splitting the data parallelly. I am forwarding the data. I'm avoiding one of them and forwarding it further. Able to get it, everyone? Amit, Dhruv, Shakti, Akash, Harish, Kaushik, Kranti, Raghu, Saurav.
Yes, Krishna.
Logical? Yeah?
Yeah.
Okay, good. So this is what RESTnet does. Now the only challenge, so nobody challenged me here saying that, okay, fine, if I do that, let us say, as I said, there is one convolution layer, max pooling layer, convolution, max pooling, convolution. There are so many like this. Now what I do is, by default, there is a sequential order. Yes, it will follow when till it goes to a fully connected neural network. But if I take an output from one node and give it to say this node, don't you think the filter is going to mismatch? Agreed? So let us say this is 28 cross 28 cross 3, for example, the output. And when we reach here, it could be 16 cross 16 cross 6, for example. Don't you think this is going to mismatch? Yes or no? Because in convolution, every step we are reducing the size. Agreed? So the output of this particular one is going to mismatch with the next or next to next one. So what we do to solve this is we keep the same stuff for all of them. That means we design a network which has same filter sizes, same activation functions. All right. This is how it looks like. It looks pathetic. So if you look at it, it makes no sense as of such. But yeah, try to understand that we are giving an early output. We are skipping one convolution and we are going further. All right. So it's a very, very deep network as suggested. Because of vanishing and exploding gradient problems. Now, what do you mean by vanishing and exploding gradient problems? So I will show you down the line. So let us say I ask you, guys, you have done the model. All of you have cleared the model on statistics. Yes. The first module. Yes. Can somebody name the 3 distribution we have done in the statistical module? Can somebody name this?
Normal distribution.
Okay.
Poisson distribution.
Okay.
And there's a
binomial distribution.
Okay.
Binomial distribution, yes.
Okay. And one more. Okay. I underestimated you guys. Yeah. Now 5.
Distribution, chi-square distribution.
Oh, bapre. Okay, good. Dhruv remembers everything. Okay, good. Okay, what if I say what were the statistical tests you people did? What are statistical tests we know here?
Two-way.
T-test.
T-test.
ANOVA.
ANOVA. Perfect.
Z-test.
Goodness of it.
Sorry?
Goodness of it.
Okay, fine. Okay, then you guys are ruining my example. Okay, see what I was trying to show you guys was, okay, good, you people remember. My other batches said we don't know. So it helped me to explain my stuff. See what happens is, guys, when you have a particular data which is passing through a multiple neural networks, now let us say the data is entered here. It went through a lot of these convolution, non-convolution layers, whatever, pooling layers, whatever layers, and finally it came here. Now say you found a loss here, dou L by dou of weight 1. So let us say this is weights. So what you do, immediately you go here and change the weights. If still in the next propagation, if you are not happy, we immediately go back and change the weights. At least I can say that at least till here, if I change my weights, I'll be able to at least control them. So what do I need to say is, the weights which are there in the earlier part of the network, if you have a very deep network like this particular weights are going to vanish away. More or less, they will make not much significance to the network, to be very frank. This is called the problem of vanishing gradient. We are going to revisit this concept in NLP next module. Under NLP, we have a network called RNN, recurrent neural network. So there is a problem, same problem. RNN is a deep network where we will face the same issue. And to solve this, we use a network called LSTM, long short-term memory network. So we'll have some memory where we are going to store these weights down the line. Okay. Now, if you look at our ResNet model also, this is a very deep network. And whenever you find the word deep network, always say that, or always remember that vanishing and exploding gradients are going to be a big issue. Vanishing gradient for these people, exploding gradient for these people. Their gradients are going to go pretty high because a lot of changes will happen, which is very near to the output itself. Okay, so this is what is your ResNet. Next, I think that's all you need, more or less. Yeah, so this is what is the important points. So the architecture of ResNet 34. Now you have many versions of this. This is ResNet 34. There is ResNet 150. I have seen ResNet 50 also. The concept is changed. Only thing is the number of layers that you are going to see here will be different. The deep layers. Okay. All are 3x3 convolutions and same convolutions. No change. So we keep a uniformity. Keep it simple in design of the network because we don't want to play around, because I want my output to work on any of these convolutions. So I will keep it as simple as possible. Okay, and if you observe, there are no fully connected layers. Okay, and I think that's it. That's all. And one thing to remember is the dotted lines in this case, when the dimension. Okay, 1 minute. Where is my dotted line? Concept. Okay, so there are two things. I'm not sure if you are able to see the dotted lines. If your input and output are kind of tracing each other, that means you can switch off some of these lines. That these are optional connections that we have given. It's not necessary to take each one of them and throw it. So if you are designing it that you are surpassing only one neural network, you can have some of them as dropouts, saying that we don't need them basically. So these are the dotted ones. So we will see, I will implement one of these ResNets. It's not in our course. It's not in our standard format here, but I don't want to leave this. I will implement this ResNet and I will show you once you are comfortable with the first three algo networks. Okay, so we'll do this. Let's see how we can design and take this. So first thing is we'll do design it. Second thing is we'll directly import the weights and use them. Okay, perfect. So this is what is the expanded or zoomed version of ResNet 34. Yeah, 34 represents the total number of how deep the network is. Now, coming to how to decide how many layers to take and all this part of it. So very simple. If you have around 5 layers in your network, it's a very easy network. Okay, it's not a deep network at all. If you have around 10 layers, including initialization and batch normalization is included, I can say, yeah, it is still an easy one, but a little complex, a little deep as compared to 5. If you go to 30 and 100, these are the real deep networks, especially I'll say that this one is a very deep network. And in this network, if you are using this, you have to identify how to skip the connections because the time is going to be very long. So if you are planning to have 100 layers or even 30 layers, please make sure that you have skipping the connections, the one which you did in RESTnet. So more or less, I can say these are the examples of RESTnets, LSTMs, and all this lot. Okay, and anything above 1,000 layers, I'm not sure. I've never seen in my life. So what? We have no idea about it. How deep is going to be? So if you want to look at one of the layers which is very deep, this could be an example of the Inception network from Google. Okay, look at this, and they have a lot of connections, a lot of skippage is happening here. So what is it? The Inception network consists of concatenated blocks of Inception modules. Okay, the name Inception was taken from the meme image, blah blah blah. We don't need this. Sometime a max pool block is used even before the Inception module to reduce the dimension of the input. So please remember, it is not always necessary to take the image as it is. The way we used to do PCA, same thing we can do it here also. Now, have I shown you any times how to reduce the dimension in image processing?
No.
No. Have I shown you anything on autoencoders anytime? No, right?
No.
Right? I'll show you today. So
No.
if you remember, we used to do SVD, PCA, and FA, and TSNE. I'm not sure even you have done that. Have you heard about TSNE, guys? All right. I will show you one more dimensional reduction technique in machine learning today. But apart from that, if you want to do same thing in neural network, how should we do it? The first way was nothing but your convolution layer. Correct? Convolution was something like shrinking the data itself. But if you look at convolution as data reduction, there is a problem. Let's see how. Let us say this image you are having here, which is say 64 cross 64. And after convolution, before flattening, you got an image, say, which is 5 cross 5. Or you will, I will not say image, I got some data which is 5 cross 5. What we have done, we are able to shrink this up. Okay. Now, can I use this for future processing? If I give it to one of our networks, say LENet, LXNet and all, will LENet be able to identify that this is a part of a larger image like this? Yes or no? Can I do something like this, which I call it dimensional reduction? Is it possible to think about?
Yes, we can do that.
We can do that. Okay, we got one yes. Anybody else thinks it's not a good idea or it's a good idea?
It is possible, yes.
Okay, fine. So from my side, you guys can try this out. If you can do it. If you put a FCNN at the end, yes, it is possible. It'll become your CNN again if you put an FCNN here. But what if I want to send this to some other networks? The other networks will not have the decodings here, right? You remember we have done some encoding here. We have used some filters to encode this data. Have we given them the decoder back? It is like that cipher. I'm not sure if you've heard about this. Let us say you want to secretly communicate something. So what you do is you implement your cipher. There will be a filter which you multiply with all the things and it will create some new numbers. It will look like junk data. Now this cipher, to decode this, you have to divide the whole data by the cipher again. Then you are going to get it back. Correct? Now, this is what I call it as a cipher, whatever we have done here. Are we providing cipher along with that? So tomorrow, if you want to recreate this image, use this cipher. We are not doing it, right? So what if I want to reduce the size of the image and if I want to recreate it, we should be even able to replicate it back. Okay, but in this case, what I will do is if this was 64 cross 64, I cannot replicate the whole thing back. I cannot have the whole sampling done. So what I will do is, yes, if I want to reduce the size to 50%, I will say 32 cross 32. But still I will be, let us say if the number 7 is here, I will be able to vaguely represent 7 back. This is called autoencoders. I'll show you today one implementation also. But on a very high level, this is how it looks like. And if you ask me what is present inside these networks, there are two things which is present. One is called encoding. Okay. Encode. And one is decode. Okay. Now, anybody here from electronics and communication background or communication background, or at least especially DSP part of it? Anybody? Shakti, your camera is on. Huh? Yeah. Anybody from this background, or even from computer science background, you guys would have done it. Encoders, decoders, no? Cryptology or something like that.
I think
Cryptography.
I have.
Yeah.
So you can correlate.
Yeah, studied.
Correct. You can correlate these concepts there, saying that we will have something done on an image, we'll shrink it, and then later on we'll pass it, we will again recreate it and pass it to our network. Now, why do we do that? Very simple thing. I've reduced my dimension, I've retained the data. All right. Now, what are these encode and decode? Very simple. It could be your fully connected neural network. Design a network whose outputs are little lesser as compared to your original input. How many of layers you want it? How will you design these layers? Depending on this. So first of all, you have to decide the decoding size, how much you want to decode up to. Okay, and then finally you design inverse neural networks. Keep training them unless and until we are satisfied that both of them are almost similar. This is called auto encoding. It's not a very popular way to do it, because definitely in future, if I have 7, this image will not be 1 megapixel. Okay, I want to take HD images and shrink it. And if I take an HD image shrink like this, definitely I'm going to lose some data out of it. Everybody agrees to that. We cannot completely recreate this, no matter how good our network is here. Okay, so this is your neural network, simple one. This is also a neural network. You train the weights back and forth till they both sync up. All right, so this is an auto encoder. I'll show you one implementation down the line. Yeah, so what I was asking here. Yeah, so so in other cases, what Google has done is they have done max pooling. So also you can think about max pooling as a dimensionality reduction. Yeah, so let us say if you have an image, say my favorite number 32 cross 32. Okay, now if I want to if I want to replicate this image into 16 cross 16, what I'm going to do, I'm going to max pool by 2. 32 by 2 is 16. Very simple. You can do this, or you can do the one which I showed you. Anything is okay. Okay, so this is your Google Net. We will take this particular network at the end of the module so that you are very comfortable and you don't get confused, because by looking at it itself, it's pathetic, it's horrible. And to understand this, I'm not sure even if this is open source. I'm still seeing to it if we can download it. Else what I'll do is we'll do a very good in-depth theoretical review onto this. What is it and how they got hold on to this. Okay, and what is the application of Google Net? All right, now if you compare the most popular ready-made networks available, you will find them over here. If you look at this, the most stable one is VGG. So down the line, I think almost all of my implementations, you will find VGG itself. It's very simple to work with VGG. Okay, and look at the accuracy also. VGG is not very great. It covers around 65 to 75, but yes, from the parameters point of view, it is showing one of the highest parameters available. More the parameters, better will be your learning. Okay, LXNet and Google Net lies somewhere here. ResNet is somewhere here. ResNet 152. Okay, so 152 in the sense you are having more parameters. That's it. More number of deep layers as compared to 18, 34, and 152. ResNet 50, ResNet 101. So different versions are there. Okay, so this is how you can visualize this particular graph. So I will say, if you guys have decided to transition your career onto computer vision, then you need to know some of the most popular ones like VGGs. I will say LXNet, Base 1, and ResNet 152. So if you know these 3 algorithms, you can say, yes, I know computer vision. Yeah, because they are the top performers, if you see, except LXNet. LXNet is the one very basic one, but these 2 are kind of top performers here. And also try to correlate them with the number of features available. Okay, good. All right. Now coming to the concept of transferred learning. So too much of theory. We'll come down to this very simple diagram. I have got a source task, let us say some task, generic one. I'm putting and I'm running a lot of hardware onto this, and I'm putting it to my knowledge. Now what do I do is I've got my target task. Yeah, let us say our real-time application, which I want to use it on. I get my data, I import your learnings onto my learning system, and I classify my stuff. That's it. So you don't have no more. We have to do the classical, traditional machine learning way of doing it. Train your model and then use your model. No need to do that. Use ready-made learnings to move on. So this is your transfer learning. And if you look at the learning curve also, to be very frank, this is a better one, obviously. And majority of my implementations that I do, I take a ready-made network itself. I don't take a pain of doing CNNs. Now you may ask me, okay, fine, then why are we learning it? You will understand CNNs, the use of it after week number 4, where we enter RCNN, fast RCNN, YOLO, SSD, all the complex algorithms that we enter. No? At that time, again, we have to use CNNs. We have to use some part of it. So the concept of building CNN is important. Okay. Great. So I think we are done. Yeah, too much of theory. So what do we have today is we have got a very simple data set where we have got data splitted already into test and train. Okay. And what do we have inside? Both of them, we have same 5 folders, and each folder is having some flowers which belong to each one of them. Okay. So this is what is the data. Our job here is to classify the flowers from the testing part of it. So we'll train it using our training data, and we'll use this particular chunk to classify them. As simple as that. So the upper ones is the upper code is for the people who want to use Colab. So I'll start from here. So this is my Keras. So now I think you guys are comfortable on the sequential part, convolution 2D. As soon as you say convolution 2D, max pooling comes into it, flattening it, dense and dropout. Now I'm not sure with version 2.0 whether this is going to work good, but I think from here it looks like something like this from TensorFlow Keras, and then everything goes save. Okay, you'll have to make some modifications. You might get some errors if you have latest version. Now moving on directly to the classifier. So if you look at this, I have got 32 3x3 filters, and I've got an input shape of 64x64x3. So very simple. Padding is 0, stride is 1. Just put the formula. 64 minus 3, that is 61. 61 by stride is 1 as usual, plus 1. That means answer is going to be 62. No. 1 minute. Answer is going to be
62.
62 only, no? Then why it's not working? Because the next one is 3x3 32. Okay, so rather than taking this approach, what I will say is we'll take this particular approach. Say 64 into 64 is what? 4096. Okay, 4096, when you pass it through your max pooling function of 2x2, what are we doing? Basically, we are dividing it by 2. So when you divide 4096 by 2, you are going to get 1096. 1096, again, you max pool it. You are going to get, I'm sorry, not 1096, sorry. You are going to get 20. How much? Can somebody help me here? I'll have to get my phone. 4096 divided by 2 is 2048. Perfect. Now 2048, when you again divide it max pool by 2, divide this by 2, you are going to get 1024, right? And 1024, when you again max pool it by 2, we are going to get 500. Correct? So now if you look at my activation, okay, there's a lot of noise. If you look at our input for fully connected neural network, our neural network ends at 512 as flattened. Okay, so take this approach of solving this problem. Yeah, so as per me, this I'm not changing the filter size, it's working good. Now this is not an optimal solution. I'll create some problem statement and give it to you. You guys play around with the layers more and more, but make sure that at the end it should match with your input of your fully connected neural network. As simple as that. Okay. Now, if you look at it, what we have on the first layer, we have 32, 3 cross 3. This is my input, standard stuff I'm using, no changes here. Second one also standard, third one standard, same thing. This is 512. And once you enter a fully connected neural network, I'm saying give me some dropout. A dense layer could be, say, divide by 4 of this, for example, and activation function is ReLU. And finally, if you observe, I have got 1, 2, 3, 4, and 5 classes. So obviously, my total number of outputs is 5, and my layer is softmax. So now I think we are good at it. Right? So this is a simple CNN that I have designed. Now moving on, I wanted to show you something a little bit more here, wherein we are calling our Adam, okay, and we are putting into our compiler. But apart from our learning rate, if you remember, we have not used these functions so far. Now, what are these? How do you check this? So one way to go and check all of the activation thing is you can go to Keras documentation and go to optimizers. You will get list of all the optimizers available, which is SGD, RMS prop, ADA grad, AMS grad, ADA delta, Adam. Adam is the most common one, and SGD is also most common one. And if you have a deep network, you can use an RMS propagation, RMS prop. Yeah. So I'll show you down the line how you can use this also. Now, what are these extra terms? So these all hyperparameters are defined there anyway. So the first thing is your decay factors. Now, everybody gets what is a decay, what decay I'm talking about. If you remember, the gradient descent that we have, is kind of decays down. So the standard values, if you don't even initialize them, the standard values are going to be this only. So I'm not playing around with this anymore. I'm just trying to show you that tomorrow, if you increase your learning rate, your decay is going to be more steeper. So if you look at it, beta 2 and decay rate, if you add them up, you are going to get standard answer is 1. So please keep a good check on both of them if you are playing around more with learning rate. And also, if you observe, there is something called beta 1 and beta 2. Both of them represent decay rate. So this could be the decay rate for the first estimate. First estimate, let us say it could be the first dou function that you do from your backprop. And this could be the estimate, the one from the second estimate, the second one. Yeah, usually we don't play around with this. Even on web, you will not find many implementations who have done this, but just wanted to give you some hyperparameters here. And the last one is epsilon. It makes sure that we don't misclassify anything, or we don't basically go into infinity state. So in none of our implementations, we are doing any operations with zeros. If you observe that, we are not adding or multiplying or dividing any of the zero part of it. Some of the neural networks or machine learning part of it, Keras, we do some manipulation with zero. So in this case, it will make sure that we don't do it. So by default, we keep it off. Okay, we are not worried about this. So these are some of the hyperparameters. And as usual, we are using categorical cross entropy because I have got 5 outputs and my matrix is nothing but accuracy. Right? Next thing, we have not done any data manipulation. That means we have not cleaned our data. So now what I'm doing is I'm augmenting my data. Now, if you don't want to write a separate function for augmentation, and if you want to do it as per stuff, what you do is you import image data generator. This is the function. So it will give you a lot of parameters. Some of the important ones are these, wherein rescaling the image, you are rotating the image, you are zooming the image, you are flipping, horizontal flip, vertical flip, all those things. Yeah. So this is the way you can create some kind of augmented images if you are not happy with size of data. Same thing, you can do it with your test data also. Okay. Next thing, you call your test data from the directory and you say clip it to this size. Select one size. Why 64, 64? Because you have designed a CNN which input 64, 64. 3 is the number of channels. Okay. So match it up. Next, total number of images you want to pick up in one run. So depends on your computer. If you have a high-end RAM for it, I will say increase the size of this. Now, can somebody tell me why do I need to focus on increasing my batch size? What difference is going to make even if I specify this or if I don't specify this? What is your understanding of batch size? What do you mean by batch size?
How much data it processes per epoch?
Correct. So why should we take 32 here? Why can't I take a more number? Correct. So please remember, if you want to speed up total number of, so if you say 20 epochs, and in each epoch, say you are picking up around, your computer is keeping ready 32 images to be processed. What if I give more flexibility to my computer and say I will double it up? Just observe, by changing the size of batch, just observe your epochs. The total time taken by 20 epochs to run with 32 and the total time taken by 64, and let me know what did you observe.
It might slow down.
Kind of, yes. Okay, so again, it is very important basically to select this. So what I usually do is I divide this number by 2. I know logically it's not correct. I divide this by 2 and keep some familiar number here. That's it. Okay, so there is no logic onto that, but yes, high-end computers can do it. My computer will crash if I take 64 or 128 here. Now moving on, same thing for your test. I'm taking the same part of it. And finally, you are fitting your data using the generator one so that you can get good augmented images and say this is my training set, this is my validation data, and in your epochs, say I want to run 20 epochs, you are seeing something new here today, which is called steps per epochs. Now what do you mean by that? In one epoch, I want that particular epoch to run these many number of times. So what is 3823? 3823 is the total number of training images we have, divided by how many of them are picked up at a time? 32. From where? From here. So I'm saying is, even if it is not an integer, convert it to an integer, and each epoch, inside each epoch, you give me that many number of steps. So either you can have more number of epochs or you can have internal steps within epochs, whatever suits you. I gave you both the options. So far you would have seen only this, right? Okay, so this is what you can do it. I say this is a better option so that we get to know that if in case one epoch we are running 119 times again and again, probably I'll say within 4 to 5 epochs we'll be able to get better accuracy. So if you observe here, the amount of accuracy change is pretty high. So this thing is turning pretty good rather than having 40, 50, 100 epochs. You have to wait a longer time for that. Even this will be longer because we are inside each epoch are having these many steps. So definitely it's going to take longer, but the accuracy part of it will be pretty good. So if you scroll down the line, I ended up at 20 epochs. So after certain epochs, you observe it is not going further. The accuracy is going down. Now there could be multiple reasons for that. The first reason could be the way we have chosen the steps, but this is the only way to do it. Second could be we have done too much of augmentation, might be, so that we are not able to find some pattern. Third one could be our learning rate and the optimizer. And the most important reason could be the CNN layers that we have made. Okay, so I chose totally to make 4 layers. Why? Because our ELINet had that option. So I did that. But what if I don't want this? I want to increase my accuracy here. So I give it to you guys by next Friday or Saturday maximum. Send me your inputs, how you can improve this. All right. You don't need to do this on the industry side because we have got ready-made networks. But anyway, if you play around with these numbers and also check the blog that Dhruv has given, it will help you guys to formulate it. Delete one layer, add one layer, or I have taken a max pool size of 2 cross 2. You can take 4 cross 4 also, no problem. 3 cross 3 also, no problem. And I have taken standard filters here. You play around with the filters and see how it happens. But the only issue is don't run 20 epochs. You are going to waste your time looking at your monitor. So try to run less number of epochs and see how much accuracy is increasing down the line. Okay, so here we have got around 80, loss is 49, and validation loss is 90, and validation accuracy 64. So I will still say it's not a very good model because it's an underfit model. Okay, good. So this is one implementation on CNN. Now, what if we, so now a little different way of coding this. So giving you guys a hint of how you can save your model. So first of all, what you guys do is every time you kill your kernel, you come back, you have to rerun the model. If you don't want to do it, use this two options, wherein you have an option to save your weights, whatever weights you have, so that you can import it in the next network whenever you need it, or you can save your whole network as it is. So this is one way to do it. Another way is to do called what is called joblib. So there is a library called joblib which does it, or there is something called pickling. If you want to see all these three today, I will show you down the line. If you are happy with this, usually in CVs, computer visions, we do this only. We don't do joblib and pickling. For machine learning, I can say these two are good. Okay. But in machine learning, we don't have weights to be stored. But here we have an option. Either you store the classifier itself or the weights, any of this. So now what I've done is I've pickled them so that I don't have to rerun every time I open my code. Down the line, what I'm doing, I'm calling back my model, calling back my weights, both of them together. All right. Now, once I do that, what am I doing is I'm reading some random flower or set of flowers. Okay. And next, I'm changing the dimensions. Basically, I'm reshaping them. I'm changing the dimension. I'm changing the values of it by normalizing it. Finally, I'm saying display the name of the flower that I'm going to pick it up. Okay, the dimension of the image that I'm going to pick it up. And finally, I run my classifier. I predict that particular image onto this. Yeah. So if you look at the output, this is the size of my image. This is the image after expansion. Yeah. Next, this is the set of options that we have. And out of these options, if you look at the softmax output we have got, can somebody hint out if this is my softmax output, which one of this is the classified answer? Sorry?
Daisy.
Daisy, exactly. Why? Because look at the probability. Softmax is nothing but probability. The one with the highest probability will be the answer. So in this case, we identified, anyway, it's displayed here. But yes, please look at this stuff. So this is not needed, but anyway, we got the answer directly. So now whatever image we gave was a Daisy. Now, what if I want to run it across the whole testing data and generate the matrix? So very simple. I'm just getting all of my test data from the path, putting the hyperparameters and running the model onto that. When I do that, I get a confusion matrix like this. And if you look at this, these are our flowers that we are talking about. And if you don't want to do that, there is precision, recall, F1 and support for us. Now, what is precision? We know, recall we know. What is F1? F1 is a balance between both of them. Okay, I kind of say average between both of them. And what is support? Support will say how many images of this class are present in the whole data set, the frequency of it. So it's something like our target. We used to do dot value counts, if you remember, to check the target. Same thing like that. In this case, good representation. But if you observe the precision recall, they are not that great. So the one which gets classified the best is this one, sunflower. All right. So this is a very simple image identifier.
I have a question. How do we read that matrix that is shown above the?
Yes. Yes. So in this case, how you can read 67 of daisies have been identified properly. Okay. Now, out of that, 12 of them, which are actually daisies, are identified as the next one, dandelion. 13 of them are identified as rose. 3 of them as sunflower, and 5 of them as tulip. Okay, so find out if you want insights out of this, you can find out the flowers which are very close to each other. So in this case, you can say that daisy and rose. We can say, or daisy, rose, and dandelion. They look almost similar. Why? Because the misclassification is maximum here. Or else if you look at the last 3 of them, which is rose, sunflower, and tulip, the misclassification is happening too much. So tulip, by mistake, is getting classified majorly as tulip, and rose are getting confused. Okay, so this is how you can read it. Good. And if you want to look at the correct classifiers, look at the diagonal elements. They are the correct values of your classification. All right. Amit, okay?
Yeah, thanks, Krishna.
Perfect. Good. So this is one simple CNN example that you can see. Let's try to. So this is one way you can do transferred learning. One way I showed you, but that learning was not from any of the normal better networks. It was our own network. Now let's try to see one more data set where we can do.
Sir, I have a question on last
Please
neural
tell.
network.
Yeah.
Why we used padding as same?
We are not doing padding. That's what we mean by that.
Okay.
Padding is 0.
Okay.
Okay. So what I did was I kept it very standard. So I want you guys to basically do all the mix match possible and try to create your own network. Yeah. All right. Good. After that,
Right
yeah.
now, in the case study that we just saw, it was a continuation, right? Where we were loading the model that we created at the upper part. So does that mean the kernel is restarting when we are loading the model again?
Yeah, the kernel is anyway.
It's the same workbook because.
No, see, what you can do is when there is a lot of noise on it. I'll just mute. Okay. So now you mean to say is that when I switch off my kernel and when I restart, will I be able to get the same model back? That's what you're trying to ask me, right?
Do I have to re-import the entire program, or it's just from the load model part?
Just load model part. That's it. That's it. But if you are loading your weights onto your new model, wherever you are loading, we have to make sure that the weights that we had over here, no, the infrastructure that we created here should be same as this. So if your new, say, new network should look something like this. It should have at least these many layers to put the weights onto. Got it? So it is like your machine learning part. Let us say you trained your machine learned model onto 4 variables. Now, when your model is ready, when you're predicting it, if you're predicting on 3 variables, what's going to happen? It's going to crash. Why? Because it was not one more variable is missing. So you should match this up. That's it. But yes, you are perfectly right. You can do it on any of the other codes, not only on this code, you can import it somewhere else also. All right. Only thing we have to make sure is we have to get the good correct path of the file, or else what I usually do is I put it in a local directory itself, wherever I'm using the code, so that I don't have to take a headache of copy.
Yeah, so right now in this example, we saw there are images in the folder.
Yeah.
But in the case study or in the project that we have a H5 file, which I think is a conversion of images into some different, right? So I just wanted to understand why here we are, because we are also saving here in H5 part. But is it that we will get what do you say, the coded part H5 file sometimes and sometimes images, and based on that we have to take it into account? Because the way this was this data set was loaded is something in a different way compared to how we load it.
Okay, so I think you were not there in my session when I explained the HDF format, right? I think this is your second session or third session, no?
It's my second.
Second, okay. So you were not there when I explained HDF basically. What is this HDF format? HDF format is a zipped file, you can say, okay, which will consist of lot of matrices. Okay, now each matrix represents an image over here. Okay, and each image has a target variable attached to it. So in your previous project, if you remember, the target column was what number it is, and the sampled part of image was stored as a matrix. This is what is HDF format. Now in our case, what we are doing is when we are storing it as an H5 format or any other format, what happens is it tells me, or it gives me some kind of mapping that this is, say, layer number 1, and these are the weights of layer number 1. This is layer number 2, and these are the weights of layer number 2. So whenever I import this, okay, Python interprets this and directly starts loading these weights in our current infrastructure. Got it, Amit? If you want to see in detail, give me some time. I will make one specific case study on what are the different varieties in which we can import and map the data. If you want to do that, you can do that also. We have zip format, we have tar format, we have got HDF format, we have got HDF4 format, we have got H5 format, then we have got JPEG and PNG format also. Multiple ways we can do it. We down the line in one of the case studies, even what we have done is we have done embeddings. That means we have directly imported the image and tagged it ourselves. That's our own format. If you guys want to see one specific case studies on all the imports, we can do that also. No problem. Let me know. Okay.
Yeah, sure. That will be great.
Perfect. All right. So can we move on, Amit? Is it good now? You're clear about it? Yeah. All right. Hey, one more. I did not ask any of you. Project is submitted, right, by all of you. I think even the score is out. Anybody wants to discuss the project solution? Do let me know. We'll do it. Okay. The previous project. Let me know. I'll dump the solution anyway, but I'm not sure whether I've discussed the solution with you guys or not. Please remind me, okay? I might forget sometimes. Now, coming to, okay, we'll do this autoencoder last. Okay. Now, coming to this particular data set, we'll do one thing. We don't have enough time to go through the whole data set, so we will revisit it's a huge, basically huge case study. So for now, what I will show you guys is I will show you how to import findings and how to load it on the network. Okay, so just think about it, that there is a data set that I have which has different breeds of dogs. Okay, and they have the photographs and embeddings inside of these breeds. The same way we had flowers, now we have got different breeds. I think we have around 19 or 20 odd unique breeds available here. Now what are we doing is we are building our own convolution neural network as usual, my normal pattern of building it. So I'm starting with some number, say 32, 5 cross 5. Okay, and my input size is exactly same as the size of my images, which is 128 cross 128 cross 3. All right. Next, say I'm having a filter size of 64 cross 64. Sorry, total number of 64 filters, 4 cross 4 each, kernel size. Yeah, and I'm keeping the standard functions the same. So I've got 1, 2, 3, 4 layers, and after that I'm building my dense layer. Very simple. And the total number of unique outputs we have is 120. I'm sorry, I said 90, but its total unique breeds are 120. All right. So this is one example of a CNN that we are building. Now, when I run my CNN down the line, let me show you. So when we run the CNN, yeah. So when I run my CNN, say for example, for some number of epochs, say for 1 epoch, and each epoch I have taken a step of 8177. That means I am running 8177 epochs as of such. When I do that, look at my validation accuracy and normal accuracy. I'm getting 0.08. That is 0.8% of accuracy, and validation is 0.01. That is 1.1% of accuracy. Underfit model, definitely. Yeah. Why we got this? Because of whatever stunt we did over here by creating our own CNN. All right. Now, what if we are stuck in this situation? We don't have time to play around with multiple stuff over here. So in that case, what we can do is we have got standard VGG 16 weights. The only thing is there is a file which we have to store it. Either you can download it, yeah, from here. You can give the reference over here, or I can put it in my local directory and give a reference like this, whatever you wish. Yeah. So I'm saying this is my new base model. This is my new model that I call base, and these are nothing but VGG 16 weights. And here you define the location of your H5 file from where you are getting them. So if you observe the format of this file, and if you observe the format of this file, they're exactly same. So basically this format is used to store this up. Next thing, what I get is I reinitialize, like put my X and Y again. So basically I reinitialize my target column and training column. Now in this, only one thing I wanted to show you guys something new was TQDM. Now TQDM is a method of generating this status bar. If you observe, what is the current status of it? If you want to, because sometimes when the epochs are running, we are not sure how much time it will take. So definitely we have a timer here, but yes, if you want the whole stack, TQDM will help you to do that. All right. Now, next thing is, what are we doing is we are getting all the images one by one. And once we get the images, we are passing the images through our base model. What is a base model? Base model is a model that we have defined by building our VGG. So I am indirectly telling them, I don't want to take this through my neural network, my FCNN, or my normal network where I am doing forward and backward. For now, you pass on my inputs through my new weights. As simple as that. All right. And once we do that, we are building our fully connected neural network, the backend part of it, the final part of it. And then I'm compiling it. And finally, we are running it. Did you get it? How I froze the layers? Because if you remember, we are not supposed to backpropagate this. So if I would have put the weights here along with our model.fit, what's going to happen? It's going to do backpropagation and change all of our weights. I don't want to do that. So first itself, I'm running my inputs through our weights. I'm multiplying them. So it is nothing but your input is there. This is your input and these are your weights. You're directly multiplying it and making it as one particular matrix. Now you use this as your X train, basically, onto your final model. Got it? And when you run the model, if you observe, the last accuracy we got is around 98.39%. So it's a better model than the one above. Are we clear? Guys, any confusion onto this? The freezing part of it and non-freezer part of it?
Freezing is multiplying our current input with weights.
Weights, exactly. So what I'm doing is, in hurry, I'm having my images or my X training data. I'm saying it, whatever weights I've got, multiply with the inputs and make it a bigger matrix. And now use this as your training data with your FCNN to do front and back propagation. Now, even if back propagation happens, do you think it will change anything for training data? Nothing. It will change everything on your FCNN only. Because it will not get it that this is a neural network. And what are weights? Weights are nothing but some kind of matrix. Very simple. All right. It'll take some time. So it'll take a week's time for you guys to get normal to this way of coding it. Yeah. So give some time, try exploring this. So now I will deliver both the codes to you. What you people do is, in this particular, the earlier code that I've shown you, instead of using my model, you use this VGG16 model and see if you are able to improvise. Okay. And this, from here down the line, it's a universal code. It will work for anywhere. No problem at all. Good. Everyone clear? Let me go through. Harish, Akash, Avmeet, Dhruv, Kaushik, Kranti, Raghu, Saurav, Shakti. Are we all clear on this?
Yes.
Yeah.
Krishna,
Yes,
for
yes.
this one, you have imported OpenCV.
Yeah. So yeah, that will come to it. So the way we are getting the images will come to that. That's what I'm saying. We'll do this. We'll redo this case study in detail.
Okay.
So it's supposed to be a mix between week 2 and week 3 actually. It will be very heavy if I go through it right away.
Okay. Sure.
So we'll redo this, but I just wanted to give you the idea of transferred learning. This is how we do transferred learning majorly. I don't waste my time doing this. I'll directly pull out the data. Right? The only drawback of transferred learning is, first thing is you have to, I will say, completely depend on their weights. Tomorrow, if they remove the stuff from online or their support, we are helpless. The model will go down. And second issue is that if the weight is not trained on that particular set of images, let us say you want to build a neural network on space images. Now we should have some network pre-trained on that, right? If it is not trained on that, then we'll not be able to use it. That's the only two issues. Otherwise, everything works good. Okay. Perfect. Yeah. So these are the two. We'll redo this. We will go through again, and if possible, we'll do live coding so that we get hands on to the complete coding part. Yeah. And also I want to give you the complete flow. So what is the standard flow of a CNN? Okay, what do we do? What should we do? And all this part. Okay, so this is one thing. Now let's come to something onto auto encoding. So if you remember that dimensional reduction technique that I was talking about, a very simple code where we have the same MNIST data, handwritten data, and this is the original image, and this is the undersampled image, or I will say the dimensionally reduced image. Good. How do we do that? Get the libraries, get the data, reshape the data, normalize the data. Decide that from this level of input, how much you want to come down to. So say I want to come down to 64. Depends on you how much you want to reduce the dimension to. Okay, so once I come down to that, you do all the resizing, all reshaping thing on the image part of it. Next, we have to call our model. So if you observe here, what do we have? We have got an input. So I just explained you guys what is on the autoencoder. This is your real input. Then you will have some encoding part of it, and then you will have some decoding. This is encoding, this is decoding, and this is your output. Okay, so this is my input, this is my encoding layers, this is my decoding layers, and this is my autoencoder layer. So if you observe here, I'm not writing multiple layers, I'm just writing normal dense layers here, and other things I think are self-explanatory to you guys. All right, so this is another alternate way of creating a Keras dense model. 4 lines, enough. After that, what are we doing is we are calling our backprop and fitting the model. Now, while fitting the model, what are we doing? We are increasing the batch size. We are having some epochs. We are saying shuffle is equal to true. Shuffle in the sense, if you want, you can do some augmentation part of it. And test and train split we are doing here. We are saying 80-20 split, basically. Okay. So validation is nothing but our testing data. So when I run it through, and if you look at the accuracy part, I get around, okay, there is no accuracy here. I'm really sorry because we did not put the metric over here as accuracy. I just wanted to see the loss part, how much loss we are having. And if you observe it, the loss percentage is not that great between both of them. All right. Now, how we see this image, how do we observe whatever we have done is good or bad? So in that case, we'll call the autoencoder.predict onto our testing data. And then finally, we'll plot the original data versus the testing data. So the only showstopper here is IM.show. That's it. You are supposed to know this. Okay. How a matrix gets converted to an image, IM.show. As simple as that. And what shape and size you want, even you can specify. So here I've got 28 cross 28. This is the original image. This is the dimensionally reduced image. Now, if we are not happy with this, so let us say if you are making a implementation where when a security guard, let us say, runs the device through some of the cars, they will get the number plate automatically, or by looking at the logo, they will get the make of the car, or by looking at the car, they'll get the color of the car, anything. Here, you don't need a HD image, basically. You don't have to compute or spend a lot of time and money on hardware onto this. Reduce the image and then compute onto this. This could be a very simple application. Okay. So this is your autoencoder. Good. There is one more dimensional reduction technique. I'm not sure if you guys have heard about it. Have you heard about TSNE?
No.
It's part of supervised learning. No? Yes or no? No, right? Okay, let me know if you guys are interested. I will show you something on this also. It's
Yeah,
not
sure.
a part of our course anyway, but it is. I feel it's a little important sometimes. So let me show you first of all why we need TSNE and where and all in deep learning you will need it. So something off the track, huh? Not as a part of our course. This is what we do in industry. I don't want you guys to miss it. Say I have module number 1 minute. Huh? Yes, got it. Okay, so it is a part of NLP. So I showed something extra to some of my batches. Now, if you look at computer vision, we saw today what all transferred learning can be done. That is VGG, ImageNet, LXNet, LeNet and all. Same thing you can do it in your NLP also. where we already have some kind of encodings available, ready-made. So the first encoding that we can see here is glove. Another one could be, Elmo. Another one could be Word2Vec. So Word2Vec is developed by Google. So these are standard embeddings that we have. We directly import it and start using it. This is what we mean by transfer learning. So again, it's an example. So what if I say that in our text, so what is this case study about is we have got a huge text available with us. Now I want to know that, let us say, I want to predict something. So I will say the prince, today's prince will be tomorrow's question mark. Okay. So what we can do out of this? So I will say today's prince is tomorrow's dash. What is it? So obviously you guys will know, okay, prince is nothing but tomorrow he'll be a king. What if I remove the prince and say today's princess, or today's queen will be tomorrow's what? We don't know. So this is used when you want to do some kind of prediction. Now the best example I'll give you is LinkedIn. So when you are messaging on LinkedIn, you guys have observed now. So for example, if Harish sends me a message on LinkedIn, something, so it will give me some kind of tokens if you have seen it. It will first say, hi Harish, good morning Harish. Sure, depending on the data or what is written on that, it will also predict me, sure, we'll meet tomorrow, or sure, I will do that, or something. How do we get these predictions? We use something called RNN. Okay. We use RNN to do this. Now, what is RNN? It's a different network, recurrent neural network. We'll do in NLP anyway. But RNN auto uses, or we can sometimes auto use glove. Glove is the way you did VGG and all in CV. In NLP, we can say ready-made network. So this is called global vectors, basically, and it is developed by Stanford University. Now, what I will do is I will show you. What if I want to predict what is the nearest encodings to king? So from our corpus, if you remember what is corpus, I've showed you our chatbot. Corpus is a set of huge data available to train your model. Okay. Now, what if I say, give me the top 5 words, 1 to 6 means 5 words, which are very near to king. So if you observe queen, monarch, prince, kingdom, and reign, from our corpus, he is able to find these are the 5 predictions. Which one you want me to send? So I will say share the top 3 predictions always. Something like a recommendation system, I can say, for text. All right. Now, why am I showing you this? Because here, if I want to represent this, what if this is all backend? I'm sure you guys wouldn't have understood what is the data, what is he talking about. If I want to represent this, what if I represent my tokens from my corpus? Are you able to visualize this? Not very great, but you are able to see that yes, there are some words which are tightly packed. That means they are very near to each other. There are some words which are almost away, but yes, they are nearer. So if you can observe university and college, okay, school and education, hospital and health, you can observe that these words are tagged together. Now, if you ask me how, that's again a different topic, how I tag them together. But glove will help me to do it. Okay, so how I represented this? How did I convert a higher dimension image to a 2D image like this? We use TSNE over there. So let me go to TSNE. What is TSNE? In a very simplistic way, it is a supervised learning dimensional reduction technique. So far, we have done unsupervised learning dimensional reduction technique, that is PCA, right? In this case, what we'll do is we will say there is a 2D data and we have got 4 points, say 1, 2, 3, 4. I will say this is point number A, this is point number B, point number C, point number D. Now I will say the distance between, okay, let me not give the answer now. I will ask you guys, what are the similarity measures that you have seen so far? Guys, how I can find similarity between 4 points?
Cosine similarity.
Distance.
Cosine similarity, Pearson similarity, and distance. This works majorly. Okay, so in this case, let me say that I'm saying distance could be one of the similarity matrices. So I will say, for our convenience, I will say each one of them is at a unit distance from each other, and the diagonal elements will be a distance of square root of 2 from each other. Agreed? Pythagoras theorem. Yeah. Now, how would I reduce the dimension? Let me ask you. I want to reduce the dimension to 1D. How should I do it? So to do that, okay, let me not ask you. Let me show you something, then I'll ask you. To do that, what I will do is I'll pick up a point of reference. Let us say I'll start with A. I will put A over here. Now, next to A, what do we have? We have B, we have B here at a unit distance, and we have D at a unit distance. So now, if I say the distance between A, D, and B. So now we are kind of close. So if I keep distance in my mind, and if I replicate them on a 1D space, I can transform them like this. Now, please remember, how am I transporting? I'm saying that I will make sure that I don't change the distances. And right now, the similarity matrix between all of them is distances. So I have maintained distances between A, B, and D. Agreed? Everybody agrees to that? Now, what about C? Where should I place my C? What if I place it here? Because if you remember, the distance between D and C is 1. Correct? And the distance between A and C is also square root of 2. So if I place it here, if this is C, what is going to happen? B and C is going to be far away, whereas B and C is kind of 1 itself here. So what if I place C here? Now it's satisfied, but now D will be an issue. So A is anyway satisfied with both of them, but D and B are creating some issue for C. So this is a problem if we take this configuration.
Alright guys, this brings us to the end of the deep learning tutorial in Python video. We took a look at a lot of different things, right from having the understanding of all the libraries which are extremely important from deep learning, all the way to taking a look at important concepts which we require in machine learning. After this, we took a theoretical and a practical understanding of the concepts of deep learning and neural networks as well. Finally, we also understood how computer vision works and everything associated with that as well. With this, I hope we are clear with all of the concepts that are covered in this particular video. Make sure you guys are subscribed to the Great Learning YouTube channel to get notified as and when we post more of these videos. Thank you so much for watching. I'll see you on the next one.
I want to introduce you to Great Learning Academy, a free initiative by Great Learning. You can access over 200 plus courses with 1000 plus hours of free content on trending high demand domains absolutely free. Register now to complete the course and get your free certificate of completion. Check out the link in the description of the video below. If you haven't yet subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notifications bell so that you do not miss out on any new updates or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing. So make sure you share this video with your friends and colleagues. Make sure to comment on the video if you have any queries or suggestions, and I'll respond to your comments.